Disclosure to promote the right to information. Whereas the Parliament of India has set out to provide a practical regime of right to information for citizens to secure access to information under the control of public authorities, in order to promote transparency and accountability in the working of every public authority, and whereas the attached publication of the Bureau of Indian Standards is of particular interest to the public, particularly disadvantaged communities and those engaged in the pursuit of education and knowledge, the attached public safety standard is made available to promote the timely dissemination of this information in an accurate manner to the public. 1 plus Mazdorki San Shakti Sangathan. The right to information, the right to live. 015 Jawaharlal Nehru. Step out from the old to the new is 456, 2000. Plain and reinforced concrete, Code of Practice Set 2, Cement and Concrete. $+ Satyanarayan Gang Aram Petroda. Invent a new India using knowledge. 0b Bharthariantiyatakam. Knowledge is such a treasure which cannot be stolen. Is 456, 2000, R. Florum 2005, Indian Standard Plain and Reinforced Concrete, Code of Practice, 4th Revision, 10th reprint April 2007, including amendments No. I and 2, ICS 91.100.30 July 2000 CBI 52000 Bureau of Indian Standards Manak Bhavan. 9 Bahadur Shah Zafar Marg New Delhi 110,002 Price Rs 830.09 plus Rs 120.09 Contents is 456, 2000 Page Section 1 General J Scope, J2 References 11.3 Terminology 11.4 Smbu 11 Section 2 Materials, Workmanship, Inspection, and Testing 5 Materials 13.5.1 Cement 13.5.2 Mineral Admixtures 13.5.3 Aggregates 14.5.4 Water 14.5.5 Admixtures is 5.6 Reinforcement 15.5.7 Storage of Materials 15.6 Concrete 15.6.1 Grades 15.6.2 Properties of Concrete 15.7 Workability of concrete 17.8 Durability of concrete 17.8.1 General 17.8.2 Requirements for durability 18.9 Concrete mix proportioning 22.9.1 Mix proportion 22.9.2 Design mix concrete 22.9.3 Nominal mix concrete 23.10 Perdolone of concrete 23.10.1 Quality assurance measures 23.10.2 Batching 24.10.3 Mixing 24.11 Formwork 25.1 J.1 General 25.11.2 Cleaning and treatment of phonework 25.11.3 Stripping time 25.12 Assembly of reinforcement 25.13 Transporting, placing, compaction and curing 26J3.1 Transport and Gond handling 26.13.2 Placing 26.13.3 Compaction 26.5 is 456, Z000 13.4 Construction joints and cold joints 13.5 Curing 13.6 Supervision 14 Concreting under SBECIAL COSORNAS 14.1 Work in extreme weather conditions 14.2 Underwater concreting 15 Sampling and strength of designed concrete mix 15.1 General 15.2 Frequency of sampling is 0.3 Test specimen 15.4 Test results of sample 16 Acceptance criteria 17 INS ECRLO N and testing of structure Section 3 General Design Consideration 18 Bases RLR Design 18.1 Aim of Design 18.2 Methods of Design 18.3 Durability, Workmanship, and Materials 18.4 Design Process 19 Loads and Forces T 9.1 General 19.2 Dead Loads 19.3 Imposed Loads, Wind Loads and Snow Loads 19.4 Earthquake Forces 19.5 Shrinkage, Creep, and Temperature Effects 19.6 Other Forces and Effects J 9.7 Combination of Loads 19.8 Dead Load Counteracting Other Loads and Forces 19.9 Design Load 20 Stability of the STRUC1 LJRE 20.1 Overturning 20.2 Sliding 20.3 Probable Variation in Dead Load 20.4 Moment Connection 20.5 Lateral Sway 21 Fire Resistance 22, Analysis 22.1, General 22.2, Effective Span 22.3, Stiffness 6, page 27, 27, 27, 27, 27, 27, 29, 29, 29, 29, 29, 29, 30, 32, 32, 32, 32, 32, 32, 32, 32, 32, 32, 32, 33, 33, 33, 33, 33, 33, 33, 33, 33, 33, 33, 34, 34, 34, 3.5, 22.4, Structural frames 22.5, Moment and shear coefficients for continuous beams 22.6, Critical sections for moment and shear 22.7, Redistribution of moments 23, Beams 23.0, 23.1, 23.2, 23.3, Effective depth T-beams and L-beams, Control of deflection, Slenderness limits for beams to ensure lateral stability 24. Solid slabs 24. 124.2, 24.3, 24.4, 24.5, General slabs, Continuous over support slabs, Monolithic with support slabs spanning in two directions at right angles, Loads on supporting beams 25, Compression members 25.1, Definitions 25.2, Effective length of compression members 25.3, Slenderness limits for columns 25.4, Minimum eccentricity 26, Requirements, Coverning, reinforcement and detailing 26. General 26.2, Development of stress in reinforcement 26.3, Spacing of reinforcement 26.4, Nominal cover to reinforcement 26.5, Requirements of reinforcement for structural members 27, Expansion joints section 4, Special design requirements for structural members and systems 28, Concrete corbels 28.1, General 28.2, Design 29, Deep beams 29.1, General 29.2, Lever arm 29.3, Reinforcement 30, Ribbed, Holu, W block or Volden slab 30.1, General 30.2, Analysis of structure 30.3, Shear 30.4, Deflection 7 is 456, 2000. Page 35, 35, 36, 36, 36, 36, 36, 37, 39, 39, 39, 39, 39, 41, 41, 41, 41, 42, 42, 42, 42, 42, 42, 45, 46, 46, 50, 51, 51, 51, 51, 51, SI 51, 52, 52, 52, 52, 52 is 456. 2030.5 Size and position of ribs 30.6 Hollow blocks and formers 30.7 Arrangement of reinforcement 30.8 Precast joists and hollow filler blocks 31 Flat slabs 31.1 General 31.2 Proportioning 31.3 Detonation off bending moment 31.4 Direct desip method 31.5 Equivalent from method 31.6 Shear in flat slab 31.7 Slab reinforcement 31.8 Openings in flat slabs 32 WAUS 32.1 General 32.2 Empirical design method for walls subjected to in-plane vertical loads 32.3 Walls subjected to combined horizontal and vertical forces 32.4 Design for horizontal shear 32.s Minimum requirements for reinforcement in walls 33 Stairs 33.1 Effective span of stairs 33.2 Distribution of loading on stairs 33.3 Depth of section 34 FOOT1 NOS 34 J General 34.2 Moments and forces 34.3 Tensile reinforcement 34.4 Transfer of load at the base of column 34.5 Nominal reinforcement section 5 Structural design, limit state method 3 Safety and service ELIOI year surrounds 3S.1 General 35.2 Limit state of collapse 35.3 Limit states of serviceability 3S.4 Other limit states 36 Characteristic and design VALTMS and PAR11AL Safety failures 36.1 CH8 Characteristic strength of materials 36.2 Characteristic loads 36.3 Desip values 36.4 Partial safety factors 37 Analysis 37.1 Analysis of Structure 8 PAGBS 252 53 53.5 353 S3 S3 54 56 S1.59 61 61 61 61 62 62 62 63 63 63 63 63 63 64 65 SIXS 66 67 67 67 67 67 67 67 67 68 68 68 68 38 Limit Statbook Collapse, Flexure 38.1 A. Lumptions 39 Limit Statbook Quops, Compression 39.1 Assumptions 39.2 Minimum Eccentricity 39.3 Short axially loaded members in compression 39.4 Compression members with helical reinforcement 39.5 Membrane subjected to combined axial load and UI-axial bendings 39.6 Membrane subjected to combined axial load and biaxial bending 39.7 Slender compression members 40 LLMRR Stats of collapse, shear 40.1 Nominal shear stress 40.2 Desian shear strength of concrete 40.3 Minimum shear reinforcement 40.4 deci of shear reinforcement 4 OS Enhanced shear strength of sections closed to supports 41 LIMRR State OP collapse Torsion 41.1 General 41.2 Critical section 41.3 Shear and torsion 41.4 Reinforcement in members subjected to torsion 42 Limit state of Spervlosive. New York, deflection 42.1 Flexural members 43 Limit state of serviceability cracking 43.1 Flexural members 43.2 Compare ion members Annex a list of referred Indian standards Annex structural design. Working stress method B1 General B1.1 BL.2 BL.3 General Design Requirements Redistribution of moments Assumptions for design of members B2 Permissible stresses 8 to 2.1 Permissible stresses in concrete 8 to 2.2 Permissible stresses in steel Reinforcement B2.3 Increase in permissible stresses B3 Permissible loads in compaction members B3.1 Pedestals and support columns with lateral ties 8 to 3.2 Shan columns with helical reinforcement B3.3 Lawn columns 8 to 3.4 Composite columns /R211 E815/07-3 is 456 1000 page 69 69 70 70 71 71 71 71 71 71 72 72 12 72 72 74 74 74 7 75 75 75 75 16 76 76 71 80 80 80 80 80 80 80 80 80 81 81 81 81 81 is 456 B4 members subjected to combined axial load and binding 8 to 4.1 to IID beat on uncracked section B4.2 to Lilft beat on cracked section B4.3 members subjected to combined direct load and flexure DS shear BS1 nominal shear stress. B5, 2 Neop shear strength of concrete BS.3 minimum shear reinforcement B5.4 Desil of shear reinforcement B. Enhanced shear strength of sections closed to supports B6 torsion B6.1 general B6.2 critical section B6.3 shear and torsion B6.4 reinforcement in members subjected to torsion Annex C calculation of deflection ELC2C3 totaled 8 pliak non-shoil TBIM deflection C10 and due to shrinkage C4 defless I10 and due to creep Annex D slabs spanning in two directions 01 IM tainted slam D2 sim tisapoton S subs Annex B Sperctivi la NOTH of columns Annex F calculano of crack WID1 LI Annex G mom, and TSOP. Slow stang sieb for rectangular and TSEC I10 NSGLRSCRANOULARSBC110 NS 0 to 1.1 sections without comprelan reinforcement 0 to 1.2 sections with compression reinforcement 0 to 2 Flanud SEC 110 N Annex H Committee Composition PAGI 83 83 83 83 83 83 84 8 85 8 86 86 86 86 86 88 88 88 88 89 90 90 90 92 95 96 96 96 96 96 98 10 Amendment No. I Juni.1 is 45 I 2000 plain and to reinforce C on CIT Cody or per C ICE, OWIR, dot bulletin OII, PA 2 FONW ORD, 2. Sublocal to at AA318, 1995 for Tacli I. And we. Pili 1I, C/4 delete T mailer L, World ENTLLDLLTLDCIC.DTIII off later all Lila. Pil 15C/TLLU, sublocal to at CIA lil at _xlug. Lore at.iit. Pal 17, Klgif 7.1, sublocal ib follown, for Tilix lolly dl fomalliable, placl cdndlltud _o/whirlajb only siw 11 iii, 1, 2, 3, bud L concrete, shallow wheat lawn L, abamenta olnspelven very low s.l.l ma. Concrete, uply reinforced ixiod in ij.high, belma, willa, columna, low fluon, hind placed pavements, canal lining, strip footings 25 to 75 heavily reinforced sections in slabs, beams, walla, columna, medium 50 to 100 slip formwork, pumped concrete medium 75-100 trench Fi1L, in situ piling high 100 is 0 treme concrete very high C7.1.1 nom, for motive, placid. Conditions, internal vil low is, edel vibraloral, resuitable. Tile Eli. Fill. Determined bad 08 the density and space idi of reinforcement barsit thd of ishi oil for tulmai. Van. 10 Bust, Su.lto 113. Page 19, Table 4, Columns, UB heading, substitute free for face, page 27, Clause 1 3.5.3, delete. Pika 29, Clause 15.3a, substitute specimens lore samples in lines 2, 6 1 and D7. B, substitute is 9013 lore is 9103. I, page 29, Clause 1.1, substitute conditions for condition in line 3 and TBFOJ low in L, UA for lilt E matter against I, the mean strength determined from any group of Kurananov-Kriapim coffee telcutib lal III diapie _ appropriate limits in column 2 of table 11. PTL 29, Clause 1.3, PAR2, substitute COL 3 tons lore COL2. Page 29, CLAL UE 1.4, LINE2, substitute C16.1 or 16.2 as the case may be lore 1.3. PTL 30, Table 2, Column 3, substitute IC, 3 lore IE3, INDA _ I24T or dot. OJ PRLC GRE up 3 1 amend number 1 to is 456, 2000, page 33, clause 21.3 line 2, Hill Untitled F section. Page 37, clause 23:26 still ut B o low lore 10. B lore B and B, lore B, in the formulae. Still Fn \3 4, page 46 clause Z 6.4. 8.2.3. IL page 49, clause 26.5.3.1, C, 2, loss I line, substitute 6 mm for 16 mm. Page 62, clause 3% Z.5, substitute H, for Hui in the explanation of E _, page 62, clause 3%.3.1, line4, substitute 32.4 lore 32.3. Page 62, clause 3%.4.3, B, line6, insert few between the words but and shall. Page 65, clause 34%.4.1, 1, last line, insert FOJ lowing after the words depth of footing, in case of footings on soils, and at a distance equal to half the effective depth of footing. Page 68, Table 18 COL4, substitute _ for 1.0 against TB load combination DL and LL, page 72, clause 40.1, substitute BD for BD in the formula. PAGE83, clause B4.J, LINE2, delete the word and. Page 85, Clause B.5.5.1 Para 2, Line 6, substitute Table 24 for Table 23. Page 85, Clause B 5.5%. Substitute the following for TB existing formula, L, A equals Q, T.Y2 dt.EIQY, 0.4 QYB / 0.87 / page 90, clause 1.11, line 1, substitute where Lord torsion. Page 93, Fig 27, substitute EFL for IL. Page 95 Annex FA, the reference to Fig 28 given in column 1 of TB text along with the explanation OTB symbols used in the Fig 28 given thereafter may be read just before TB formula given for the rectangular tension zone. B. Substitute compression for compression in TB explanation of symbol A. Pages 98 to 100 Annex H, substitute the following for the existing Annex, Annex H, for MORD, Compa T. Comey, Oscition Cement and Concrete Sectional Committee, CEO2CLUG. ADRTL. Cvid Vesvaria CH Ndrib, 15 Cross, 63 to 64 East Park Road, Malisworld E, Banploor S60003 Majd B.FEPRUQI/in, DA SCOOCL India Ltd, New Delhi Shriv. BAIASL/Burmanland Stili RPSLNOH, Al-Elid, Directorate General of Supplies and Disposals. New Delhi Shrig. Arbayatkar.Shrja. Kchada SHJUJ Arsil, Al-Erlul, CMSPENOINEBR, DFSLGN, SUPI, Iundino FNOINBA, S&S, ALTE Lujail, BG Shirk Construction Tikraloli Lidpun Hindusran Precab Limited, New Delhi Central Public Works Department, New Delhi Kais Inoan Ibr, Navom Dam, Supalun Elendino Inanir, OCC, Alter E, S. Radar Sarab Lower Narmadan Ibn Lad, O. and Hillier Chief Engineer, R, SFAICH Cum.D. Liskroa Research Officer, CONCRL. T. Shanuksa, A/term/E, Iriptialian Power Rial Shia Institute. Omri, 2 CNI, Diet 3, Amend Number 1 to is 456, 2000, Call Imul Frompa E2, Memban representing Shil JP Desai Suribk. Jajina, A/year MLE, Gujarat Ambuja Cements Lid, Ahmedabad Dleklo Joint Nukur Mujade, AP Engineering Research Lahore Laris, Hyderabad DIRF.C1 Oil, ODOD, N&W, Senelral Water Commission, New Delhi JV Durlshire, CMDD, NWNS, A/Talajal, Shrik. H.Oangwal STWV.Pa1 Tab High, Alamkal, Shriv. IE.GHANBKAIL Hyderabad Industries LZD, Hyderabad.RSA Nemrslow Engineering IT R, H Center, CSIR, GHA7JABAD Shris. Go PINA 11 I Shri R.Tam 1 Lajkajlan, Alanult, the India Semen LSLJ Chana Shias. K Gutta Thakurta Shias. Sankaranarayanan, Alternate, Ganan Dunkerley and Company. Lad, Mumbai Sulai NS Buell Dr Irshad Masood, Al Chalikal, Central Building Research Institute, CSIR, Roorkee Prop AK Jain University of Roorkee, Roorkee SHRJNC Jain Joint Lairbter, Standards, BNS, CN1, Joint Dial Plier, Standards, BNS, CB2, Altanult, Cement Corporation of India Ltd New Delhi Research, Designs and Standards Organization, Ministry of Railways. Lucknow Shu Ng. Joseph Shrib. D. Kukar, Alaymi, the Indian Hume Pipe Company Lad, Mumbai Shri D. At Kananushub. R. Mbana, Alteral 4 LE, National Test Jailhouse, Kalkola SHRJPK Jasilnamuanli Stili S. Chawoirai, Al Tulult, Larson and Turo 1.JD, Mumhydrag.madhavaRaosiwk.man. Al Tunnelul, Structural Engineering Research Center, CSIR, Chennai Shioj. Set up Hospital Services Consultancy Corporation, Ayodhya, Lid, New Delhi Shri VSL1 RMH Stili D.P. Sino, Alt Mujail, Housing and Urban Development Corporation LJD, New Delhi Shri Prafwi. A Kumar Shri PP. Nair, A11L7 Ulk, Ministry of Surface Transport Department of Surface Transport, Roadswin and, New Delhi Mbrishkritari Loktok, CML, Alter Lemeli, Central Board of Irrigation and Power, New Delhi Shris. Kananhani Dras. Gobi. Alteral 4. Engineering Clefs Branch. Army Headquarters, New Delhi SHRJS.S. Samira Shri Sathander Kumar, Altoyoli, Central Road Research Institute, EJIR, New Delhi Shri. RPHLUSTLRLAK Sharma, Alt G. Road, Indian Roads Congress. New Delhi DRC Ikumar DRK Mohan, Al Temple C, National Council Forcement and Building Materials, BAL Jabpirb Shri S. Airbui Gaman India Lid. Mumbai Repair Maklay 11W Builders Association of India, Mumbai Shiaj. Sano Ania Uwashil N. ARWAL, Alam GLE, SL1 Lbrin 1 BMING Inoani JIL, DFSION, XID/IM, Inoan. A. SMR Division, A/Temal, Geological Survey of India. Calcutta or Punic Works Department. Ubemadi I Tamil Nadu, Spenashu IE. K Tapai Washil AIE. Jain, AI, TE, Shri TH Dewari or D Gla H, Ali, E, Indian Rayon and Industries I.JD, Pyo the Associated Cement Companies L.JD. Mumbai DRK Venkatatalan Shri N. Shandalasia Kalan, AI, IC, Central Soil.ND Materials Research Station Oft, New Delhi 3, Continual 011 Pose. And ND number 1 and 0 is 4_I 2000, Kwaiyilm JJAI. EV Ajaya SHIID.C.CM1 /JMDI, A, STW Unit Kuma 011, 1010, Ely Bag, BNAIF, I/ILM Ludlal or, LD Kalyol Dertzio, 0.1, 181s, IM 1 TJ, M. TI Tau IIE. Pi.AMD edition. Dlertoy or, L Black. I Thuriami IPant Dep PTRNL or, OV__811 Concrete I Upmeln CEO2:3 Bow. It. National Council Tour CLM.DLLND Buldin. M. Iralal, Shri CROMCHANDANI Shri. Rainawan, AII.RLLLL. DAP. COILDHURYOAC.S. Vishwana 11 IA, AT. III. SHRLLP Dubai SHKB. Jayabsha, ALDE.com. DIRSC10R Shri N Omablokayan, A Arud, DUUICIOA, Kandu, Deputy DIUC10I, Kand, AI.com. Joint Diab 10R Standaildi CB.LS, CB1I it. Joint Diab 1015 Tandads, Bass, ICBR, A Super Inti, and Dino Enamel CDJ, Science, X, Col 1 VL Engineer, Beans, 111, Ale. Shriv. Kaya Hainker Shri D.S. Prakash Rao, AI. E, Shai S.ie. Ouha Elawajita Shris. P. Sanakayanarayanan, Alar MTE, STDUJ.S. Shri L. at Jain Shri MP. Jabana DRB Campsalarao, Alar.e, Chuinoanura Joint Secretariat SUPIJLIN1 Didnoinoan Br. AI, Pyop S.Ka.1 IMAMOOL11LY Shuke Navail, Alc.Te, Das.C. Marn Manaoing Diuktoy S. M. Kundu, AI.com. A. Stili SKNAN1 TANILTCOLIE. S. Jokshrib. VB.PAL S. MG Danva N, AI. SNRIAB.PHATA S. D.M.S. AI. A Shri YR.PU. S. SSS.1 IIAI, Shiizay Tandai Ukume, al.comma.tcll, IHLP Konalintal Lid, Mumbai Tours Teal Arolel Rich Poundalo in India, Calcutta Ojl Nel Ambuja Semen Lad, Ahmedabad AE. Chelil Soliad Meltiria. Usib 5 Lato. New Dale CNL Ulter Kamayoyan. New Delby Re _Reb. Delhi JIIIUD Slidel Oalnazatio D, ML Distri of Railway. El Jakbo Central Public Worb Department. New Delhi Structural Engineering Research CEDRA, CSIR. A Hazelbad Gannon Dunkerley and Kolad. MW Bay Associated Consultina Services. Mumbai and Penity I Capacity Senelrol Buildin Arklirch Instalul, CSIR, Rurbi Public Works, Erement, Mumbai Lodi. I Albtui of Tchalalal Y. Now Delhi Nado Dal Kudal Force I.D Bildi D, Materiala. Bala Pirlo Mild Tad Prefab Uldil CL. New Delhi Neoasia Eek, A Compilatal JD. Mum N Hi DD Ultil Quaiyink Dal COLJD. M, ICEA, 1 Road Re Ierch Idla Ethui, CSIR. New Delhi 4, C _.5, C comma, slash, I. SMIIAIPWAD Rao Shuke Mani, AI. IHI. JC. LP Mashil.R. OA, IL, A comma dot. 1, 8. D. Lahakal Stili U. S.P. Vilma slash, SHII Rao Stili G. Rama Isai. HMAN Cal comma dot. Shil. A.RIDD N.JC. Naval, AI. Shri. C. Sahni SHIR. P. Miatia Cal comma dot. Pow M.S. Shim Shi Nk Sinha Shiib. T. Unwaya AI comma dot comma, 01 Anil Kumar Surov. K. Otlan Blakar Pa. A. At Jane Shilk. Jane Stlijoi. Kurian das.c. Mam drakmntal Shri sarsodi drv no dam amend number 1 to is45, 2000 iv. Comma. Structural NALN Renel Remarch C.nin, CSIR, Chona Foot N. Clonal Buldi Kanel Truklon Korponlian Lad. New Delhi Nuclear Power Corporation, Amulbay APNI1 Rearch Laban Larika, Hyderabad Gamal India Lid. Mumbai Anano India IJD. New Delhi Idian Con Sirol Inlhul Kanal Minlari or Surface Trapalpearl, Road. Wina, New Delhi in Panonal Capacity Panel for Revision or is456, CEO2:2 IP Rep NLCNL, LT, National Council for Cement and Building. Material, AAU Upper National Council for Commonel and Dulduln, Mail Reals, BAU Abarb Structural Engineering Redi. Center, CSIR, a Hazelbad University of Roorkee, Roork, in Perlonal Capacity Center 1 Public Work Department, New Dale Nalinal Council for Semiknal Duildin. Material, BLU Ablar Central Public Work Department, New Dale Gammon India LCD, Mumbai School of Planning and Architecture, New Delhi Special Ad Hoc Group for Revision of is456, Convener Drive HCVIS.5 Vedava Chandrika, 215D1 Cross. 63 to 64 Basi Park Road, Malleswaram. Banalari S60003 DRC Ikumar SIUS. ARE Dole National Council Roar Cement and Suildana Materials, Balabir Gammon India LJD, Mernbay, CED 2, 52. Amendment No. 2 SERIMBER 2 or 2. TW/U is 456, 2000 PLAIN and Reinfo D Concrete, Code of Practice, FIJ Earth Revision, page 13, clause 5.2.1.1, line 1, substitute is 3812, Part 1, for grade Rens 3812. Page 13, Clause 5.2.1.2 and corresponding note, substitute the following for the existing. Silica fume conforming to is 15388 may be used as part replacement of cement provided uniform blending with the cement is ensured. Note, silica fume is usually used in proportion of to 10% of the cement content of a mix T. Page 13. Note under clause 5.2.1.3, line 5, substitute before range from being. Page 25 clause 10.3.3, line 4, delete the word and. Page 65 clause 34.2.4.2 line 1, substitute on for or. Page 65 clause 34.3.1, a, line 2I, delete the words extending in each direction. Page 66, clause April 3, 34 line 5, substitute not for no. Page 78 1 next a, substitute the following for the existing entries for 153,812, 1981, /S1 /0. Title is 3812, Part 1, 2003 Specification for Pulverized Fuel Ash, Part I for USC as pozzolana in cement, cement mortar, and concrete, Second Revision, page 79. Annex A, _ add the following at the end, 41, 1 no. Title is 15388, 2001 Specification for Silica Fume 2116 815/07-1, p. 80, 1-2.1.1, ILF/OIFIM bleu, inlert the FOU from the table, 5.6, PAG, 81, TTJBL, 21, insert the following row after the row, 1, 2, 3, 4, MS 17.513,0I. PAG, 91, TTJBL, 26, EMF number 2, COL2, Sublatitude OM short ed delaltal nuolor anilhoit ed. Conti, PGI 96, G1.L, C, ./olulul/G sublatitude MG8/O, my PAGL 96, GL.1, D, dot, sublatitude 31.1I/039.1I. CED2, 218-456, 2000 Indian Standard Plain and Reinforced Concrete Code of Practice, 4th Revision, forward this Indian Standard, 4th Revision, ways adopted by the Bureau of Indian Standards, after the draft finalized. By the Cement Concrete Sectional Committee had been approved by the Civil Engineering Division Council. This standard was first published in 1953 under the title Code of Practice for Plain and Reinforced Concrete for General Building Construction and subsequently revised in 1957. The code was further revised in 1964 and published under modified title Code of Practice for Plain and Reinforced Concrete, thus enlarging the scope of use of this code to structures other than general building construction also. The third revision was published in 1978, and it included limit state approach to design. This is the fourth revision of the standard. This revision was taken up with a view to keeping abreast with rapid development in the field of concrete technology and to bring in further modifications/improvements in the light of experience gained while using the earlier version of the standard. This revision incorporates a number of important changes. The major thrust in the revision is on the following lines. A. In recent years, durability of concrete structures have become the cause of concern to all concrete technologists. This has led to the need to codify the durability requirements world over. In this revision of the code, in order to introduce inbuilt protection from factors affecting a structure, earlier clause on durability has been elaborated and a detailed clause covering different aspects of design of durable structure has been incorporated. B. Sampling and acceptance criteria for concrete have been revised. With this revision, acceptance criteria has been simplified in line with the provisions given in BS 5328, P8L14 1990 Concrete, Part 4 Specification for the procedures to be used in sampling, testing, and assessing compliance of concrete. Some of the significant changes incorporated in Section 2 are as follows. A. All the 3 grades of ordinary Portland cement, namely 33 grade, 43 grade and 53 grade and sulfate-resisting Portland cement have been included in the list of types of cement used, in addition to other types of cement. B. The permissible limits for solids in water have been modified keeping in view the durability requirements. C. The clause on admixtures has been modified in view of the availability of new types of admixtures including superplasticizers. D. In TABLE2 grades of concrete, grades higher than M40 have been included. E. It has been recommended that minimum grade of concrete shall be not less than M20 in reinforced concrete work, see also 6.1.3. F. The formula for estimation of modulus of elasticity of concrete has been revised. G. In the absence of proper correlation between compacting factor, VB time, and slump, workability has now been specified only in terms of slump in line with provisions in BS 5328, parts 1 to 4. H. Durability clause has been enlarged to include detailed guidance concerning the factors affecting durability. The table on environmental exposure conditions has been modified to include very severe and extreme exposure conditions. This clause also covers requirements for shape and size of member, depth of concrete cover, concrete quality, requirement against exposure to aggressive chemical and sulfate attack, minimum cement requirement and maximum water cement ratio limits of chloride content, alkali silica reaction, and importance of compaction, finishing and curing. J. ACOS on quality assurance measures has been incorporated to give due emphasis to good practices of concreting. K. Proper limit shape been introduced on the accuracy of measuring equipments to ensure accurate batching of concrete. 2116 bis/07:. is456, 2000 m. The clause on construction joints has been modified. N. The clause on inspection has been modified to give more emphasis on quality assurance. The significant changes incorporated in Section 3 are as follows. A. Requirements for fire resistance have been further detailed. H. The figure for estimation of modification factor for tension reinforcement used in calculation of basic values of span to effective depth to control the deflection of flexural member has been modified. C. Recommendations regarding effective length of cantilever have been added. D. Recommendations regarding deflection due to lateral loads have been added. E. Recommendations for adjustments of support moments in restrained slabs have been included. F. In T.E determination of effective length of compression members. Stability index has been introduced to determine sway or no sway conditions. G. Recommendations have been made for lap length of hook S4 bars in direct tension and flexural tension. H. Recommendations regarding strength of welds have been modified. J. Recommendations regarding cover to reinforcement have been modified. Cover has been specified based on durability requirements for different exposure conditions. The term nominal covered has been introduced. The cover has now been specified based on durability requirement as well as for fire requirements. The significant change incorporated in Section 4 is the modification of the clotion walls. The modified clause includes design of walls against horizontal shear. In Section 5 on limit state method, a new clause has been added for calculation of enhanced shear strength of sections close to supports. Some modifications have also been made in the clause on torsion. Formula for calculation of crack width has been added, separately given in Annex F. /Weinricking stress method has now been given in Annex B so as to give greater emphasis to limit state design. In this annex, modifications regarding torsion and enhanced shear strength on the same lines as in Section 5 have been made, whilst the common methods of design and construction have been covered in this code. Special systems of design and construction of any plain or reinforced concrete structure not covered by this code may be permitted on production of satisfactory evidence regarding their adequacy and safety by analysis or test or both. C19. In this code it has been assumed that the design of plain and reinforced cement concrete work is entrusted to a qualified engineer and that the execution of cement concrete work is carried out under direction of a qualified and experienced supervisor. In the formulation of this standard, assistance has been derived from the following publications: BS 5328, Part 1, 1991 Concrete, Part 1 Guide to Specifying Concrete, British Standards Institution BS 5328, Part 2, 1991 Concrete, Part 2 Methods for Specifying Concrete Mixes, British Standards Institution BS 5328, Part 3, 1990 Concrete, Part 3 Specification for TB Procedures to be used in producing and transporting concrete. British Standards Institution BS 532R, Part 4, 1990 Concrete, Part 4 Specification for the procedures to be used in sampling, testing, and assessing compliancy of concrete, British Standards Institution BS 8110, Part 1, 1985 Structural Use of Concrete, Part T Code of Practice for Design and Construction, British Standards Institution BS Rito, Part 2, 1985 Structural Use of Concrete, Part 2 Code of Practice for Special Circumstances, British Standards Institution Act 319 1989 Building Code. Requirements for Reinforced Concrete, American Concrete Institute S 3600, 1988 Concrete Structures. Standards Association of Australia 2. is456, 2000 in 1045 JULY 1988 Structural Use of Concrete, Design and Construction. Deutschlandsrichtut für Normen EBC FIP Model Code 1990, Comite Euro. International Dubclan. The composition of the technical committee responsible for the formulation of the standard is given in Annex H. For the purpose of deciding whether a particular requirement of the standard is complied with, the final value, observed or calculated, expressing the result of a test or analysis shall be rounded off in accordance with IS2, 1960 Rules for Rounding Off Numerical Values, revised. The number of significant places retained in the rounded off value should be the same as that of the specified value in the standard. 3 is 456, 2000 Section 1 General 1 Scope 1.1 This standard deals with the general structuralis of plain and reinforced concrete. 1.1.1 For the purpose of this standard, plain concrete structures are those where reinforcement, if provided, is ignored for determination of strength of the structure. 1.2 Special requirements of structures, such as shells, folded plates, arches. Bridges, chimneys, blast-resistant structures, hydraulic structures, liquid retaining structures and earthquake-resistant structures covered in respective standards have not been covered in this standard. These standards shall be used in conjunction with this standard. 2 References. The Indian standards listed in Annex A contain provisions which, through reference in this text, constitute provisions of THIL standard. At the time of publication, the edition indicated were valid. All standards are subject to revision and parties to agreements based on this standard are encouraged to investigate the possibility of applying the most recent editions of the standards indicated in Annex A. 3 Terminology. For the purpose of this standard, the definitions given in IS 4845 and IS 6461, Parts 1 to 12, shall generally apply. 4 Symbols. For the purpose of this standard, the following letter symbols shall have a thymkanina indicated against each, where other symbols are used. They are explained at the appropriate place: A. Area. B. Breadth of beam, or shorter dimension of a rectangular column. Bet. Effective width of slab. B. Effective width of flank. B. Breadth of web or rib. D. Overall depth of beam or slab or diameter of column, dimension of a rectangular column in the direction under consideration. Drive, thickness of flange. DL, dead load. D, effective depth of beam or slab. D, depth of compression reinforcement from the highly compressed face. EC. Modulus of elasticity of concrete. L, earthquake load. E. Modulus of elasticity of steel. E, eccentricity, let. Characteristic cube compressive stress. N. Th of concrete. T, modulus of rupture of concrete, flexural tensile oath, ft1 splitting, tensile luf of concrete t, dissipitron thi, characteriatic itron jth of steel, h unsupported iht of wall hui, effective ht of wall ie, effective moment of inertia f, 1 moment of inertia of the gross section excluding reinforcement I, moment of inertia of crack section k, stiffness of member k, constant or coefficient or factor, LD. Development length, U live load or imposed load LW, horizontal distance C between centers of lateral restraint, length of a column or beam between adequate lateral restraints or the unsupported length of a column, LR effective span of beam or slab or effective length of column, LE effective length about XX axis i.e., effective length about YY axis, I clear span, face to face of supports IN, for shorter of the two spans at right and LGLES, I length of shorter light of slab LE. LIN.th of loftier 8 of slab, 10, distance between points of 0 Nomen. In a beam, I span in the direction in which moments are determined, center to center of supports, 12 span transverse E to I center to center of supports I2 to 12 for the shorter of the continuous spans M, bending. Moment, M modular ratio N, number of samples, P axial load on a compression member Q calculated maximum bearing pressure 11 is 456, 2000 Qn, calculated maximum bearing pressure of soil R, radius S, spacing of stirrups or standard deviation T, torsional moment, wall thickness V, shear force W, total load WL wind load W, distributed load per unit area WD, distributed dead load per unit area WI, distributed imposed load per unit area X, depth of neutral axis Z modulus of section L. Lever R May 8, annile or ratio year, partial safety factor for load E8 MEEC, G and high, and, E, oft K, GM, J, AV, THD, T and, TEME and XTV, partial safety factor for material percentage reduction in moment creep strain of concrete permissible stress in concrete in bending compression permissible stress in concrete indirect compression permissible stress in metal indirect compression permissible stress in steel in compression permissible stress in steel in tension. Permissible tensile stress in shear reinforcement design bond stress shear stress in concrete maximum shear stress in concrete with shear reinforcement nominal shear stress diameter of bar. J. Section 2 Materials, Workmanship, Inspection, and Testing is 456, 2005 Materials S.T Cement. The cement used shall he any of the following and the type selected should be appropriate for the intended use. A. 33 grade ordinary Portland cement conforming to is 269 B, 43 grade ordinary Portland cement conforming to is 8112 C, S3 grade ordinary Portland cement conforming to is 12269 D, rapid hardening Portland cement conforming to is 8041 E, Portland slag cement conforming to is 4.5 F, Portland pozzolana cement, fly ash based, conforming to is 1489, Part 1, G, Portland pozzolana cement, calcined clay based, conforming to is 1489, Part 2, H, hydrophobic cement conforming to is 8043 J, low heat Portland cement conforming to is 12600 K, sulfate resisting Portland cement conforming to is 12,330. Other combinations of Portland cement with mineral admixtures, C.2 of quality conforming with relevant Indian standards laid down may also be used in the manufacture of concrete provided that there are satisfactory data on their suitability, such as performance test concrete containing them. 5.1.1 Low heat Portland cement conforming to is 12,600 shall be used with adequate precautions with regard to removal of formwork, etc. 5.1. High alumina cement conforming to is 6,452 or supersulfate cement conforming to is 6,909 may be used only under special circumstances with the prior approval of the engineer in charge. Specialist literature be consuite for guidance regarding the use of these types of cements. 5.1.3 The attention of the engineers in charge and users of cement is drawn to the fact that quality of various cements mentioned in 5.1 is to be determined on the basis of its conformity to the performance characteristics given in the respective Indian standard specification for that cement. Any trademark or any trade name indicating any special features not covered in the standard or any qualification or other special performance characteristics sometimes claimit'll indicate in the base or containers or in advertisements alongside the statutory quality marking or otherwise have no relation whatsoever with the characteristics guaranteed by the quality marking as relevant to that cement. Consumers are, therefore, advised to go by the characteristics as given in the corresponding Indian standard specification or seek specialist advice to avoid any problem in concrete making and construction. 5.2 Mineral admixtures. 5.1.1 Pozzolanas Pozzolanic materials conforming to relevant Indian standards may be used with the permission of the engineer in charge, provided uniform blending with cement is ensured. 5.2.1.1 Fly ash, pulverized fuel ash. Fly ash conforming to grade 1 of is 3812 may be used as part replacement of ordinary Portland cement provided uniform blending with cement is ensured. 5.2.1.2 Silica fume. Silica fume conforming to a standard approved by the deciding authority may be used as part replacement of cement provided uniform blending with the cement is ensured. Note the silica fume, very fine non-crystalline silicon dioxide, is a byproduct of Thel1UU1 manufacture of silicon, ferrosilicon, or the like. From quartz and carbon in electric arc furnace. It is usually used in proportion of 10% of the cement content of a mix. 5.1.1.3 Rice husk ash. Rice husk ash giving required performance and uniformity characteristics may be used with the approval of the deciding authority. Note rice husk ash is produced by burning rice husk and contain large proportion of silica. To achieve amorphous state, rice husk ash be burnt at controlled temperature. It is necessary to evaluate the product from a particular source for performance and uniformity since it can run from BNL as deleterious as silt when incorporated in concrete. Water demand and dry NL shrinkage should be studied before using rice husk. 5.2.1.4 Metacaolin. Metacaolin having fineness between 700 to 900 m2/kg may be used as pozzolanic material in concrete. Note metacaolin is obtained by calcination of pure or refined coaltic clay or temperature between 6500 C and 80 degrees C, followed by rindin. To achieve a fineness of 700 to 900 mLK. The result IDI material hoihil pozzolanicity. S.2.2 Ground granulated blast furnace slag. Ground granulated blast furnace slag obtained by grinding granulated blast furnace slag conforming to is12089 may be used as part replacement of ordinary 13 is456, 2000 Portland cements provided uniform blending with cement is ensured. 5.3 All RA.8's aggregates shall comply with the requirements of is383. As far as possible, preference shall be given to natural aggregates. 5.3.1 Other types of aggregates such as sial and crushed overbump brick or tile, which may be found suitable with regard to strength, durability of concrete and freedom from harmful effects may be used for plain concrete members. But such aggregates should not contain more than 0.5% of sulfates and should not absorb more than 10% of their own mass of water. 5.3.2 Heavyweight aggregates of lightweight aggregates such as bloated clay aggregates and sintered fly ash aggregates may also be used provided the engineer in charge is satisfied with the data on the properties of concrete made with them. Note some of the proviso di of the code would require modification when these AL plates are used. Speculailed literated je may be consult for ordinance. 5.3.3 says F aggregate. The nominal maximum size of coarse aggregate should be as large as possible within the limits specified but in no case greater than 1/4 of the minimum thickness of the member, provided that the concrete can be placed without difficulty so as to surround all reinforcement thoroughly and fill the comers of the form. For most work, 20 non-alariat is suitable. where there is no restriction to the flow of concrete into sections, 40 none, or layer size may be permitted. In concrete elements with thin sections, closely spaced reinforcement, or small cover, consideration should be livened to the use of 10 mm nominal maximum lis. Plums above 160 none and up to any runabilize may be used in plain concrete work up to a maximum limit of 20% by volume of concrete when specifically permitted by the Ananiran Karau. The plums shall be distributed evenly and hall be not closer than 10 mm from the surface. 5.3.3.1 For have.ij reinforced concrete membanu in the else of ribs of main beams, the nominal maximum is of the ALF late eald usually be retriatetoum lay. Than the minimum clear ili.tani between the main bars or SMM lel than the minimum cover to the reinforcement whichever I amaler. 5.3.4 Coarse and fine allies relate hall be batched separately. All. In aller lte may be used only where specifically permitted be though in linear and chari 1.4 water. Water used for mixin, and kun hall be clean and free from injurious amounts of oils. Acids, alkalis, salta, sugar, organic materials, or other substances that may be deleterious to concrete or steel. Potable water is generally considered satisfactory for mixing a concrete. As a guide, the following concentrations represent the maximum permissible values. A. To neutralize 100 ml sample of water, use 0.1 phenolphthalein as an indicator. It should not require more than ml of 0.02 nominal NaOH. The details of test are given in 8.1 of is 3025, Part 22. B. To neutralize 100 ml sample of water, Ewing's mixed indicator, it should not require more than 2 ml of 0.02 nominal H2 so. The details of test shall be as given in 8 of is 3025, Part 23. C. Permissible limits for solids shall be as liven in Table 1. 5.4.1 In case of doubt regarding development of strength. The suitability of water for making concrete shall be ascertained by the compressive strength and initial setting time tests specified in 5.4.1.1 and 5.4.1.3. 5.4.1.1 The sample of water taken for Teslin, hall represent water proposed to be used for concreting, due account being paid to seasonal variation. The sample shall not receive any treatment before te_un, other than that envisaged in their regular supply of water proposed for using concrete. The sample shall be belted in a clean container previo lly rinsed out with limilar water. 5.4.1.2 Avrilo 28 days compressive ITTN.th of at least 3 LO non-concrete cubes prepared with water proposed to be used shall not be less than 90% of the average of strength of 3 similar concrete cubes prepared with distilled water, th cube hall be prepared. Cured and tested in accordance with the requirements of is456. 5.4.1.3 The initial Trinel time of te.t block made with the appropriate cement and the water proposed to be used. Hall not be le than 30 minutes and hall not dlff. By plus or minus 30 min from the initial. Etlin a time of control telt block prepared with the lame cement and dilty jailed water. The telt block Hanbe prepared and tilted in accordance with the requirementa of is4031, p.n5. 5.4.1 The pH value of water hall be not less than 6. 5.4.3 See water mixin L or curin, of concrete with .ea whaler il not recommended because of pF1s of harmful. LLTL in, water. Under unavoidable circummeltanil 1m water may be used for mixin. Or curial in plain concrete with no emitted steel after hij liven ducan duration topislable. Disadvantapa and precaution. Including UII of appropriate cement system. 1451 nil, N organic 2, inorganic 3, sulfates, as so, 4, chlorides, as Sylvie, suspended mailer table 1 permissible limit for solids T taught is 5.4, is red as per is 02, part is 025, put ill, is 02I, part 24, is 0.1025, part 2, is 3025, part 17, is 456, 2000 LCR reliable limit, MLLX 2001 LL. 111M10 mg, 1400 mg/L2IM, IIIG, 1 for concrete 1101 containing embedded steel and Jo1 IIG/IJR reinforced concrete work 20001 LIG 115.4.4 water found satisfactory for mixing is also suitable for curing concrete. However, water used for curing should not produce any objectionable stain or unsightly deposit /10 the concrete surface. The presence of tannic add or iron compounds is objectionable. 5.5 Admixtures 5.5.1 Admixture. If used shall comply with IS 9103. Previous experience with and data, 3 such materials should be considered in relation to the likely standards of supervision and workmanship to the work being specified. 5.5.2 Admixtures should not impair durability, if concrete nor combine with the constituent to form harmful compounds nor increase the risk of corrosion of reinforcement. 5.5.3 The workability, compressive strength, and the slump loss of concrete with and without the USC of admixtures shall be established during the trial mixes. Before LISA of admixtures. 5.5.4 The relative density of liquid admixtures shall be checked for Coddy drum containing admixtures and compared with till specified value before acceptance. 5.5.5 The chloride content of admixtures shall be independently tested fil EACH HUCL, before acceptance. 5.5.6 If 2 or more admixtures are used simultaneously in the same concrete mix, JALA should be obtained to assess their interaction and to ensure their compatibility. 5.6 Reinforcement till reinforcement shall be any of the following: a. Mild steel and medium tensile steel bars conforming to IS 432, Part I. H. High strength deformed steel bars conforming to IS 1786. C. Hard drawn steel wire fabric conforming to IS 1566. D. Structural steel conforming to grade A of IS 2062. 5.6.1 All reinforcement shall be free from loose mill scales, loose rust and coats of paints, oil, mud or any other substances which may destroy or reduce hondo sand blasting or other treatment is recommended to DIN reinforcement. 5.6.2 Special precautions like coating, if reinforcement may be required for reinforced concrete as in exceptional cases and for rehabilitation of structures. Specialist literature may be referred to in such cases. 5.6.3 The modulus of elasticity of steel shall be taken as 200 kN/L1 LLJ1. The characteristic yield strength of different steel shall be assumed as the minimum yield stress /0.2% proof stress specified in the relevant Indian standard. 13.7 Storage of materials shall be as described in is456. 6 Concrete 6.1 Grades The concrete shall be in grades designated as per TANELC 2 6.1.1 The characteristic strength is defined as the strength of material below which not more than 5% of the test results are expected to fall. 6.1.2 Tile minimum grade of concrete for plain and reinforced concrete shall be as per Table 5. 6.1.3 Concrete of grades lower than those given in Table May 5 be used for plain concrete constructions. Lean concrete, simple foundations, foundation for masonry walls and other simple or temporary reinforced concrete construction. 6.2 Properties of concrete 6.2.1 Theoretically, /I, of strength with agi there is normally a gain of strength beyond Tuesdays. The quantum of increase depends upon the radk and type of cement, curing and voructural conditions, etc. The design should 1. H1SXL on 2X dev, characteristic strength F(r). LLX there is a evidence 315 is 456, 1000 group, I, DABLE2G and DES of Cond, Clause 6.1.9.2.2.15.1.1 and 36.1, Grade DEI, IIOIL SPTED CBA1 IEEO, S till ISO AMI cube at 210, dot. NLMM 2, 2, 3, where EC is the short 10 static modulus of elasticity in N/mm2. Actual measured values may differ by plus or minus 20% from the values obtained from the above expression. Ordinary M1010 concrete M is M2020 Slalda Road M2S2s concrete M30 30 minutes and 3 seconds 3s M40 40 minutes and 4 seconds 45 MSO so MSSSS high HM60 60 strength M6S 65 concrete M70 70 minutes and 7 seconds 75 M80 80 notes I in the dissipation of concrete mix M refers to the mix the number to the specified Compnello-Vitrenith of 150 mm size cubical 28 days. Expressed in N/mmj. 1 for concrete of Comsif Strenath Ariderthan M55. The SIP parameters given in Thawing road may not be applicable and the values may be obtained from specialized literatures and experimental results. 6.2.4 Schrinell gauge the total shrinkage of concrete dep/rds upon the constituents of concrete, size of the member and environmental conditions. For a given humidity and temperature, the total shrinkage of concrete is most influenced by the total amount of water present in the concrete at the time of mixing and, to a lesser extent, by the cement content. 6.2.4.1 In the absence of test data, the approximate value of the total shrinkage strain for Deslan may be -0.0003. For more information, see IS 1343. 6.2. Creep of concrete Creep of concrete depends, in addition to the factors listed in 6.2.4, on the stress in the concrete, age at loading and the duration of leading. As long as the stress in concrete does not exceed 1/3 of its characteristic compressive strength, creep may be assumed to be proportional to the stress. Justify a higher strength for a particular structure due to age. 6.2.1.1 For concrete of grade M30 and above, the rate of increase of compressive strength this shall be based on actual investigations. 6.2.1.2 Where members are subjected to lower direct load during construction, they should be checked for stresses resulting from combination of direct load and bending during construction. 6.2.2 Tensile strength of concrete. The flexural and splitting tensile strengths shall be obtained as described in IS 516 and IS 5816 respectively. When the designer wishes to use an estimate of the tensile strength from the compressive strength, the following formula may be used. 6.1.5.1 In the absence of experimental data and detailed information on the effect of the variables, the ultimate creep strain may be estimated from the following values of creep coefficient, that is. Ultimate creep strain, elastic strain at the age of loading. For long span structure, it is advisable to determine actual creep strain, likely to take place, at loading 7 days 28 days a year. Creep coefficient 2.21.61.1 Note the ultil 1 LLECREAP1 UIIN. Etimildus described above does not include the elastic IDLN. 6.2.6 Thermal expansion flexural strength, for equals 0.7 L, N/mm2 where F, is the characteristic cube compressive strength of concretine N/mm2. 6.2.3 Elastic deformation. The coefficient of thermal expansion depends on L2E of cement, the aggregate, the cement content, the relative humidity and the size of sections. The value of coefficient of thermal expansion for concrete with different aggregates may be taken as below. The modulus of elasticity is primarily influenced by type of aggregate, coefficient of thermal, the elastic properties of the aggregate, and to a lesser expansion for concrete/C extent by the conditions of curing avantage of the concrete, the mix proportions and the type of cement. The modulus of elasticity is normally related to the compressive strength of concrete. 6.2.3.1 The modulus of elasticity of concrete can be assumed as follows: quartzite, sandstone, granite, basalt, limestone 1.2 to 1.3 x 10 5 0.9 to 1.2 x 10 0.7 to 0.95 x 10 0.8 to 0.95 x 10 0.6 LQ. 0.9 x 10 5.1. 16 is 456. 2007 Workability of concrete 7.1 The concrete mix proportions chosen should be such that the concrete is of adequate workability for the placing conditions of the concrete and can properly be compacted with the means available. Suggested ranges of workability of concrete measured in accordance with is456 are given below. Placing conditions degree OJ Workability slump, I, 2, 3, blinding concrete, shallow sections, pavements using pavers mass concrete, lightly reinforced sections in slabs, beams, walls columns, floors, hand-placed pavements, canal lining, strip footings heavily reinforced sections in slabs, beams, walls, columns, slip formwork, pumped concrete trench fill, in situ piling. Trirna concrete very low medium Li very high C7.J.L 25 to 75 50 to 100 75 to 100 100 to 150 C7.1.2 Note for most of the placing conditions, mcranol vibrators, needle virators, are suitable. The diameter of the needle shall be determined based on the density and spacing of reinforcement bars and thickness of sections. For Trimi concrete, vibrators are not required to be used, se also LT. 7.1.1 In the very low category of workability where strict control is necessary, for example pavement quality concrete, measurement of workability high determination of compacting factor will be more appropriate than slump, C is 1199, and a value of compacting factor of 0.75 to 0.80 is suggested. 7.1.2 In the very high category of workability, measurement of workability high determination of flow will be appropriate, C is 9103. 8. Durability of concrete 8.1. General A durable concrete is one that performs satisfactorily in the working environment during its anticipated exposure conditions during service. The material sand mix proportions specified and used should be such as to maintain its integrity and, if applicable, to protect embedded metal from corrosion. 8.1.1 One of the main characteristics influencing the durability of concrete is its permeability to the ingress of water, oxygen, carbon dioxide, chloride, sulfate, and other potentially deleterious substances. Impermeability is governed by the constituent sand workmanship used in making the concrete. With normal weight aggregates a suitably low permeability is achieved by having an adequate cement content sufficiently low free water/cement ratio, by ensuring complete compaction of the concrete, and by adequate curing. The factors influencing durability include, a. the environment, h. the cover to embedded steel, c. the type and quality of constituent materials, d. the cement content and water/cement ratio of the concrete, e. workmanship, to obtain full compaction and efficient curing, and f. the shape and size of the member. The degree of exposure anticipated for the concrete during its service life together with other relevant factors relating to mix composition. Workmanship. Design and detailing should be considered. The concrete mix to provide adequate durability under these conditions should be chosen taking account of the accuracy of current testing regimes for control and compliance as described in the standard 2116 818/07-4. 17 is 456, 2008.2 Requirements for durability 8.2.1 Shape and size of member. The shape or design details of exposed structures should be such as to promote good drainage of water and to avoid standing pools and rundown of water. Care should also be taken to minimize any cracks that may collect or transmit water. Adequate curing is essential to avoid the harmful effects of early loss of moisture, see 13.5. Member profiles and their intersections with other members shall be designed and detailed in a way to ensure easy flow of concrete and proper compaction during concreting. Concrete is more vulnerable to deterioration due to chemical or climatic attack when it is in thin sections, in sections under hydrostatic pressure from one side only, in partially immersed sections and at comer sand edges of elements. The life of the structure can be lengthened by providing extra cover to steel, by chamfering the corners or by using circular cross-sections or by using surface coatings which prevent or reduce the ingress of water, carbon dioxide, or aggressive chemicals. 8.2.2 Exposure Conditions. 8.2.2.1 General Environment. The general environment to which the concrete will be exposed during its working life is classified into 5 levels of severity, that is, mild, moderate, severe, very severe and extreme as described in Table 3. Table 3 Environmental Exposure Conditions, Clauses 8.2.2.1 and March 2, 35, SI No. 1, I, 2, 3, 4, V, Environment, 2, Mild Moderate Severe Very Severe Extreme Exposure Conditions, 3, Concrete surfaces protected against weather or aggressive conditions, except those situated in coastal area. Concrete surfaces sheltered from severe rain or freezing whilst wet. Concrete exposed to condensation. Algmin concrete continuously underwater. Concretine contactor BT, ride under non-aggressive soil/ground /yater. Concrete surfaces sheltered from saturated salt air in coastal area. Concrete surfaces exposed to severe rain, alternate wet and drying or occasional freezing whilst wet or severe condensation. Concretely immersed in sea water. Concrete 1TC exposed to casual environment. Concrete surfaces exposed to sea water spray, corrosive fumes or severe freezing conditions whilst wet. Concrete in contact with or buried under erosive lube around water surface of members in tidal zone. Membrane in direct contact with liquid solid aggressive chemicals. 8.2.2.2 Abrasive specialist literatures may be referred to for durability requirements of concrete surfaces exposed to abrasive action, for example, in case of machinery and metal FES. 8.2.2.3 Freezing and thawing. Where freezing and thawing actions under wet conditions exist, enhanced durability can be obtained by the use of suitable air entraining admixtures. When concrete lower than grade M50 is used under these conditions, the mean total air content by volume of the fresh concrete at the time of delivery into the construction should be nominal maximum size aggregate, mm, 2040 entrained air percentage S plus or minus L4 plus or minus T. Since air entrainment reduces the strength, suitable adjustments may be made in the mix design for achieving required strength. 8.1.1.4 Exposure to sulfate attack. Table 4 gives recommendations for type of cement, maximum free water/cement ratio and minimum cement content, which are required at different sulfate concentrations in near neutral groundwater having pH of 6 to 9. For the very high sulfate concentrations in Class S conditions, some form of lining such as polyethylene or polychloropyrene sheet, or surface coating based on asphalt, chlorinated rubber, epoxy, or polyurethane materials should also be used to prevent excess by the sulfate solution. 8.2.3 Requirement of concrete cover. 8.1.3.1 The protection of the steel in concrete against corrosion depends upon an adequate thickness of good quality concrete. 8.2.3.2 The nominal cover to the reinforcement shall be provided as per 26.4. 8%.4 Concrete mix proportions. 8.1.4.1 General. The free water cement ratio is an important factor in governing the durability of concrete and should always be the lowest value. Appropriate values for minimum cement content and the maximum free water cement ratio are given in Table S for different exposure conditions. The minimum cement content and maximum water cement ratio apply to 20 mm nominal maximum size aggregate. For other sizes of aggregate they should be changed. 81 given in Table 6. 18 is 456, 2008.2.4.2 Maximum cement content not including fly ash and ground granulated blast furnace slag in excess of 450 kg/ml should not be used unless special consideration has been given in design to the increased risk of cracking due to drying shrinkage in thin sections, or to early thermal cracking and to the increased risk of damage due to alkali-silica reactions. Table 4 Requirements for concrete exposed to sulfate attack, Clauses 8.2.2.4 and 9.1.2, SICLA 6 No. Concentration of sulfates, expressed U. SOJ. 1 oil, total sol solin 2:1 water, Soil extract in groundwater type of cement % Gil dense, rooty compacted concrete. Made WLTB 20 mm nominal maximum size ALRA.8. Comply idle width is 383 number, minimum cement content KLLMJ maximum face water cement ratio, I, 2, 3, 4, 5, 6, 7, 8, 1, traces less than ordinary Portland 280 0.5 S 0.2, 1.0 N.3 cement or Portland slag cement or Portland pozzolana cement 2, 0.2 to 1.0 to 0.3 to ordinary Portland 330 0.50 0.5 1.9 1.2 cement or Portland slag cement or Portland pozzolana cement supersulfate 310 0.so cement or sulfate resisting Portland cement 3, 0.5 to 1.91 U 1.110 supersulfate 330 0.50 1.0 3.12.5 cement or sulfate resisting Portland cement Portland pozzolana 350 0.45 cement or Portland slag cement 4, 410 TO 1102.5 to supersulfate 370 04 S 2.0 SO 50 or sulfate resisting Portland cement V, 5 more thin more chan more than sulfate resisting. 4, X, 0.402.05.05.0 Portland cement or supersulfate C, enant with protective coatings. Notes 1 cement content given in this table is irrespective of grades of cement. 2 Use of supersulfate cement is generally restricted where the prevailing temperature is above 40 FC. 3 Supersulfated cement gives an acceptable life provided that the concrete is dense and prepared with a water-cement ratio of 0.4 or less, in mineral acids, down to pH 3. 4 The cement contents given in COL6 of this table are the minimum recommended. 4 So, contents near the upper limit of any class. Cement contents above these minimum are advised. 5 For severe conditions. Such thin sections under hydrostatic pressure on one side only and sections panty immersed. Considerations should be given to a further reduction of water-cement ratio. 6 Portland slag cement conforming to is 45.5 with slag content more than 50% exhibits better sulfate resisting properties. 7 Where Chloride is encountered along with sulfates in soil or groundwater. Ordinary Portland cement with C1A content from 2 to 8% shall be desirable to be used in concrete, instead of sulfate resisting cement. Alternatively, Portland LLLG ermant conforming to is 4 having more than 0% slag of a blend of ordinary Portland cementan slag may be used provided sublucent information is available on performance of. Such blended cements in these conditions. 19 is 456, 2008.2.5 Mix constituents 8.2.5.1 General for concrete to be durable, careful selection of the mix and materials is necessary, so that deleterious constituents do not exceed the limits. 8.2.5.1 Chlorides in concrete. Whenever there is chloride in concrete there is an increased risk of corrosion of embedded metal. The high earth chloride content, or if subsequently exposed to warm moist conditions, the greater the risk of corrosion. All constituents may contain chlorides and concrete may be contaminated by chlorides from the external environment. To minimize the chances of deterioration of concrete from harmful chemical salts, the levels of such harmful salts in concrete coming from concrete materials, that is, cement, aggregates, water and admixtures, as well as by diffusion from the environment should be limited. The total amount of chloride content, as Cl, in the concrete at the time of placing shall be as given in Table 7. The total acid-soluble chloride content should be calculated from the mix proportions and the measured chloride contents of each of the constituents. Wherever possible, the total chloride content of the concrete should be determined. 8.2.5.3 Sulfates in concrete. Sulfates are present in most cements and in some aggregates. Excessive amounts of water-soluble sulfate from these or other mixed constituents can cause expansion and disruption of concrete. To prevent this, the total water-soluble sulfate content of the concrete mix. Expressed as SOL should not exceed 4% by mass of the cement in the mix. The sulfate content should be calculated as the total from the various constituents of the mix. The 4% limit does not apply to concrete made with supersulfate cement complying with IS 6909. 8.2.5.4 Alkali aggregate reaction. Some aggregates containing particular varieties of silica may be susceptible to attack by alkalis, NO and O, originating from cement or other sources, producing an expansive reaction which can cause cracking and disruption of concrete. Damage to concrete from this reaction will normally only occur when all the following are present together: A high moisture level within the concrete, B a cement with high alkali content, or another source of alkali, C aggregate containing an alkali reactive constituent. Where the service records of particular cemental aggregate combination are well established and do not include any instances of cracking due to alkali aggregate reaction, no further precautions should be necessary. When the materials are unfamiliar, precautions should take one or more of the following forms: A. Use of non-reactive aggregate from alternate sources. Table 5 Minimum cement content, maximum water-cement ratio and minimum grade of concrete for dipterrant exposures with normal weight aggregates of 20 mm. Nominal maximum size, Clause 6.1.2, 8.2.4.1, and 9.1.2, SIT, Spazure No. Minimum cement content kglm plain concrete. Maximum free water cement ratio. Minimum grade of concrete. Minimum cement content kglnl. Reinforced concrete. Maximum free water cement ratio. Minimum grade of concrete, 2, 3, 4, 6, 7, 8, I. Mild 220 0.60 300 0.5 M203, Moderate 240 0.60 Miss 300 0.SO M253, Severe 2S0 0.SO M20 320 0.4 MJ04, Very Severe 260 0.45 V, Extreme 80 0.40 M20 340 0.45 M2 360 0.40 M3S M40 NC, T and I cement content prescribed in this table is irrepetitive of the GRs of cement and it is inclusive of additions mentioned in 5.2. The additions such diffly asher around granulated blast furnace slag may have taken into account in the concrete composition. With respect to the cement content and water cement ratio, the suitability is established and as Linnell as the maximum 81 nounce cacn into C and unt do not exceed thlymolar pozzolana and ale specified in is 1489. Part I, and is 4S respectively. 2 Minimum grade for plain concrete under mold exposo condition at null specified. 21S4S6:2000 Table 6 Adjustments to minimum cement contents for all regates other than 20 mm. Nominal maximum size, Clause 8.2.4.1, SI nominal maximum adjustments to minimum seam DT no. RF size contents in 1 ABLE 5 mm K and LM evaporation may cause serious concentrations of salts with subsequent deterioration, even where the original salt content of the soil or water is not high. Note, guidance regarding requirements for can at exposed 10 sulfate anic is liven in 1.4. 8.1.6.2 Drainage, I, 2, I, 10-2, 23, 40, 3. At sites where alkali concentrations are high or may plus 40 become very high. The groundwater should be lowered by drainage so that it will not come into direct contact -30 with the concrete. Table 7 Limits of chloride content or concrete, Clause 8.2.5.2, SI type or use 01 concrete no. I, 2, maximum total acid soluble chloride quantity TEXPCD as KLH and Jor Crete, 3. I. Concrete containing metal and 0.4 steam cured at elevated temperature and pre-stressed concrete 2, reinforced concrete or plain concrete 0.6 containing embedded metal. Additional protection may be obtained by the use of chemically resistant stone facing or a layer of plaster of Paris covered with suitable fabric, such as jute thoroughly impregnated with bituminous material. 8.2.7 Compaction. Finishing and curing. Adequate compaction without segregation should be ensured by providing suitable workability and by employing appropriate placing and compacting equipment and procedures. Full compaction is particularly important in the vicinity of construction and movement joints and of embedded water bars and reinforcement. 3. Concrete not containing embedded geometal or any material requiring protection from chloride. B. USC of low alkali. Ordinary Portland cement having total alkali content not more than 0.6%, as Na20 equivalent. Further advantage can be obtained by use of fly ash, grade I, conforming to is3812 or granulated blast furnace slag conforming to is12089 as part replacement of ordinary Portland cement, having total alkali content as Na20 equivalent not more than 0.6%, provided fly ash content is at least 20% or slag content is at least 50%. C. Measures to reduce the degree of saturation of the concrete during service such as use of impermeable membranes. D. Limiting thiecement content in the concrete mix and thereby limiting total alkali content in the concrete mix. For more guidance, specialist literatures may be referred. 8.2.6 Concretine aggressive soils and water. 8.2.6.1 General. The destructive action of aggressive waters on concrete is progressive. The rate of deterioration decreases as the concrete is made stronger and more impermeable, and increases the salt content of the water increases. Where structures are only partially immersed or are in contact with aggressive soils or waters on an ECD only, good finishing practices are essential for durable concrete. Overworking the surface and the addition of water cement to aid in finishing should be avoided. The resulting lance will have impaired strength and durability and will be particularly vulnerable to freezing and thawing under wet conditions. It is essential to use proper and adequate curing techniques to reduce the permeability of the concrete and enhance its durability by extending the hydration of the cement, particularly in its surface zone. IZ13.5. 8.2.8 Concrete in sea water. Concrete in sea water or exposed directly along the sea coast shall be at least M20 grade in the case of plain concrete and M30 in case of reinforced concrete. The use of slag or pozzolanissement is advantageous under such conditions. 8.2.8.1 Special attention shall be given to the design of Admixtures obtained he densest possible concrete, slag, broken brick, soft limestone, soft sandstone, or other porous or weak aggregates shall not be used. 8.2.8.2 As far as possible, preference shall be given to precast members unreinforced, well cured and hardened, without sharp corners, and having trowel smooth finished surfaces free from crazing, cracks or other defects. Plastering should be avoided. 8.2.8.3 No construction joints shall be allowed within 600 mm below low water level or within 600 mm of the upper and lower planes of wave action. Where 21 is 456, 1000 unusually severe conditions or abrasion are anticipated, such parts of the work shall be protected by bituminous or silicofluoride coatings or stone facing did with bitumen. 8.2.8.4 In reinforced concrete structures care shall be taken to protect the reinforcement from exposure to saline atmosphere during storage, fabrication and use. It may be achieved by treating the surface of reinforcement with cement wash or by suitable methods. 9 Concrete mix proportioning. 9.1 Mix proportion. The mix proportions shall be selected to ensure the workability of the fresh concrete, and when concrete is hardened, it shall have the required strength, durability, and surface finish. 9.1.1 The determination of the proportions of cement, aggregates, and water to attain the required strengths shall be made as follows. A. By designing the concrete mix, such concrete shall be called design mix concrete, or B. By adopting nominal concrete mix, such concrete shall be called nominal mix concrete. Design mix concrete is preferred to nominal mix. If design mix concrete cannot be used for any reason on the work for grades of M20 or lower, nominal mixes may be used with the permission of engineer in charge, which, however, is likely to involve a higher cement content. 9.1.2 Information required in specifying a particular grade of concrete. the following information shall be included: A. Type of mix, that is, design mix concrete of nominal mix concrete. H. Grade designation. C. Type of cement. D. Maximum nominal size of aggregate. E. Minimum cement content, for design mix concrete. F. Maximum water cement ratio. G. Workability. H. Mix proportion, for nominal mix concrete. J. Exposure conditions as per tables 4 and 5. K. Maximum temperature of concrete at the time of placing. M. Method of placing, and N. Degree of supervision. 9.1.2.1 In appropriate circumstances, the following additional information may be specified: A. Type of aggregate. B. Maximum cement content. And C. Whether an admixture shall or shall not be used and the type of admixture and the condition of use. 9.2 Design mix concrete. 9.2.1 As the guarantor of quality of concrete used in the construction, the constructor shall carry out the mix design, and the mix so designed, not the method of design, shall be approved by the employer within the limitations of parameters and other stipulations laid down by the standard. 9.2.2 The mix shall be designed to produce the grade of concrete having the required workability and a characteristic strength not less than appropriate T values given in TABLE2. The target mean strength of concrete mix should be equal to the characteristic strength plus 1.65 times the standard deviation. 9.2.3 Mix design done earlier not prior to 1 year may be considered adequate for later work provided there is no change in source and the quality of the materials. 9.2.4 Standard deviation. The standard deviation for each grade of concrete shall be calculated separately. 9.2.4.1 Standard deviation Blued on test strength of sample A, number of test results of sample S. The total number of test strength of samples required to constitute an acceptable record for calculation of standard deviation shall be not less than 30. Attempts should be made to obtain the 30 samples as early as possible when a mix is used for the first time. B. In case of significant changes in concrete, when significant changes are made in the production of concrete batches, for example changes in the materials used, mix design, equipment or technical control, the standard deviation value shall be separately calculated for such batches of concrete. C. Standard deviation to be brought up to date. The calculation of the standard deviation shall be brought up to date after every change of mix design. 9.2.4.2 Assumed standard deviation where sufficient test results for a particular grade of concrete are not available. The value of standard deviation given interval May 8 be assumed for design of mix in the first instance. As soon as the results of samples are available, actual calculated standard deviation shall be used and the mix designed properly. 22 is456, 2000 However, when adequate past records for a similar grade exist and justified that designer a value of standard deviation different from that shown in Table 8, it shall be permissible to use that value. Table 8 Assumed standard Jaleviatution, Clause E 9.2.4.2 and Tub/Pound 11, grade of concrete as 5 of D standard deviation n/Narns Mio L5 Miss M204.0 M2 SMJO MJSM 405.0 M4 SM. So note the above values correspond to the site control having proper storage of cement, weigh hatching of all material, controlled addition of water, regular checking of all nate joules, aggregate and jadings and moisture content, and periodical checking of work 3 highlighting and strength. WRC there I deviation from TH above the values given in the Admixtures shall he inc via CD high in/none. 9.3 Nominal mix concrete. Nominal mix concrete may be used for concrete of M20 or lower. The proportions of Worknalls for nominal mix concrete shall be in accordance with 1:1 9.3.1 The cement content of the mix specified in Table 9 for any nominal mix shall be proportionately increased if the quantity of water in a mix has to be increased to overcome the difficulty of placement and compaction, so that the water-cement ratio as specified is not exceeded. 10. Production of concrete. 10.1 Quality assurance measures. 10.1.1 In order that the properties of the completed structure be consistent with the requirements and the assumptions made during the planning and the design, adequate quality assurance measures shall be taken. The construction should result in satisfactory strength, serviceability, and long-term durability so as to lower the overall life cycle cost. Quality assurance in construction activity relates to proper design, USC of adequate materials and components to be supplied by the producers, proper workmanship in the execution of works by the contractor, and ultimately proper care during the use of structure, including timely maintenance and repair by the owner. 10.J.2 Quality assurance measures are both technical and organizational. Some common cases should be specified in a general quality assurance plan, which shall identify the key elements necessary to provide fitness of the structure and the means by which they are to be provided and measured, with the overall purpose to provide confidence that the realized project will work satisfactorily in service, fulfilling intended needs. The job of quality control and quality assurance would involve quality audit of both the inputs as well as the outputs. Inputs are in the form of materials for concrete, workmanship in all stages of hatching, mixing, transportation, placing, compaction and curing, and the related plant, machinery, and equipments, resulting in the output in the form of concrete in place. To ensure proper performance, it is necessary that each step in concreting, which WI11 be covered by the next step, is inspected as the work proceeds. See also 17. Table, Proportions for Nominal Mix Concrete, Clause 9.3 Lind 9.L, Grade of concrete. Total quantity of dry aggregates by I/las per so kg of cement, to be taken as the SUID of the individual M1I$IES of FTNTAOD coarse algreg H1ES, kg, MTLX proportion of fine aggregate to ors axgrade, HYL/1 ATT, quantity of what are per so kg of cement, max I, 2, 4, M5 Ru M7 625 M10 480 M15 330 M20 201 generally 1:2 but subject to an upper limit of I, 11 and a 60/45 lower limit of 1:21/1. 34-32-30 Note 11 LE proportion of the fine to coarse aggregates should be adjusted from upper limit 10 lower limit progressively as the rating of fine AGL gates becomes finer and the maximum size of coarse aggregate becomes larger. Graded coarse aggregate shall be used. Example for M of Araradina of fine aggregate, that is, Zone 2 of Table 4 of is 83. The proportions shall be L1 foot 1 inch 1:1 and L2/:. For maximum size of NGGG and TES 10 mm, 20 mm and 40 mm respectively, 23 is 456, 2001 0.1.3 Each party involved in the realization of a project should establish and implement a quality assurance plan for its participation in the project. Suppliers and subcontractors' activities shall be covered in the plan. The individual quality assurance plans shall fit into the general quality assurance plan. A quality assurance plan shall define the tasks and responsibilities of all persons involved. Adequate control and checking procedures and the organization and maintaining adequate documentation of the building process and its results. Such documentation should generally include a. Test reports and manufacturer's certificate for materials. Concrete mix design details. B. Pour cards for site organization and clearance for concrete placement. C. Record of site inspection of workmanship, field tests. D. Non-conformance reports. Change orders. E. Quality control charts. And 1. Statistical analysis. Note: quality control charts are recommended wherever the concrete is in continuous production over considerable period. 10.2 Batching. To avoid confusion and error in batching, consideration should be given to using the smallest practical number of different concrete mixes on any site or in any one plant. In hatching concrete, the quantity of both cement and aggregate shall be determined by mass, admixture. If solid, by mass, liquid admixture may however be measured in volume or mass, Water shall be weight Oj measured by volume in a calibrated tank, set also is 4925. Ready mixed concrete supplied by ready mixed concrete plant shall be preferred. For large and medium project sites the concrete shall be sourced from ready mixed concrete plants or from on-site or off-site hatching and mixing plants, C is 4926. 10.2.1 Except where it can be shown to the satisfaction of the engineer in charge that supply of properly graded aggregate of uniform quality can be maintained over a period of work. The grading of aggregate should be controlled by obtaining the coarse aggregate in different sizes and blending them in the right proportions when required. The different sizes being stocked in separate stockpiles. The material should be stockpiled for several hours, preferably a day before use. The grading of coarse and fine aggregate should be checked as frequently as possible. The frequency for a given job being determined by the engineer in charge to ensure that the specified grading is maintained. 10.2.2 The accuracy of the measuring equipment shall be within plus or minus 2% of the quantity of cement being measured and within plus or minus 3% of the quantity of aggregate. Admixture sand water being measured. 10.2.3 Proportion flow and grading of aggregates shall be made by trial in such a way so as to obtain densest possible concrete. All ingredients of the concrete should be used by mass only. 10.2.4 Volume batching may be allowed only where weight batching is not practical and provided accurate bulk densities of materials to be actually used in concrete have earlier been established. Allowance for bulking shall be made in accordance with is 2386, Part 3. The mass-volume relationship should be checked as frequently as necessary. The frequency for the given job being determined by engineer in charge. 10 Ensure that the specified grading is maintained. 10.2. It is important to maintain the water-cement ratio constant at its correct value. To this end, determination of moisture contents in both fine and coarse aggregates shall be made as frequently as possible. The frequency for a given job being determined by the engineer in charge according to weather conditions. The amount of the added water shall be adjusted to compensate for any observed variations in the moisture contents. For the determination of moisture content in the aggregates. Is 2386, Part 3, may be referred to allow for the variation in mass of aggregate due to variation in their moisture content. Suitable adjustments in the masses of aggregates shall also be made. In the absence of exact data, only in the case of nominal mixes, the amount of surface water may be estimated from the values given in Table 10. Table 10 Surface water carried by aggregate, Clause 10.2.5, approximate quantity of surface WA ter, I, 2, 3, I, very wet sand 7.52, modern lel, wet sand 5.03, moist sand 2.54, moist gravel or crushed rock 1.25-2,52 coarse earth aggregate. Less the altered will quarry. 4. 120 80 40 20 to 41 0.2.6 No substitutions in materials used on the work or alterations in the established proportions. Except as permitted in 10.2.4 and 10.2. Shall be made without additional tests to show that the quality and strength of concrete are satisfactory. 10.3 Mixing concrete can be mixed in a mechanical mixer. The mixer should comply with IS 179 and IS 12119. The mixers shall be fitted with water measuring, metering, devices. The mixing shall be continued until there is a uniform distribution of the materials and the masses. 24 18456, 1000 U before ton in color and consistent. Y. If there is aeration alter unloading from the mixer, the concrete should be remixed. 10.3.1 Poor guidance, the mixing time shall be at least 2 minutes. For other types of more efficient mixers, manufacturers' recommendations shall be followed. For hydrophobic cement it may be decided by the engineer in charge. 10.3.2 Workability should be checked at frequent intervals, ITT is 1199. 10.3.3 Dosages of retarders, plasticizers, and superplasticizers shall be restricted to .s. 1.0 and 2.0% respectively by weight of cementitious materials, and unless a higher value is agreed upon between the manufacturer and the constructor based on performance test. 11 Formwork 11.1 General The formwork shall be designed and constructed so as to remain sufficiently rigid during placing and compaction of concrete, and shall be such as to prevent loss of slurry from the concrete. For further details regarding design, detailing, etc. reference may be made to is456. The tolerances on the shapes, lines, and dimensions shown in the drawing shall be within the limits given below. A. Deviation from specified dimensions off cross-section plus _ 162 mm of columns iod beams. B. Deviation from dimensions off utens 1, dimensio. In plan plus 50 mm minus 12 2, eccentricity 3, thickness 0.02 times the width of the footing in the direction of deviation but not more than s ohm plus or minus o.os times the specified thickness. These tolerances apply to concrete dimensions only, and not to positionulof vertical reinforcing steel or to wells. 11.2 en _tnatme dt01 Formwork all rubbish, particularly, chippings, shavings and sawjuates shall be removed from the interior optophones before the concrete is placed. The face of formwork in contact with the concrete shall be cleaned and treated with form release agent. Release agents should be applied so as to provide a thin uniform coating to the phones without coating reinforcement. 11.3 STRLPPLNL 11 Me phones shall not be released until the concrete has achieved a strength of at least twice the stress to which the concrete may be subjected at the time of removal of phone work. The strength referred to shall be that of concrete using the same cement and aggregates and admixture, if any, with the same proportions and cured under conditions of temperature and moisture similar to those existing on the work. 1.3.1 While at above criteria of strength shall be the guiding factor for removal of formwork, in normal circumstances where ambient temperature does not fall below ISOC and where ordinary Portland cement is used and adequate curing is done following STRI WNG period may deem to satisfy the guideline given in 11.3, type of formwork/C minimum period before striking formwork. A. Verticaphone work to columns, walls, beam 16 to 24 HB, soffit formwork to slabs, props to bear fixed immediately after removal of formwork, 3 days. C. Soffit phonework to beams, props to be refixed immediately after removal of formwork. D. Props to slabs, 7 days. 1. Spanning up to 4.5 m. 2. Spanning over 4 sm 7 days. 140 AYSE, props to beams and arches, 1. Spanning up to 6 m. 2. Spanning over 6 m 14 days. 21 days for other cements and lower temperature. The stripping time recommended above may be suitably modified. 1.3.2 The number of props left under their sand disposition shall be such as to be able to safely carry the full dead load of the slab, beam or arch as the case may be told there with any live load likely to occur during curing or further construction. 1.3.3 Where the shape of the element is such that the formwork has reentrant angles, the formwork shall be removed as soon as possible after the concrete has set, to avoid shrinkage cracking occurring due to the restraint imposed. 11 Assembly of reinforcement 12.1 Reinforcement shall be bent and fixed in accordance with procedure specified in IS 2502. The high-strength defoned steel bars should not be bent 2118 818/07-52 is 456, 2000 or straightened without the approval of engineer in charge. Bar bending schedules shall be prepared for all reinforcement work. J2.2 All reinforcement shall be placed and maintained in the position shown in the drawings by providing proper cover blocks, spacers, supporting bars, etc. 2.2.1 Crossing bars should not be lack welded for assembly of reinforcement unless permitted by engineer in charge. 12 Placing of reinforcement rough handling, shock loading, prior to embedment, and the dropping off reinforcement from a height should be avoided. Reinforcement should be secured against displacement outside the specified limits. 12.3.1 Tolerances on placing, F. Reinforcement unless otherwise specified by engineer in charge, the reinforcement shall be placed within the following tolerances, a. For effective depth 200 none or less plus or minus 10 none b. For effective depth more than 200 mm plus or minus 15 mm T 2.32 Tolerance for cover unless specified otherwise. Actual concrete cover should not deviate from the required nominal cover plus 10 by 0 mrn. Nominal cover as given in 26.4.1 should be specified to all steel reinforcement including links. Spacers between the links, or the bars where no links exist, and the formwork should be of the same nominal size as the nominal cover. Spacers, chairs, and other supports detailed on drawings, together with such other supports as may be necessary, should be used to maintain the specified nominal cover to the steel reinforcement. Spacers or chairs should be placed at a maximum spacing of and closer spacing may sometimes be necessary. Spacers, cover blocks should be of concrete of same strength or PVC. 1.2.4 Welded joints or mechanical connections. Welded joints or mechanical connections in reinforcement may be used, but in all cases of important connections, tests shall be made to prove that their joints are of the full strength of bars connected. Welding of reinforcements shall be done in accordance with the recommendations of IS 2751 and IS 94J7. 12.5 Where reinforcement bars up to 12 mm for high-strength deformed steel bars and up to 16 mm for mild steel bars are bent aside at construction joints and afterwards bent back into their original positions. Care should be taken to ensure that at no time is the radius of the bend less than 4 bar diameters for plain mild steel or against 6 bar diameters for deformed bars. Care shall also be taken when bending hack bars, to ensure that the concrete around the bar is not damaged beyond the bend. 12.6 Reinforcement should be placed and tied in such a way that concrete placement be possible without segregation of the mix. Reinforcement placing should allow compaction by immersion vibrator. Within the concrete mass, different types of metal in contact should be avoided to ensure that bimetal corrosion does not take place. 13 Transporting, placing, compacting, and curing. 1.3.1 Transporting and handling. After mixing, concrete shall be transported to the formwork as rapidly as possible. Be methods which will prevent the segregation of gas of any of the ingredients or ingress of foreign matter or water, and maintaining required workability. 13.1.1 During hoy of cold weather, concrete shall be transported in deep containers. Other suitable methods to reduce the loss of water, high evaporation in hot weather and heat loss in cold weather, may also be adopted. 13.2 Placing tile. Concrete shall be deposited as nearly as practicable in its final position to avoid rehandling. The concrete shall be placed and compacted before initial setting of concrete commences and should not be subsequently disturbed. Methods of placing should be such as to preclude segregation. Care should be taken to avoid displacement of reinforcement or movement of ironwork. As a general guidance, the maximum permissible free fall of concrete may be taken as 1.5 Il. 13.3 Co. Compaction. Concrete should be thoroughly compacted and fully worked around the reinforcement, around embedded fixtures and into corners of the formwork. 13.3.1 Concrete shall be compacted using mechanical vibrators complying with IS 2505, IS 2506, IS 2514 and IS 4656. Over vibration and under vibration of concrete are harmful and should be avoided. Vibration of very wet mixes should also be avoided. Whenever vibration has to be applied externally, the design of formwork and the disposition of vibrators should receive special consideration to ensure efficient compaction and to avoid surface blemishes. 26 is456, 2013.4 Const meltion joints and cold joints. Joints are a common source of weakness and, therefore, it is desirable to avoid them. If this is not possible, their number shall be minimized. Concreting shall be carried out continuously up to construction joints, the position and arrangement of which shall be indicated by the designer. Construction joints should comply with IS 11817. Construction joints shall be placed at accessible locations to permit cleaning out of lands, cement slurry and unsound concrete, in order to create rough/uneven surface. It is recommended to clean out lands and cement slurry high using wire brush on the surface of joint immediately after initial setting of concrete and to clean out the same immediately thereafter. The prepared surface should be in a clean saturated surface dry condition when fresh concrete is placed against it. In the case of construction joints at locations where the previous pour has been cast against shuttering, the recommended method of obtaining a rough surface for the previously poured concrete is to expose the aggregate with one high-pressure water jet or any other appropriate means. Fresh concrete should be thoroughly vibrated near construction joints so that mortar from the new concrete flows between large aggregates and develop proper bond with old concrete. Where high shear resistance is required at the construct ion joints, shear keys he provided. Sprayed curing membranes and release agents should be thoroughly removed from joint surfaces. 13.5 Urine of ordinary Portland cement and at least 10 days where mineral admixtures or blended cements are used. The period of curing shall not be less than 0 days for concrete exposed to dry and hot weather conditions. In the case of concrete where mineral admixtures or blended cements are used, it is recommended that above minimum periods may be extended to 14 days. 13.5.2 Membrane. Urine approved curing compounds may be used in lieu of moist curing with the permission of the engineer in charge. Such compounds shall be applied to all exposed surfaces of the concrete as soon as possible after the concrete has set. Impermeable membranes such as polyethylene sheeting covering closely the concrete surface may also be used to provide effective barrier against evaporation. 13.5.3 For the concrete containing Portland pozzolana cement, Portland slag cement or mineral admixture, period of curing may be increased. 13.6 Supervision. It is exceedingly difficult and costly to alter concrete once placed. Hence, constant and strict supervision of all the items of the construction is necessary during the progress of the work, including the proportioning and mixing of the concrete. Supervision is also of extreme importance to check the reinforcement and its placing before being covered. 13.6.1 Before any important operation, such as concreting or stripping of the formwork is started, adequate notice shall be given to the construction supervisor. Curing is the process of preventing the loss of moisture. 14 Concreting under special from the concrete whilst maintaining a satisfactory conditions temperature regime. The prevention of moisture loss from the concrete is particularly important if water. 14.1 Work in extreme weather conditions. Cement ratio is low. If the cement has a high rate of during hot or cold weather, the concreting should be strength development. If the concrete contains done as per the procedure set out in is 7861 granulated blast furnace slag or pulverized fuel ash. Part 1, or is 7861, Part 2. Tila and Gregime should also prevent the development of high temperature gradients within the concrete. 14.2 Underwater concrete. In the rate of strength development at early ages of concrete made with supersulfate cement is significantly reduced at lower temperatures. Supersulfate cement concrete is seriously affected by inadequate curing and the surface has to be kept moist for at least 7 days. 13.5.1 Moist curing. Exposed surfaces of concrete shall be kept continuously in a damp of wet condition by pending or by covering with a layer of sacking, canvas, hessian or similar materials and kept constantly wet for at least 7 days from the date of placing concrete. In case 14.zl1 when it is necessary to deposit concrete underwater, the methods, equipment, materials, and proportions of the mix to be used shall be submitted to and approved by the engineer in charge before the work is started. 14.2.2 Underwater concrete should have a slump recommended in 7.1. The water-cement ratio shall not exceed 0.6 and may need to be smaller, depending on the grade of concrete or the type of chemical attack. For aggregates of 40 rom maximum particle size, the cement content shall be at least 350 kg/m of concrete. 14.1.3 Cofferdams or forms shall be sufficiently tight. 27 is 456, 2000 to ensure still water if practicable. and in any queue to reduce the flow of water to less than 3 m1 min through the space into which concrete is to be deposited. Cofferdams or phones in still water shall be sufficiently tight to prevent loss of mortar through the walls. Dewatering by pumping shall not be done while concrete is being placed until 24h thereafter. 14.2.4 Concrete cast under water should not fall freely through the water. Otherwise it may be leached and become segregated. Concrete shall be deposited continuously until it is brought to the required height. While depositing, the top surface shall be kept as nearly level as possible and the phonation of seams avoided. The methods to be used for depositing concrete under water shall be one of the following: a. Treme the concrete is placed through vertical pipes, the lower end of which is always inserted sufficiently deep into the concrete which has been placed previously but has not set. The concrete emerging from the pipe pushes the material that has already been placed to the side and upwards and thus does not come into direct contact with water. When concrete is to be deposited under water by means of treme, the top section of the treme shall be a hopper large enough to hold an entire batch of the mix or the entire contents the transporting bucket, if any. The treme pipe shall be not less than 200 mm in diameter and shall be large enough to allow a free flow of concrete and strong enough to withstand the external pressure if the water in which it is suspended, even if a penial vacuum develops inside the pipe. Preferably, flanged steel pipe of adequate strength for the job should be used. A separate lifting device shall be provided for each treme pipe with its hopper at the upper end. Unless the lower end of the pipe is equipped with an approved automatic check valve, the upper end of pipe shall be plugged with a wadding of the gunny sacking or other approved material before delivering the concrete to the treme pipe through the hopper, so that when concrete is forced down from the hopper to the pipe it will force the plug, and along with it any water in the pipe, down the pipe and out of the bottom end, thus establishing a continuous stream of concrete. It will be necessary to raise slowly treme in order to cause a uniform flow of the concrete, but the treme shall not be emptied till that water enters the pipe. At all times after the placing of concrete is started and until all the concrete is placed, the lower end of the treme pipe shall be below the top surface of the plastic concrete. This will cause the concrete to build up from below instead of flowing out over the surface, and thus avoid formation of lands layers. If though cluco in though treme is tenled while depositin, though tromeo shall bonist ilkseld d1 concrete surface, and done loss _04 by ick valvo, it shall be rc pluladot though to pend, as the beginning l. Before refl11 inl for depositin, concrete. b. Direct placement with pumps as in the case of the treme method, though vertical end piece of the pipeline is always inserted sufficiently deep in the previously cast concrete and should not move to TLTE side during pumping. c. Bucket. The top of the bucket shall be covered with a canvas flap. The bottom doors shall open freely downward and outward when tripped. The bucket shall be died completely and lowered slowly to avoid back water. The bottom doors shall not be opened until the bucket rests on the surface upon which the con Series 2 is to be deposited, and when discharged, shall be withdrawn slowly until well above the concrete. d. Bags of at least 0.028 m capacity of jute or other coarse cloth shall be filled about 2/3 full of concrete, the spring turned under so that BAA is square-ended and securely tied. They shall be placed carefully in header and stretcher courses so that the whole mass is interlocked. Bags set for this purpose shall be free from deleterious materials. e. Grouting. A series of round cages made from mesh of 6 mm steel and extending over the full height to be concreted shall be prepared and laid vertically over theria to be concrete so that the distance between centers of the cases and also to the faces of the concrete shall not exceed 1 meter. Stone aggregate of not less than SOM normare than 200 mziza shall be deposited outside the stool cages over the full area and height to be concrete with due care to prevent displacement of the cages. A stable 1:2 cement sand grout with a water cement ratio of not less than 0.6 and not marked than 0.8 shall be prepared in a mechanical mixer and sent down under pressure, about 0.2 n/m2, through 38to50 nundiameter pipes 10 in adding in ta steel cages about so above at the bottom of the concrete. As the N ratio proceeds, the pipe shall be raised gradually up to a height of not more than 6,000 nun above its starlin level, after which it may be withdrawn and pl into the next kale for further grouchy all by the same procedure. After ifutanel the whole area for a height of about 600 mm, the same operation shall be repeated, if necessary. For the next layer of 28L456, 1600 mm and so on. The amount of grout to be sent down shall be sufficient to fill the voids, which may be either ascertained or assumed as 55% of the volume to be concreted. 14.2.5 To minimize the formulation of lands, great care shall be exercised not to disturb the concrete as far as possible while it is being deposited. For testing at 28 days. Additional samples may be required for various purposes, such as to determine the strength of concrete at 7 days or at the time of striking the formwork, or to determine the duration of curing, or to check the testing error. Additional samples may also be required for testing samples cured by accelerated methods as described in IS 9103. The specimen shall be tested as described in IS S16. 15 Sampling and strength of designed concrete mix. 15.1 General samples from fresh concrete shall be taken as per IS 1199, and cubes shall be made, cured, and tested at 28 days in accordance with IS S16. 15.4 Test results of sample. The test results of the sample shall be the average of the strength of 3 specimens. The individual variation should not be more than plus or minus ls% of the average. If more, the test result of the sample are invalid. 16 Acceptance criteria. 15.1.1 In order to get a relatively quicker idea of the quality of concrete, optional tests on beams for modulus of rupture at 72 plus or minus 2H or at 7 days, or compressive strength tests at 7 days may be carried out in addition to 28 days compressive strength test. For this purpose the values should be arrived at based on actual testing. In all cases the 28 days compressive strength specified in Table 2 shall only be the criterion for acceptance or rejection of the concrete. 15.1 Frequency of sampling. 15.2.1 Sampling procedure. A random sampling procedure shall be adopted to ensure that a concrete batch shall have a reasonable chance of being tested, that is, the sampling should be spread over the entire period of concreting and cover all mixing units. 15.2.2 Frequency. The minimum frequency of sampling of concrete of each grade shall be in accordance with the following. 16.1 Compressive strength. The concrete shall be deemed to comply with the strength requirements when both the following condition are met. A. The mean strength determined from any group of 4 consecutive test results compiles with the appropriate limits in COL2 of Table 11. B. Any individual test result complies with the appropriate limits in COL3 of Table I. 16.2 Flexural strength. When both the following conditions are met, the concrete complies with the specified flexural strength. A. The mean strength determined from any group of 4 consecutive test results exceeds the specified characteristic strength by at least 0.3 n/mn12. B. The strength determined from any test result is not less than the specified characteristic strength less 0.3 n/mm1. Quantity of concrete in the number of samples work, Mi56, is 16 to 30 31 to 50 51 and above 1 2 3 4 4 plus 1 additional sample for each additional 50 m or part thereof. At least 1 sample shall be taken from each shift. Where concrete is produced at continuous production unit, such as ready mixed concrete plant, frequency of sampling may be agreed upon mutually by suppliers and purchasers. 15.3 Test specimen. 3 test specimens shall be made for each sample. 16.3 Quantity of concrete represented by strength. T results. The quantity of concrete represented by a group of 4 consecutive test results shall include the batches from which the first and last samples were taken together with all intervening batches. For the individual test result requirements given in COL2 of Table 2 or in Item B of 16.2, only the particular batch from which sample was taken shall be at risk. Where the mean rate of sampling is not specified, the maximum quantity of concrete that 4 consecutive test results represent shall be limited to 60 m. 16.4 If the concrete is deemed not to comply pursuant to 16.3. The structural adequacy of the parts affected shall be investigated, see 17, and any consequential action as needed shall be taken. 29 is 456. 2016.5 Concrete of each grade shall be assessed separately. 16.6 Concrete is liable to be rejected if it is porous or honeycombed. Its placing has been interrupted without providing a proper construction joint. The reinforcement has been displaced beyond the tolerances specified. Or construction tolerances have not been met. However, the hardened concrete may be accepted after carrying out suitable remedial measures to the satisfaction of the engineering charge. 17 Inspection and testing of structures. There is a system to verify that the quality is satisfactory in individual parts of the structure, especially critical ones. 17.2 Immediately after stripping the formwork, all concrete shall be carefully inspected and any defective work or small defects either removed or made good before concrete has thoroughly hardened. 17.3 Testing in case of doubt regarding grade of concrete used, either due to poor workmanship or based in results of cube strength tests, compressive strength tests of concrete on the basis of 17.4 and/or load test, see 17.6, may be carried out. 17.1 Inspection to ensure that the construction complies with the design and inspection procedure should be set up covering materials, records, workmanship and construction. 17.1.1 Tests should be made on reinforcement and the constituent materials of concrete in accordance with the relevant standards. Where applicable, use should be made of suitable quality assurance schemes. 17.1.2 Care should be taken to see that a. Design and detail are capable of being executed to a suitable standard, with due allowance for dimensional tolerances. B. There are clear instructions on inspection standards. C. There are clear instructions on permissible deviations. D. Elements critical to workmanship, structural performance, durability and appearance are identified. And 17.4 Core Test 17.4.1 The points from which cores are to be taken and the number of cores required shall be at the discretion of the engineer in charge and shall be representative of the whole of concrete concerned. In no case, however, shall fewer than 3 cores be tested. 17.4.2 Cores shall be prepared and tested as described in is456. 17.4.3 Concrete in the member represented by a core test shall be considered acceptable if the average equivalent cube strength of the cores is equal to at least 85% of the cube strength of the grade of concrete specified for the corresponding edge and no individual core has a strength less than 7%. 17.5 In case the core test results do not satisfy the requirement S of 17.4.3 or where such tests have not been done, load test, 17.6, may bear sorted to. 17.6 Load tests for flexural member 17.6.1 Load tests should be carried out as soon as Table 11 Characteristic compressive strength compliance requirement, Clause S 16.1 and 16.3, S-Pilfted rate mean of the group of 4 non-unrelational consecutive NSF results in NFMMJ individual test results in N1MMJ2, 2, 3, MI4. 1, plus 0.825x established standard deviation, rounded off to neajal 0.5 nlmm1, or m20 or above f plus 3 nlmmj whichever is greater. F, plus 0.82s, established standard deviation, rounded off to nealet on/mmj, or L plus 4 n/Mr whichever is ter f, n/mm1. Note in the absence of established value of standard deviation the values given in table 8 L114 be assumed. Temp should be L1 LLIDE 10 obtain results of 30 samples early list possible to ambush value of standard deviation 30 is 45, I. 200, possible after expiry of 28 days from the lily of placing of concrete. 17.6.2 The structure should be subjected to a load equal to full dead load of the structure plus 1.25 tills the imposed load tore a period of 24h and then the unposed load shall be removed. Note DC add load includes self-weight of the structural members, pili weight of finishes and walls or partition. If any L / considered in the design. 17.6.3 The deflection due to it load D load only shall be recorded. If within 24h of removal of the imposed load, the structure does not recover at least 75% of the deflection under superimposed load, the test may be repealed after a lapse of 72h. If the RLCO /CIY is ICS then XO%, the structure shall be DC.ELND10 unacceptable. Point 7. LLIR the maximum deflection in 111,111. Shown during 24h under load I less than 4/1. Where I is the effective span in M, and 1, the overall depth of TOC CCLJ, N in 111,111, it I /not NCCCXS.NYFOI the tel O /CIV10 he measured and the recovery pro V ion, of T7.TL, hall not apply. 17.7 members, 1 THCR than flexural members memher, other than flexural members should he preferably investigated high analysis. 17.H Non-destructive tests Non-destructive tests are used to obtain estimation of the properties of concrete in the structure. Tile methods adopted include ultrasonic pulse velocity, SEC is J33, I, parry I, J and rebound hammer is 13,311, parry 2, LPR and BPC net rat I, N. Pol 0 Utand mat LJ Ty non-destructive VC tests provide alternatives to core tests for externating the strength of concrete in a structure or can supplement the data obtained 110111 a limited NUIII her of course. These methods are based on measuring a concrete properly tie bears sonic RL latic. Ship to strength. The accuracy of these methods, in part, is determined by the degree of correlation H. L //TLTLFNNCTHHNDIHE physical quality 1 I1 till Searle DH, TH non-destruct IVC texts. ANV of TH /IMTHX TNA he .ulot. In which Husk the HN. IIIIHLCNLLRIAHLLL he agreed upon prior to H sling. 11 is 456. 1000 Section 3 General Design Consideration 18 Basis for Design 18.1 Aim of design D be taken from Table 18 for the limit state of collapse. The aim of design is the achievement of an acceptable probability that structures being designed will perform satisfactorily during their intended life. With an appropriate degree of safety, they should sustain all the loads and deformations of normal construction and use and have adequate durability and adequate resistance to the effects of misuse and fire. 18.3 Durability. Workmanship ad terlal. It is assumed that the quality of concrete, steel, and other materials and of the workmanship, as verified by inspections, is adequate FOT safety, serviceability and durability. 18.4 Desilde process 18.2 Methods of design 18.2.1 Structure and structural elements hall nominally be designed by limit state method. Account should be taken of accepted theories, experiment and experience and the need to design for durability. Calculations alone do not produce safe, serviceable and durable structures. Suitable materials quality control, adequate detailing and good supervision are equally important. 18.2.2 Where the limit state method cannot be conveniently adopted, working stress method, see Annex B, may be used. Design, including design for durability, construction, and use in service should be considered as a whole. The realization of design objectives requires compliance with clearly defined standards for materials, production, workmanship, and also maintenance and use of structure in service. 19 Loads and Darkies 19.1 General in structural design account shall be taken off dead imposed and wind loads and forces such as those caused by earthquake and effects due to shrinkage, creep, temperature, etc., where applicable. 18.2.3 Design based on experimental basis. Designs based on experimental investigations on models or full-size structure or element may be accepted if they satisfy the primary requirements of 18.1 and subject to experimental details and the analysis connected therewith being approved by the engineer in charge. 18.2.3.1 Where the design is based on experimental investigation on full-size structure or element, load tests shall be carried out to ensure the following. A. The structure shall satisfy the requirements for deflection, C 23.2, and cracking, C March 2, 35, when subjected to a load for 24H equal to the characteristic load multiplied B. 33 Year where R shall be taken from Table 18 fourth a limit state of serviceability. If within 24H of the removal of the load, the structure does not show a recovery of at least 7% of the maximum deflection shown during THE24H under the load, the test loading should bear peat after a lapse of 72H. The recovery after second test should beat least 7% off the maximum deflection shown during the second test. Note if the maximum deflection in mm, shown during 24H under load is less than 4012/D where I is the effective span in m, and D is the overall depth of the section in ROMIT I not necessary for the to be measured. B. The structure shall have adequate strength to sustain for 24H, a total load equal to the characteristic load multiplied by 1.331 where Y, shall 19.2 dead loads shall be calculated on the basis of unit weights which shall be established taking into consideration material specified for construction. 19.2.1 Alternatively, the dead loads may be calculated on the basis of unit weights of materials liven in is 875, Part 1. Unless more accurate calculations are warranted, the unit weights of plain concrete and reinforced concrete made with sand and gravel or crushed natural stone aggregate may be taken as 24 kN/m/ and 25 kN/m3 respectively. 19.3 Imposed loads, wind loads and snow loads. Imposed loads. Wind loads and snow loads shall be assumed in accordance with is 87s, Part 2, is 87s, Part 3, and is 875, Part 4, respectively. 19.4 Earthquake forces. The earthquake forces shall be calculated in accordance with is 1893. 19.5 Shrinkage, NEP, and temperature L feeds. If the effects of shrinkage, creep and temperature are liable to affect materially the safety and serviceability of the structure, these shall be taken into account in the calculations, see 6.2.4, 6.z.5 and 6.2.6, and is 875, Part 5. 19.5.1 In ordinary building, such low-rise dwelling whose lateral dimension do not exceed 45 m, the 32 is 456, 2000 effects due to temperature fluctuations and shrinkage and creep can be ignored in design calculations. 19.6 Other forces and effects. In addition, account shall be taken of the following forces and effects if they are liable to affect materially the safety and serviceability of the structure. A. Foundation movement, C is 1904, B. Elastic axial shortening, C. Soil and fluid pressure, C is 875, Part 5, D. Vibration, E. Fatigue. O. Impact, C is 875, Part 5, G. Erection loads, C is 875, Part 2, and H. Stress concentration effect due to point load and the like. 19.7 Combination of loads. The combination of loads shall be as given in is 875, Part S. 19.8 Dead load counteracting other loads and FONES. When dead load counteracts the effects due to other loads and forces in structural member or joint, special care shall be exercised by the designer to ensure adequate safety for possible stress reversal. 19.9 Design load. Design load is the load to be taken for use in the appropriate method of design. It is the characteristic load in case of working stress method and characteristic load with appropriate partial safety factors for limit state design. 20. Stability of the structure. 0.1 Overturning. The stability of a structure as a whole against overturning shall be ensured so that the restoring moment can be not less than the sum of 1.2 times the maximum overturning moment due to the characteristic dead load and 1.4 times the maximum overturning moment due to the characteristic imposed loads. In cases where dead load provides the restoring moment, only 0.9 times the characteristic dead load shall be considered. Restoring moment due to imposed loads shall be ignored. 20.1.1 The anchorages or counterweights provided for overhanging members, during construction and service, should be such that static equilibrium should remain, even when overturning moment is doubled. 20.2 Sliding. The structure shall have a factor against sliding of not less than 1.4 under the most adverse combination of the applied characteristic forces. In this case only 0.9 times the characteristic dead load shall be taken into account. 20.3 Probable variation in dead load. To ensure stability at all times, account shall be taken of probable variations in dead load during construction, repair or other temporary measures. Wind and seismic loading shall be treated as imposed loading. 20.4 Moment connection. In designing the framework of a building, provisions shall be made by adequate moment connections or by its system of bracings to effectively transmit all the horizontal forces to the foundations. 20.5 Lateral sway. Linder transient wind load. The lateral sway at the top should not exceed Hi500, where 11 is the total height of the building. For seismic loading, reference should be made to IS456. 21 Fire resistance. 21.1 A structure of structural element required to have fire resistance should be designed to possess an appropriate degree of resistance to flame penetration, heat transmission and failure. The fire resistance of a structural element is expressed in terms of time in hours in accordance with IS 1641. Fire resistance of concrete elements depends upon details of member size. Cover to steel reinforcement detailing and type of aggregate, normal weight or lightweight, used in concrete. General requirements for fire protection are given in IS 1642. 21.2 Minimum requirements of concrete cover and member dimensions for normal weight aggregate concrete members so as to have the required fire resistance shall be in accordance with 26.4.3 and Fig.L respectively. 21.3 The reinforcement detailing should reflect the changing pattern of the structural section and ensure that both individual elements and the structure as a whole contain adequate support. Ticks, bonds, and anchorages for the required tire resistance. 21.3.1 Additional measures such as application of fire-resistant finishes. Provision of fire-resistant false ceilings and sacrificial steel in tensile zone, should be adopted in case the nominal cover required exceeds 40 mm for beams and 35 mm for slabs, to give protection against spelling. 21.4 Specialist literature may be referred to for determining fire resistance of the structures which have not been covered in Fig 1 or Table 16a. 2116 L5/07-633 is 456. 2000 Beam solid slab PW rib by waffle slabs IBJ. Full V exposed columns. BF.T:. 1 face expose _____. Fire resistance 0.5 I 1.5234 mg/team width BMM 200 ZU 240 280 rib width /11 slabs BW mil 125 125 12s 125 ISO 175 minimum thickness, column dimension TB for DJ. Fully 50% 1 of floors exposed X pollock face deep exposed mid 30 111 mm 75 150 m 295 200 160 120 110 252 X 140 125 on 200 160 150 400.100 200 170 450 350 240 Notes 1 These minimum dimensions relate specifically to the covers given in Table 16a. ZP is the percentage of steel reinforcement. Minimum wall thick. U 10.4% 0.4% SPSL %1 1% MMMMMM 150 100 100 ISO 120 100 175 140 100 160 100 200 150 240 180 flow. 1 Minimum dimensions of reinforced concrete 1 LL members for fire resistance 22 Analysis 22.1 General All structures may be analyzed by the linear clastic theory to calculate internal actions produced by design loads. In lieu of rigorous elastic analysis, a simplified analysis as given in 22.4 for frames and as given in 22.5 for continuous beams may be adopted. 22.2 Effective span. Unless otherwise specified, the effective span of a member shall be as follows: a simply supported beam or slab. The effective span of a member that is not built integrally with its supports shall be Tachina's clear span plus the effective depth of slab or beam or center to center of supports, whichever is less. 34 is 456, 2000 b, continuous beam or slab, in the case of continuous beam or slab. If the width of the support is less than 1/12 of the clear span, the effective span shall be as in 22.2, a. If the supports are wider than 1/12 of the clear span or 600 mm whichever is less, the effective span shall be taken as under, 1, for end span with one end fixed and the other continuous, or for intermediate spans. The effective span shall be the clear span between supports. 2. For end span with one end free and the other continuous, the effective span shall be equal to the clear span plus half the effective depth of the beam or slab, or the clear span plus half the width of the discontinuous support, whichever is less. 3. In the case of spans with roller or rocket bearings, the effective span shall always be the distance between the centers of bearings. C. Cantilever. The effective length of a cantilever shall be taken as its length to the face of the support plus half the effective depth except where it forms the end of a continuous beam, where the length to the center of support shall be taken. D. Frames. In the analysis of a continuous iron, center to center distance shall be used. 2.4.1 Arrangement of imposed load. A. Consideration may be limited to combinations of 1. Design dead load on all spans with full design imposed load on two adjacent spans, and 2. Design dead load on all spans with full design imposed load on alternate spans. B. When design imposed load does not exceed 3/4 of the design dead load, the load arrangement may be design dead load and design imposed load on all the spans. Note, dash. For beams and slabs continuous over support 22.4.1 ca, RNA, be assumed. 2.4.2 Substitute frame for determining the moments and shears at any floor or roof level due to gravity loads. The beams at that level together with columns above and below with their far ends 2xed may be considered to constitute the frame. 2.4.2.1 Where side sway consideration becomes critical due to unsymmetry in geometry or loading, rigorous analysis ITIE be required. 2.4.3 For lateral loads, simplified methods may be used to obtain the moments and shears for structures that are symmetrical. For unsymmetrical or very tall structures, more rigorous methods should be used. 22.3 Stiffness. 2.3.1 Relative stiffness. The relative stiffness of the members may be based on the moment of inertia of the section determined on the basis of any one of the following definitions. A. Gross section, the cross section of the member ignoring reinforcement. B. Transformed section, the concrete cross section plus the area of RC inter CCMCRN transformed on the basis of modular ratio, STLBI.3, or C. Crack section the area of concrete in compression plus the area of reinforcement transformed on the basis of modular routine. The assumptions made shall be consistent for 111 The members of the structure throughout any analysis. 2.3.2 For deflection calculations, Appropriate values of moment of inertia as specified in Annex C SHGUIUB used 22.4 structural frames. The simplifying assumptions as given in 22.4.1 to 22.4.3 may be used in the analysis of frames. 22.5 Moment and shear coefficient phi for continuous beams. 22.5.1 Unless more exact estimates are made for beams of uniform cross-section which support substantially uniformly distributed loads over 3 or ILHIR/1 OLS which do not differ by more than 15% of the longest, the bending moments and shear forces used in design may be obtained using the coefficients given in Table 1.2 and Table 13 respectively. For moments at supports where two unequal spans meet or JN case where the spans are not equally loaded, the average of TTLC2 values for the negative moment at the STLPPTUT may be taken for design. Where coefficients given in Table 12 are used for calculation of bending moments, redistribution referred to in 22.7 shall not be permitted. 22.5.2 Beams and slabs over free end supports where a member is built into a masonry wall which develops NNLY partial restraint. The member shall be designed to resist a negative moment at T.E face of the support of W1/24 where W is the total design load and L is the effective span, or such other restraining moment as may be shown to be applicable. For such a condition shear coefficient given in Table 13 at the end support may be increased high 0.05. 35 is456, 2000 Type of load Table 11 Bending moment coefficients, Clause 2 2.5.1. Span moments. Near middle at middle of end span of interior span, support moments TT, at support at other next to the interior end support supports, 1, 2, L, 4, 5, dead load noting post load, fixed, plus 112 plus I16 I10 I12 imposed load, not fixed, plus 110 plus I12 1919. Note: for obtaining bending moment, the coefficient shall be multiplied by the total design load and effective span. Table 13 Shear for coefficients I clauses 2.5.1 and 2.5.2, type 01 LOAD at end support, I, 2, dead load and imposed 0.4 load, fixed, imposed load, not 0.45 fixed, at support next to the end support TT and, ter side inner side, 3, 4, 0.6 0.55 0.6 0.6 at other interior supports, 0.5 0.6. Note: for obtaining shear force, the coefficient shall be multiplied by the total design load. 22.6 Critical sections for moment and shear. 2.6.1 For monolithic construction, the moments computed at the face of the supports shall be used in the design of the members at those sections. For non-monolithic construction, the member shall be done keeping in view 22.2. 2.6.2 Critical section / or shear. The shears computed at the face of the support shall be used in the design of the member at that section except as in 2.6.2.1. 22.6.z.1 When the reaction in the direction of the applied shear introduces compression into the end region of the member, sections located at a distance less than d from the face of the support may be designed for the same shear as that computed at distance d, see Fig. 2. N, T. The above clauses are applicable for beams generally carrying uniformly distributed load where the principal load is located further than 2d, ruin the face of the support. 22.7 Redistribution of moments. Redistribution of moments may be done in accordance with January 1, 37 for limit state method and in accordance with 8-1.2 for working stress method. However, where simplified analysis using coefficients is adopted, redistribution of moments shall not be done. 23 Beams. 23.0 Effective depth. Effective depth of a beam is the distance between the centroid of the area of tension reinforcement and the maximum compression fiber, excluding the thickness of finishing material not placed monolithically with the member and the thickness of any concrete provided to allow for wear. This will not apply to deep beams. 23.1 T-beams and L-beams. 23.1.1 General. A slab which is assumed to act as a compression flange of a T-beam or L-beam shall satisfy the following: a. The slab shall be cast integrally with the web, or the web and the slab shall be effectively bonded together in any other manner, and b. If the main reinforcement of the slab is parallel to the beam, transverse reinforcement shall be provided as in Fig. 3, such reinforcement shall not be less than 60% of the main reinforcement at midspan of the slab. 3.1.2 Effective width of flange, in the absence of more accurate determination. The effective width of flange may be taquinas the following 36, 0, T is 456, 2000 D, B, Fig. 2 Typical support conomons for locating FACIORED shear force but in no case greater than the breadth of the web plus half the sum of the clear distances to the adjacent beams on either side. A. Fort beams H, equals plus B, plus 6D, equals B, for L beams, B, I12 plus BW plus 3D, C, for isolated beams, the effective flange width shall be obtained as below but in no case a greater than the actual width, T, beam B, I, O plus BJL plus 4BL beam, B equals O dot S in plus BW, L plus 4B where equals B, effective width of flange, equals in distance between points of 0 moments in the beam, B, equals breadth of the web, equals drive thickness of flange, and B equals actual width of the flange. Note, for continuous beams and frame, comma, may be assumed will be 0.7 time. The effective span 23.2 Control of deflection. The deflection of structure or part thereof shall not adversely affect the appearance or efficiency of the structure or finishes or partitions. The deflection shall generally be limited to the following: a. The final deflection due to all loads including the effects of temperature, creep, and shrinkage and measured from the as-cast level of the supports of floors, roofs and all other horizontal members, should not normally exceed span L2S0. b. The deflection including the effects of temperature, creep and shrinkage occurring after erection of partitions and the application of finishes should not normally exceed span/3S0 or 20 mm whichever is less. 3.2.1 The vertical deflection limits may generally be assumed to be satisfied provided that the span-to depth ratios are not greater than the values obtained as below. A. Basic values of span to effective depth ratios for spans up to 10 m, cantilever 7 simply supported 20 continuous 26 b, for spans above 10 m, the values in A may be multiplied by 10/span in meters, except for cantilever in which case deflection calculations should be made. C. Depending on the area and the stress of steel for tension reinforcement, the values in A or B shall be modified b multiplying with modification factor obtained as per Fig. 4. D. Depending on the area of compression reinforcement, the value of span to depth ratio be further modified by multiplying with the modification factor obtained as per Fig. S37 is 456, 2000 beam 222 XTL plus dash plus I and I, dash plus dash T section XX Fig. 3 transverse reinforcement in flange off beam when main reinforcement of slab is para E.L tuth beam E, for flanged beams, the values of A or B be modified as per Fig. 6 and the reinforcement percentage for Uzi in Fig. 4 and 5 should be based on area of section equal to BD. Note when deflections are required to be calculated, the method given in Annex C may be used. 20 \\\\\\\\\r R R 6I R R I R 10 R IRRRIF F45I F90 FU240 H290I. Note, F is steel stress of service loads in N/mm2IO040 216202228 0% tension reinforcement I 0.58 F armofsioi _shan required area of CMLL ection of steel provided flow. Formodiakajan factor for tension reinforcement 38L/V/V/100 0 to 50 001 to 52-002 to 50% compression reinforcement Fig. 0.5 muocation factor for compression return percement 18456 2001 100 EA, ESC and LZ 0.85 QT08EA, 075 1//0.700204080810 ratio of web width to flange width. Fig 6 reduction factors for RA110S of span to EJ depth for flanged beams. 23.3 slenderness limit. For beams to ensure lateral stability, a simply supported or continuous beam shall be so proportioned that the clear distance between the lateral 250 BZ restraints does not exceed 60 B of, whichever D is less, where D is the effective depth of the beam and B the breadth of the compression face midway between the lateral restraints. For a cantilever, the clear distance from the free end of the cantilever to the lateral restraint shall not exceed 25 B or _10.0 BZ, whichever is less. D24 solid slabs. 24.1 general. The provisions of 13.2 for beams apply to slabs also. NOPS 1 for slabs span in L in two directions. The shorter of the two spans should be used for calculating the span to ET effective depth ratios. 2 for 2 WAVs labs of shorter spans, up to 3 m, with mild steel reinforcement. The span to overall depth ratios given below may generally be assumed 10 satisfy vertical deflection limits for loading class up to 3 kN/mj simply supported slabs. 3's continuous slabs. 40 for high stunt defoned bar soft-summed FE41. The values given above should be multiplied by 0.8. 24.2 slabs continuous over supports. Slabs spanning in one direction and continuous over supports shall be designed according to the provisions applicable to continuous beams. 24.3 SBS monolithic with supports bending moments in slabs, except flat slabs, constructed monolithically with the supports shall be calculated by taking such slabs either as continuous over supports and 39 is 456. 2000 capable of free rotation. Or as members of a continuous framework with the supports, taking into account the stiffness of such supports. If such supports are formed due to beams which justify fixity at the support of slabs, then the effects on the supporting beam, such as the bending of the web in the transverse direction of the hewn and thetation in the longitudinal direction of the beam, wherever applicable, shall also be considered in the design of the beam. 24.3.1 For the purpose of calculation of moments in slabs in a monolithic structure, it will generally be sufficiently accurate heteroasymuth members connected to the ends of such slabs are fixed in position and direction at the ends remote from their connections with the slabs. 24.3.1 Slabs carrying concentrated load. 24.3.2.1 IFA solid slab support Eden tupositages, carries concentrated loads. The maximum bending moment caused by the concentrated loads shall be assumed to be resisted by an effective width of slab, measured parallel to the supporting edges, as follows: a. For a single concentrated load, the effective width shall be calculated in accordance with the following equation provided that it shall not exceed the actual width of the slab, BR equals kx, 1. Plus a left where equals BD effective width of slab, K equals constant having values given interval 14 depending upon the ratio of the width of the slab, / to the effective span i.e., equals x distance of the centroid of the concentrated load from nearer support, equals I effective span, and RFA equals width of the contact area of the concentrated load from nearer support measured parallel to the supported edge. And provided further that in case of a load near the unsupported edge of a slab, the effective width shall not exceed the above value nor half the above value plus the distance of T load from the unsupported edge. B. For two or more concentrated loads placed in a line in the direction of the span, the bending moment per meter width of slab shall be calculated separately for each load according to its appropriate effective width of slab calculated as in A. Above and added together for design calculations. C. For two or more loads not in a line in the direction of the span. If the effective width of slab for any load does not overlap the effective width of slab for another load, both calculated as in A. Above, then slab for each load can be designed separately. If the effective width of slab for on load overlaps the effective width of slab for an adjacent load, the overlapping portion of the slab shall be designed for the combined effect of the two loads. Table 14 values 01K for SB and PLY supported and continuous slabs, Clause 24.3.2.1, ILOR SLMPL, supported S. 0.10.20.30.40 S 0.60.70.80.91.0 and above 0.40.81.16 1.48 1.72 1.92 2.36 2.48 ILOR Code DUQ UI 51 0.40.81.16 1.44 1.68 1.84 1.96 2.08 2.16 2.24 d. For cantilever solid slabs, the effective width shall be calculated in accordance with the following equation, equals per 1.2 al plus a where equals per effective width, equals IL distance of the concentrated load from the face of the cantilever support, and equals a width.h of contact area of the concentrated load measured parallel to the supporting edge. Provided that the effective width of the cantilever slab shall not exceed 1/3 the length of the cantilever slab measured parallel to the facade edge. And provided further that when the concentrated load is placed near the extreme ends of the length of cantilever slab in the direction parallel to the fixed edge, the effective width shall not exceed the above value, nor shall it exceed half the above value plus the distance of the concentrated load from the extreme end measured in the direction parallel to the fixed edge. 24.3.2.2 For slabs other than solid slabs, the effective width shall depend on the ratio of the transverse and longitudinal flexural rigidities of the slab. Where this ratio is 1, that is, where the transverse and longitudinal flexural rigidities are approximately equal, the value of effective width as found for solid slabs may be used. But as the ratio decreases, proportionately smaller value shall be taken. 24.3.2.3 Any other recognized method of analysis for Casel of ILABA covered by 24.3%.1 and 24.3.2.2 and FOT all of that ASE8 of slabs may be used with the approve of M engineer * in charge. 24.3.2.4 The critical method for checking shear shall be given in 34.2.4.1. 24.4 Slabs spadlined 2 directions at RLLBTADII_ the slabs spanning in 2 directions at right angles and carrying S uniformly distributed load may be decilaned by any acceptable theory or by Usina coefficients liven in Annex D. For determining bending moments in slabs spanning in 2 directions at right angles and carrying co-entriered load, any accepted method approved by the engineer in charge may be adopted. Notes: the EDOI commonly used elastic methods are based on APOD, or Westerpard, theory most commonly yield limitage of COUS method is based on Johansson's yield line at theory. 14.4.1 Restrained slab with unequal conditions at adjacent pan I. In some cases the support moments calculated from Table 26 for adjacent panels may differ significantly. The following procedure may be adopted to adjust them. A. Calculate the sum of moments at midspan and I upwards, nia one-acting signs. B. Treat the values from Table 26 as fixed end MEDTs. C. According to TCJ the relative stiffness of adjacent spans, distribute the fixed end moments across the supports, leaving new support moments. D. Adjust midspan moments such that, when added to the support moments from C. Neglecting is456, 2000 signs, the total should be equal to that from A. If the resulting support moments are significantly greater than the value from Table 26, the tension steel over the supports will need to be extended further. The procedure should be as follows: 1. Take span moment as parabolic between supports, its maximum value is as found from D. 2. Determine the points of contraflexure of the new support moments from C, with the span moment from 1. 3. Extend aft the support tension steel at each end to at least an effective depth or 12 bar diameters beyond the nearest point of contraflexure. 4. Extend the full area of the support tension steel at each end to half the distance from 3. 24.5 Loads on support I-beams. The loads on beams supporting solid slabs spanning in 2 directions at right angles and supporting uniformly distributed loads, may be assumed to be in accordance with Fig. 7. 25 Compression members. 25.1 Definitions. 25.1.1 Columnar strut is a compression member, the effective length of which exceeds 3 times the least lateral dimension. 25.1.2 Short and slender compression members. A compression member may be considered as short dh when both slenderency o, I and b are less than 12. A 2116 818/07-1B load in this shaded area to be carried 8B beamy load in this shaded area to be carried by beam/flow. 7 Load carried by supporting beams. 41 is 456, 2000 where 1 equals MD equals IRY, B equals effective length in respect of the major axis, depth in respect of the major axis, effective length in respect of the minor axis, and width of the member. It shall otherwise be considered as a slender compression member, where equals b width of that cross-section, and equals d depth of the cross-section measured in the plane under consideration. 25.4 Minimum eccentricity. All columns shall be designed for a minimum eccentricity, equal to the unsupported length of column. 500 plus lateral dimensions /30, subject to a minimum 25.1.3 unsupported length of 20 rom. Where biaxial bending is considered, it is the unsupported length, I, of a compression member. Sufficient to ensure that eccentricity exceeds the shall he taken as the clear distance between end minimum about one axis at a time. Restraints except that, 26 Requirements governing a, in flat slab construction, it shall be clear distance reinforcement and detailing between the floor and the lower extremity of the capital, the drop panel or slab, whichever is 26.1 general the least. Reinforcing steel of same type and grade shall be used h, in beam and slab construction, it shall be the as main reinforcement in a structural member. Clear distance between the floor and the underside of the shallower beam framing into the columns in each direction at the next higher. However, simultaneous use of 2 different types or grades of steel for main and secondary reinforcement respectively is permissible. Floor level. 26.1.1 bars may be arranged singly or in pairs in C, in columns restrained laterally by struts. It shall be the clear distance between consecutive struts in each vertical plane, provided that to be an adequate support, 2 such struts shall contact, or in groups of 3 or 4 bars bundled in contact. Bundled bars shall be closed within stirrups or ties. Bundled bars shall be tied together to ensure the bars remaining together. Bars larger than 32 mm meet the columns at approximately the same diameter shall not be bundled. Except in columns. Level and the angle between vertical planes. 26.1.2 The recommendations for detailing for through the struts shall not vary more than 3 qt. Earthquake resistant construction given in is 13,920 from a right angle. Such struts shall be of should be taken into consideration, where applicable adequate dimensions and shall have sufficient. See also is 4,326. Anchorage to restrain the member against lateral deflection. 26.2 Development of stress in reinforcement D, in columns restrained laterally by struts or beams, with brackets used at the junction, it shall be the clear distance between the floor and the lower edge of the bracket, provided that the bracket width equals that of the beam strut and is at least half that of the column. 25.2 Effective length of compression members. In the absence of more exact analysis, the effective length of columns may be obtained as described in Annex E. The calculated tension or compression in any bar at any section shall be developed on each side of the section by an appropriate development length or end anchorage or by a combination thereof. 26.2.1 Development length of bars A. The development length L is given by D_L, 1, for FBD where 25.3 slenderness limits for columns. 25.3.1 The unsupported length between end restraints shall not exceed 60 times the least lateral dimension of a column. 25.3.2 If, in any given plane, one end of a column is unrestrained, its unsupported length, it shall not exceed Jo B2, equals nominal diameter of the bar, equals A stress and bar at the section. Consider a design load, and equals THD design bond stress given in 26.z.1.1. Notes 1. The development IKNJ include and komi vidlos of hooks in tension reinforcement. 2. For bars of sections other than cerular. The development length should be sufficient to develop the stress in the bar by bone 0 degrees, Li I.C42. is456, 2001 6.2.1.1 Design bond stress in limit state method for plain bars in tension shall be as below. Grade of concrete design bond stress SJ, FHD, N/mm2 M20 1.2 M25 1.4 M30 1.5 M35 1.7 M40 and above 1.9 for deformed bars conforming to is1786 THESE values shall be increased by 60%. For bars in compression, the values of bond stress for bars in tension shall be increased by 25%. The values of bond stress in working stress design are given in B2.1. 26.2.1.2 Bars bundled, 11 Contact. The development length of each bar of bundled bars shall be that for the individual bar, increased by 0% for 2 bars in contact, 20% for 3 bars in contact and 33% for 4 bars in contact. 26.2.2 Anchoring reinforcing bars. 26.2.2.1 Anchoring bars in tension. A. Deformed bars may be used without end anchorages provided development length requirement is satisfied. Hooks should normally be provided for plain bars in tension. B. Bends and hooks. Bends and hooks shall conform to is 2502 J. Bends. The anchorage value of bend shall be taken as 4 times the diameter of the bar for each 45 tons bend subject to a maximum of 16 times the diameter of the bar. 2. Hooks. The anchorage value of a standard U-type hook shall be equal to J6 times the diameter of the bar. 26.2.2.2 Anchoring bars in compression. The anchorage length of straight bar in compression shall be equal to the development length of bars in compression as specified in 26.21. The projected length of hooks, bends and straight lengths beyond bends if provided for a bar in compression, shall only be considered for development length. 16.2.2.3 Mechanical devices or anchorage. Any mechanical or other device capable of developing the strength of the bar without damage to concrete may be used as anchorage with the approval of the engineering charge. 26.2.2.4 Anchoring shear reinforcement. A. Inclined bars. The development length shall be as for bars in tension. This length shall be measured as under 1. In tension zone, from the end of the sloping of inclined portion of the bar, and 2. In the compression zone, front the mid-depth of the beam. B. Stirrups. Notwithstanding any of the provisions of this standard, in case of secondary reinforcement, such as stirrups and transverse ties, complete development lengths and anchorage shall be deemed to have been provided when the bar is bent through an angle of at least 90 round a bar of at least its own diameter and is continued beyond the end of the curve for a length of at least 8 diameters, or when the bar is bent through an angle of 1350 and is continued beyond the end of the curve. For a length of at least 6 bar diameters, or when the bar is bent through an angle of 1 degree and is continued beyond the end of the curve for a length of at least 4 bar diameters. 26.2.2.5 Bearing stresses at bends. The hearing stress in concrete for bends and hooks described in is 2502 need not be checked. The bearing stress since idea bend in any other bend shall be calculated as given below, equals bearing stress FHTREI where /OL equals, tensile force due to design loads in a bar or group of halves, equals internal radius of the bend, and cent equals size of the bar or, in bundle, the size of har of equivalent area. For limit scale method of design, this stress shall not exceed I.5 FKW tier R plus. K is the Charactin.S.UC cube 1 plus 2/AC strength of concrete and A, for a particular bar or group of hars in contact shall he taken as the center to center distance between bars or groups of bars perpendicular to the plane of the bend, for a bar of group of bars adjacent to the face of the member A shall he taken as the cover plus size of bar, Q. For working stress method of design, the bearing stress shall not exceed dash J plus 2C/J/A 26.2.2.6 If a change in direction of tension or compression reinforcement induces a resultant force acting outward tending to split the concrete, such force is 456, 2000 should be taken up by additional linka or stirrups. Bent tension bar at a reentrant angle should be avoided. 26.2.3 Curtailment 01 rel, on R, N force, T ill, flexural member, M, asterisk, of Loyaltalche of tile section 26.2.3.1 for curtailment. Reinforcement. Bail LTED, il nil fork. A. End adabi equo d beyond the point at which it is no longer required to resist flexure for a distance equal to the effective depth of the member or 12 times Heber diameter, whichever is greater except at simple supporter end off cantle ever. In addition to 6.2.3.2 to 26.2.3.5. Hall also satisfied. NOTEA point at which reinforcement I-80 loft required to resist flexure is where the resistance momento flow height 1 ECTI 0 LL, considering only the continuum L ban, is equal to the depth moment. TTLV equals low equals to tot 0.871 in TBIC of Lee J Pit S8 Disip and though penny Ibel. J in the case of working stroll Dielft, shear force at the section due to the zip loads, sum of the encourage beyond the center of the support and the equivalent to 6.1.3.2 flexural reinforcement shall not be tenonated in a tension zone unless any one of the following conditions is satisfied. A. The shear at the cut-off point does not exceed 2/3 that permitted, including L the shear strength of web reinforcement provided. B. Stirrup area in excess of that required for shear and torsion is provided along each 10L nated bar over a distance from the cutoff point equal pj1 or all a value of any hook or mnan ge at simple support, a tant hay tapia kidn vol at the old pluthu orf at gebr ism li 1 mli tep j12, whichever is pater, and, equals diameter of bar. The value of m/vent the above expression may be increased add by 30% when the ends of the reinforcement are, ojj by a compressive reaction. To 3/4 the effective depth of the 26.2.3.4 and gative moment, and force-renant member. The excess Steinup area shall be not less than 0.4 bil where b is the breadth of beam. S is the spacing and, is the characteristic strength of reinforce CMC and T in N/mm2 the resulting spacing shall not exceed this pit where pH is the ratio of the area of band cutoff to the total area of bars at the section, and D is the at least 1/3 of the J in fork and T provided for napa VJIJO if 8 tit ild flupajate spall extend beyond mom asterisk the point of IFB jodo for it for J stani not less than the effective depth of flow of 12, or on a 16th of the clear span which of I. 8F8 star 26.2.3.5 Kurta. Off bu nii.d bar, effective depth. Bars in a bundle shall terminate at different points C, 436 Riemanns Malur bars the continuing bars spaced apart by note LISTHAN 40 TIMES the diameter provide double the area required for flexure at except for bundles I toppin. At a support. The cutoff point and the shear does not exceed 26.1.4 special ember. 3/4 that permitted. 16.1.3.3 positive moment reinforcement adequate in Doncorolo shall be provided for 10 reinforcement in flexural membrane where rho and fajajo at least 1/3 the positive moment MCNT stress is not directly proportional to MOMELTL, reinforcement in simple members and one such as sloped, tept, or tapered footin. Brackets, 4th the positive moment reinforcement in deep beams, and members in which the tension continuous members shall extend along the same reinforcement is not parallel to the comprol.ion fico. Face of the member into the support to a length equal to LD/3. B. When a flexural member is part of the primary lateral load resisting system, the positive reinforcement required to be extended into the support as described in A. Shall be anchored to develop its design stress in tension at the face of the support. C. At simple supports and at points of inflection, positive moment tension reinforcement shall be limited to a diameter such that J by 26.2.1 does not exceed LD computed for 26%.5 R in Forkelman splicing, where splices are provided in the reinforce an L band. They shall UF81 possible away from the EQ on L of maximum itra S and beltagerd. It in commendad that splices in flexural membrane EALD OLBF at sections where the bend in L moment I more than 0% of the moment of resistance, and no Monday chan half bars shall be spliced at a section. Where more than one balf of the band are spliced at a section or Iberi splices are mad. It point of maximum stress, special precaution. Shall bo econ, 44 is 456 such as increasing the length of lapan/Oracelln spirals or closely spaced stirrups around the length of the splice. U.L lap plie, lap splices hall not used for bars larger than 36 rom, for larger diameters, bars may be welded, see 12.4, in cases where welding is not practicable, lapping of bars larger than 36 mm may be permitted, in which case additional spirals should be provided around the lapped bars. B. Lap splices shall be considered as staggered if the center-to-center distance of the splices is not less than 1.3 times the lap length calculated as described in E. C. Lap length including anchorage value of hooks for bars in flexural tension shall be LD set to 6.2.1, or 30, whichever is greater, and for direct tension shall be 2 LD or 30 whichever is greater. The straight length of the lap shall not be less than is, or 200 mm. The following provisions shall also apply, where lap occurs for a tension bar located at I. top of a section 8S cast and the minimum cover is less than twice the diameter of the lapped bar. The lap length shall be increased by a factor of 1.4. 2. Comer of a section and the minimum cover to either face is less than twice the diameter of the lapped bar, or where the clear distance between adjacent laps is less than 7 mm or 6 times the diameter of lapped bar. Whichever is greater, the lap length should be increased by a factor of 0.4. Where both condition 1 and 2 apply, the lap length should be increased by a factor of 2.0. Note: splices IA tension members shall be enclosed in spirals made of bond no less than 6 mm diameter with pitch not no than 100 mm d. The lap length in compression shan be equal to the development length in compression, calculated as described in point 1.1. But not less than 24. E. When bars of two different diameters are to be spliced, the lap legth shall be calculated on the basis of diameter of the smaller bar. T. When splicing of welded wire fabric is to be carried out, lap splices of wires shall be made so that overlap measured between the extreme cross wires shall be not less than the spacing of cross wires plus 100 mm, in case of B end lot bars, lap splices of L1 DTCD band shall be made by splicing one bar at a time. Such individual splices within a bundle shall be staggered. 16.1.5.2 Strength O/welds. The following values may be used where the strength of the WE1D has been proved by tests to be at least as great $1D1 of the parent bar. A. Splices in compression, for welded splices and mechanical connection, 100% of the deci strength of joint bars. B. Splices in tension I, 80% of the design strength of welded bars, 100% if welding is strictly supervised and if at any cross, section of the member not more than 20% of the tensile reinf, L alternate is welded. 2, \00 PCFNT of design strength of mechanical connection. 16.2.5.3 End bearing splices. End hearing splices shall be used only for bars in compression. The ends of the bars shall be square cut and concentric bearing ensured by suitable devices. 16.3 Space an L of Rolnloriana and 26.3.1 For the purpose of this ISE the diameter of a N011 / round bar shall be its diamodo, and in the case of bars WHRO no, round, or in the case of deformed bars or crimped though diameter shall be taken as the L at F of A if Cli. Ivan J an equivalent effective VE arcs. Wiro Ipassin. Limitations and minimum COQFOTC cover, IZ6A. Are boot on bar diameter. A group of band bundled in contact shall be treated as a Linslow bar of diameter derived from the total key y_nl arrow. J6.3.1 Minimum distance between individual bars. The following shall apply for pass nl of ban. A. The horizontal distance between two parallel main reinforce nl bars shall usually be not less than thol rito, of tho fo yo wina, I, ll diameter of tho bar if the diameter re4 l alt 2, th diameter of the lurler bar if the diamal crs are unequal. And 3. S111 m more than the nominal maximum size of p_iplalo. OTB This does not preclude the use or pair size of d.I. It'll beyond the conceded reinforcement in the lame member, lhi eyes of, relates nabi najuoical ground concluded reinforcement tq comply with thil provision. B. Greater horizontal distance than the minimum specified in, A, should be prov. Wherever possible. However, when needle vibrators arrow 45 is 456, 2000 used, the horizontal distance between bars of a group may be reduced to 2/3 the nominal maximum size of the course aggregate, provided that sufficient space is left between groups of bars to enable the vibrator to be immersed. C. Where there are 2 or more rows of bars, the bars shall be vertically in line and the minimum vertical distance between the bars shall be 15 mrn, 2/3 the nominal maximum size of aggregate or the maximum size of bars, whichever is greater. 26.3.3 Maxi/none, distance between bars in tension unless the calculation of crack widths shows that a greater spacing is acceptable. The following rules shall be applied to flexural members in normal internal or external conditions of exposure. A. Beams, the horizontal distance between parallel reinforcement bars, or groups, the tension face of a beam shall not be greater than the value given in Table 15 depending on the amount of redistribution carried out in analysis and the characteristic strength of the reinforcement. B. Slabs 1. The horizontal distance between parallel main reinforcement bars shall not be more than 3 times the effective depth of solid slab or 300 in Ti, whichever is smaller. 26.4 Nominal cover to reinforcement. 26.4.1 Nominal cover. Nominal cover is the design depth of concrete cover to all steel reinforcements, including links. It is the dimension used in design and indicated in the drawings. It shall be not less than the diameter of the bar. 26.4.2 Nominal cover to meet durability requirement. Minimum values for the nominal cover of normal weight aggregate concrete which should be provided to all reinforcement, including links depending on the condition of exposure described in 8.2.3 shall be as given in Table 16. 26.4.2.1 However, for a longitudinal reinforcing bar in a column, nominal cover shall in any case not be less than 40 mm, or less than the diameter of such bar. In the case of columns of minimum dimension of 200 mm or under whose reinforcing bars do not exceed 12 mm, a nominal cover of 25 mm may be used. 26.4.2.2 For footings, minimum cover shall be 50 mm. 26.4.3 Nominal cover to meet specified period of fire resistance. Minimum values of nominal cover of normal weight aggregate concrete to be provided to all reinforcement including links to meet specified period of fire resistance shall be given in Table 16a. 26.5 Requirements of reinforcement for structural members. 2. The horizontal distance between parallel reinforcement bars provided against shrinkage and temperature shall not be more than 5 times the effective depth of a solid slab or 450 mm, whichever is smaller. 26.5.1 Beams. 26.5.1.1 Tension reinforcement. A. Minimum reinforcement. The minimum area of tension reinforcement shall be not less than that. Table 15 Clear distance between bars. T taught is 26.3.3, F. Percentage redistribution to or from section considered -10 to 15 0 plus I. Clear distance between ban nijnl and 2 non mm 2, 215 260 300 300 415 12 15 180 210 500 105 130 150 17s plus 30 mm 300 235 195 n, te, the spacings given in the table are not applicable to members subjected to particularly aggressive environments unless in the calculation of the moment of resistance, I, has been limited to 300 N/mm2 in limit start design on daily I limited to 16 N/mm2 in workin, stress design. 46 is 456, 2000 Table 16 Nominal cover to meet durability requirements I Clause 2 6.4.2, exposure mild moderate severe very severe extreme nominal concrete cover in not less than 20 30 45 50 75 Notes 1 for main reinforcement up to 121 Nel diameter bar for NLJD exposure the nominal cover may be reduced by 5 mm to unless specified otherwise. Actual concrete cover should not deviate from the required nominal cover by and I 0 mm 03 for exposure condition severe and very severe. Reduction of 5 mm INF Leahy made. Where a concrete grade is M35 and above. Fire resistance table 16 a nominal cover to meet specified period of fire resistance I clauses 21.4 and 26.4.3 and Fig. I. Nominal cover beam slabs ribs columns simply supported HMMO.S20 continuous MM20 simply supported non-20 continuous RN 20 simply supported MM20 continuous min MM20 40 I20 20 20 20 20 20 40 1.5 22 360 20 25 20 30 U25 4s 45. LL 5s 20 40 J.1 40 45 44 70 50 55 45 65 55 40 Notes 1 The nominal covers live and relate specific lito the minimum member dimensions given in Fig. I2 cases that lie below B bold line require attention to the additional measures necessary to reduce the risks of spalling is C2 1.3.1. Given by the following, 26.5.1.3 side face reinforcement equals 0.85 BD phi where equals a minimum area of tension reinforcement, equals B breadth of beam or the breadth of the web of F beam, equals D effective depth, and equals F, characteristic strength of reinforcement in N/mm2B, maximum reinfo the maximum area of tension reinforcement shall not exceed 0.04 BD. 26.5.1.2 Compression reinforcement the maximum area of compression reinforcement shall not exceed 0.04 BD. Compression reinforcement in beams shall be enclosed by stirrups for effective lateral restraint. The arrangement of stirrups shall be as specified in 26.5.3.2. Where the depth of the web in a beam exceeds 750 mm, side face reinforcement shall be provided along two faces. The total area of such reinforcement shall be not less than 0.1% of the web area and shall be distributed equally on two faces at a spacing not exceeding 300/111 m or web thickness whichever is less. 26.5.1.4 Transverse reinforcement in beam S4 shear and torsion the transverse reinforcement in beams shall be taken around the outermost tension and compression bars. In T-beams and F-beams, such reinforcement shall pass around longitudinal bars located close to the outer face of the flange. 26.5.1.5 Maximum spacing of shear reinforcement the maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.75 d for vertical stirrups and d for inclined stirrups at 45 where d is the effective depth of the section 47.15456:2000 under consideration. 1 foot no case shall the space in L exceed 300 mm to 6.5.1.6 minim. Darian/or NNT minimum shear reinforcement in the form of Steinups shall be provided such that, 26.5.2 slab, the rules liven in 36.1.21 and ZU.2.2 shall apply to slabs in addition to those TWN in the appropriate clauses. 25.1.11 minimum in Horseam where AI. Total cross-sectional area of stirrup effective in shear. Stirrup espace in L though IEFTATH of the member. B equals breadth of the beam or breadth of the web of fan-led beam. And I, characteristic itra DLTB of the stirrup reinforcement in N/mm2 which shall not be taken pater dian 415 N/mm2 where the maximum shear stress calculated illels than half the permissible value and in membrane of minor structural importance such U lintels. This provision need not be complied with. Z6.5.1.7 Distributial aftersto Teinfall CNL when a member is desilane for Tonian, 41 or 8 to 6, Tonian reinforcement shall be provided below. A. The transverse reinforcement for Tonian shall be rectangular closed stirrups placed perpendicular to the WS of the member. The space L of the stirrup shall not exceed the ligature of end. I and 300 mm, Uli.ii are respectively the short and Linnell dimension of the LDI map. The mildil reinforce meet 3 lithertly actidlil tatal shall not below thin 0 is FTT. RO/8L cross sectional. HO. Tilt WIUE Canberradus to 0.12 pin ILT hen bias B strength deformed bars or welded wire fabric are used. 26.5.12 mm dgmtr thediameter of reinforcing bonaball boat ode 4.a.b est of the total thick blue of 1 m 26.5.3 kernel 26.5.11 reinforcement I, the cross-sectional area of longitudinal arrow. Reinforcement shall be not less than 0.8 pi if nor more than 6% of the sectional area of the column. NOTB of 6. Nymph. May.voiprl decade fetel cultile in plodnel dibpate cdd. Of, hence 10. Pers mii asterisk inea menkeld. When m and the col underscore below have to be \fmc in the column utter eode li. Pelton ta of steel oli, dolex 4 pers. B. In any column that basa I uja cross-sectional area than that required to support the load the minimum perk enta e of steel hall be boot upon the area of concrete reculnal to resist the direct stress and upon the actual area. C. The minimum number of lockil /clftil band provided in column ibil before in rectangular columns and 6il circular columns. B. Longitudinal reinforcement shall be placed. Close ASIS practicable to the cornon oft bicro. Section and in all casia, there shall be at least one longitudinal bar in each com. Of the teal. When the cross-sectional dimension of the member exceeds 450 mm, additional longitudinal bars. Shall be provided to satisfy the requirement of minimum reinforcement and space NL given in 26.5.1.3. 26.5.1.8 Reinforcement in ONLOS of TNL beams shall satisfy the requirements in 23.1.1, b. Where RTL adls into EOD, part of the main tension reinforcement shall be distributed over the effective flannel width or width equal to 1/10 of the span whichever is smaller. If the effective flannel width exceeds 1/10 of the span, nominal longitudinal reinforcement shall be provided in the outer portions of the flap. D. The bars shall not be less than 12 mm in diameter. E. A reinforced concrete column having L helical reinforcement shall have at Ludwig span of longitudinal reinforcement within the helical reinforcement. F. In a helically _fmead column. The longitudinal bars shall be in contact with the helical reinforcement and equidistant around its inner circumference. S. Spacina of longitudinal bars mu erdl the periphery of the column shall not exceed 300 mm h, in case of pedestal in which the longitudinal reinforcement is. Take d in account in strength calculations, nomina longitudinal reinforcement not less than 0.15% off the cross-sectional area shall be provided. 48 is 456, 2000 Note, pedestal is a Compruian member. The effective length of which does not exceed 3 times the least lateral dimension. 26.5.3.2 Transverse reinforcement A. General A reinforced concrete compression member shall have transverse or helical reinforcement so disposed that every longitudinal bar nearest to the compression face has effective lateral support against buckling subject to provisions in B. The effective lateral support is given by transverse reinforcement either in the form of circular rings capable of taking up circumferential tension or by polygonal links, lateral ties, with internal angles not exceeding 13.50. The ends of the transverse reinforcement shall be properly anchored. See 26.2.2.4, b. B. Arrangement of transverse reinforcement 1. if the longitudinal bars are not spaced more than 75 mm on either side. Transverse reinforcement need only to go round corner and alternate bars for the purpose of providing effective lateral supports, set Fig 8. 2. If the longitudinal bars spaced at a distance of not exceeding 48 times the diameter of the tie are effectively tied in two directions. Additional longitudinal bars in between these bars need to be tied in one direction be open ties, see Fig 9. 3. Where the longitudinal reinforcing bars in a compression member are placed in more than one arrow, effective lateral support to the longitudinal bars in the inner rows may be assumed to have been provided if I. Transverse reinforcement is provided for the outermost row in accordance with 26.5.3.2, and 2. No bar of the inner row is closer to the nearest compression face than 3 times the diameter of the largest bar in the inner row, see Fig 10. 4. Where the longitudinal bars in a compression member are grouped, not in contact, and each group adequately tied with transverse reinforcement in accordance with 26.5.3.2, the transverse reinforcement for the compression member as a whole may be provided on the assumption that a group is a single longitudinal bar for purpose of determining the pitch and diameter of the transverse reinforcement in accordance with 26.5.3.2. The diameter of such transverse reinforcement need not, however, exceed 20 mm, see Fig 11. C. Pitch and diameter of LoRa, tits J. Pitch. The pitch of transverse reinforcement shall be not more than the least of the following distances, I. The least lateral dimension of the compression members, 2. 16 times the smallest diameter of the longitudinal reinforcement bar to be tied, and 3. 300 mm 2. Diameter. The diameter of the polygonal links or lateral tees hall be not less than 1/4 of the diameter of the largest longitudinal bar, and in no case less than 16 mm d. Helical reinforcement 1. Pitch. Helical reinforcement shall be of regular formation with turns off the helix spaced evenly and its ends shall be ensured properly by providing 1½ extra turns of the spiral bar. Where an increased load on the column on the strength of the helical reinforcement is allowed for, the pitch of helical turns shall be not more than 75 mm, nor more than 1/6 of the diameter of the column, nor less than 2.5 mm, nor less than 3 times the diameter of the steel bar forming the helix. In other cases, the requirements of 26.5.3.2 shall be complied with. 2. The diameter of the helical reinforcement shall be in accordance with 26.5.3.2, c. 2. 26.5.3.3 in columns where longitudinal bars are offset at a splice. The slope of the inclined portion of the bar with the axis of the column shall not exceed 1/6. And the portions of the bar above and below the offset shall be parallel to the axis of the column. Adequate horizontal support at the offset bends shall be treated as a matter of design, and shall be provided by metal ties, spirals, or parts of the floor construction. Metal ties or spirals so designed shall be placed near, not more than 8 bar diameters from, the point of bend. The horizontal thrust to be resisted shall be assumed of as 1½ times the horizontal components the nominal stress in the inclined portion of the bar. Offset bars shall be bent before a thea are placed in the forms, where column faces are offset 75 or more. Splices of vertical bars adjacent to the set face shall be made by separate dowels overlapped as specified in 26.2.5.1. 2116 bis/07-849 is 456, 2027 expansion joints 27.1 structures in which marked changes in plan dimensions take place abruptly shall be provided with expansion on joints at the section where such changes occur. Expansion joints shall be so provided that the necessary movement occurs with a minimum resistance at the joint. The structures adjacent to the joint should preferably be supported on separate columns or walls but not necessarily on separate foundations. Reinforcement shall not extend across an expansion joint and the break between these sections shall be complete. 27.2 The details as to the length of a structure where expansion joints have to be provided can be determined after taking into consideration various factors, such as temperature, exposure to weather, The time and season oft healing oft concrete, etc. Normally structures exceeding 45 m in length are designed with one or more expansion joints. However, in view of the large number of factors involved in deciding the location, spacing and nature of expansion joints, the provision of expansion joint in reinforced cement concrete structures should be left to the discretion of the designer. is414 gives the design considerations. WJDIC need to be examined and provided for. AL dimensions in millimeters. Flow 8. 1 / AL dimensions in millimeters. Fig 10 AL dimensions in millimetra. Flow 9. Transverse reinforcement individual groups FRG 1150 is 456. 2000 Section 4 Special Design Requirements for Structural Members and Systems 28 Concrete Corbels 28.2.4 Resistance CETO Applied Horizontal Force 28.1 General A corbel is a short cantilever projection which supports a load-bearing member and where a. the distance AV between the line of the reaction to the supported load and the root of the corbel is less than d, the effective depth of the root of the corbel, and b. the depth at the outer edge of the contact area of the supported load is not less than 1/2 of the depth at the root of the corbel. The depth of the corbel at the face of the support is determined in accordance with May 1, 40. 28.2 Design 28.2.1 Simplifying assumptions. The concrete and reinforcement may be assumed to act as elements of a simple strut and tie system, with the following guidelines. A. The magnitude of the resistance provided to horizontal force should be not less than 1/2 of the design vertical load on the corbel, see also 28.2.4. B. Compatibility of strains between the strut and tie at the corbel foot should be ensured. It should be noted that the horizontal link requirement described in 28.2.3 will ensure satisfactory serviceability performance. 28.2.2 Reinforcement anchorage at the front face of the corbel. The reinforcement should be anchored either by a. welding to a transverse bar of equal strength. In this case, the hearing area of the load should stop short of the face of the support by a distance equal to the cover of the tie reinforcement, or b. bending buck the bars to form a loop. In this case, the bearing area of the load should not project beyond the straight portion of the bars forming the main tension reinforcement. 18.1.3 Shear reinforcement. Shear reinforcement should be provided in the form of horizontal links distributed in the upper 2/3 of the effective depth of root of the corbel. This reinforcement should be not less than 1/2 of the area of the main tension reinforcement and should be adequately anchored. Additional reinforcement connected to the supported member should be provided to transmit this force in its entirety. 29 Deep beams. 29.1 General A beam shall be deemed to be a deep beam when the ratio of effective span to overall depth is less than 1, 2.0 for a simply supported beam, and 2, 2.5 for a continuous beam. B. A deep beam complying with the requirements of 29.2 and 29.3 shall be deemed to satisfy the provisions for shear. 29.2 Lever arm. The lever arm Z for a deep beam shall be determined a below, a. For simply supported buttes, Z equals 0.2, I plus 2D, or when I, 2D Z equals 0.61 when I L, 1B, for continuous beams. Equals Z 0.2, I plus 1.5D, or I when 1S, 2.5D Z equals 0.5 I slash when D1 where slash is the effective span taken as center to center distance between supports or 1.15 times the clear span, whichever is smaller, and D is the overall depth. 19.3 Reinforcement to 9.3.1 Positive reinforcement. The tensile reinforcement required to resist positive bending moment in any span of a deep beam shall, a. extend without curtailment. R1T between supports, b. be embedded beyond the face of each support, so that at the face of the support it shall have a development length not less than 0.8 ltj, where Lj is the development length, see 26.2.1. For the design stress in the reinforcement, and 51 is 456, 2000 c, be placed within a zone of depth equal to 0.25 d, 0.0 I adjacent to the tension face of the beam where D is the overall depth and I is the effective span to 9.3.2 negative reinforcement A, termination of reinforcement, poor tensile reinforcement required to resist negative bending moment over a support of a deep beam. 1. It shall be permissible to tenonate not more than half of the reinforcement at a distance of OD from the face of the support where D is as defined in 29.2, and 2. The remainder shall extend over the full span B, distribution when ratio of clear span to overall depth is in the range 1.0 to 2.5. Tensile reinforcement over a support of a deep beam shall be placed in two zones comprising, 1. A zone off depth 0.2 D. Adjacent to the tension face, which shall contain a proportion of the tension steel given by OS, O.S, where 2 equals I clear span and equals D overall depth. A zone measuring 0.3 D on either side of the mid-depth of the beam, which shall contain the remainder of the tension steel, evenly distributed. For span-to-depth ratios less than unity, the steel shall be evenly distributed over a depth of 0.8 D measured from the tension face. To 9.3.3 vertical reinforcement 1L1 if forces are applied to a deep beam in such a way that hanging action is required. Bar suspension steel NPS shall be provided to carry all the forces concerned. 19.3.4 Side face reinforcement shall comply with requirements of minimum reinforcement of walls, STE 32.4. 30 ribbed hollow block or kitted slab 30.1 General. This covers the slabs constructed in one of the ways described below, a. As area soft concrete ribs with top in L cast-in forms which may be removed after the concreto has set, b. As a series of concrete ribs between precast blocks which remain part of the completed admixture. The top of the ribs may be connected by a two-pin loft concrete of the same strength as that used in the ribs, and c. With a continuous top and bottom face but containing voids of rectangular, oval or other shape. 30.2 Analysis or structure. The moments and forces due to Dizian loads on continuous slabs may be obtained by the methods given in section 3 for solid slabs. Alternatively, the slab may be designed as a series of simply supported spans provided they are not exposed to weather or corrosive conditions. Wide cracks may develop at the supports and the engineer shall satisfy himself that these will not impair finishes or lead to corrosion of the reinforcement. 30.3 Shear. Where hollow blocks are used, for the purpose of calculating shear stress, the rib width may be increased to take account of the wand thickness of the block on any side of the rib, with narrow precast units. The width of the jointing mortar or concrete may be included. 30.4 Deflection. Their commendations for deflection in respect of solid slabs may be applied to ribbed hollow block or voided construction. The span to effective depth ratios given in 23.2 for a flanged beam are applicable but when calculating the final reduction factor for web width. The rib width for hollow block slabs may be assumed to include the walls of the blocks on both sides of the rib. For voided slabs and slabs constructed of box or I-section units, an effective rib width shall be calculated assuming all material below the upper flange of the unit be concentrated in a retinol or rib having the same cross-sectional area and depth. 30.5 Size and Poland off rib. In situ ribs shall be not less than 65 mm wide. They shall be spaced at centers not greater than 1 apart and their depth, excluding any topping, shall be not more than 4 times their width. Generally ribs shall be formed allens each edge parallel to the span of one-way slabs. When the edge is built into a wall or rests on a beam, a rib at least as wide as the bearing shall be formed allens the eddy 30.6 Hollow blocks and foremen blocks and fawners may be of any suitable material. Hollow clay tiles for the filler type shall conform to is 39.1, Part I. When required to contribute to the is456, 2000 structural strength of a slab they shall, a. be made of concrete or burnt clay, and b. have a cruise-hinge strength of at least 14 N/mm2 measured on thinnet section when axially loaded in the direction of compressive stress in the slab. 30 Aradum dt of reinforcement. The recommendations liven in 26.3 Resardinel maximum distance between bars apply to erase off solid concrete in this phone off construction. The curtailment. Anchorage and cover to reinforcement shall be as described below. A. At least so % of the total main reinforcement shall be carried through at the bottom onto the baronel and anchored in accordance with 36.2.3.3. B. Where a slab. Which is continuous over supports, has been designed as simply supported, reinforcement shall be provided over the support to control cracking. This reinforcement shall have a cross-sectional area of not less than 1/4 that required in the middle of the adjoining spans and shall extend at least 1/10 of the clear span into adjoining spans. C. In slabs with penanent blocks, the side cover to the reinforcement shall not be less than 10 mm. In all other cases, cover shall be provided according to 26.4. 30.8 Precuts joists and Hoyoyo filler blocks. The construction with precast joists and hollow concrete filler blocks shall conform to is 6061, Part 1, and precast joist and hollow clay filler blocks shall conform to is 6061, Part 2. 31 Flat slabs. 31.1 General. The term flat slab means a reinforced concrete slab with or without drops. Supported generally without beams. By columns with or without flared column heads, see Fig 12. A flat slab may be solid slab or may have recesses phonetin. The soffit o that soffit comprises a series of ribs in two directions. The recesses may be phoned by removable or permanent filler blocks. 3.1.1 For the purpose of this clause, the following definitions shall apply. A. Column strip. Column strip means a design strip having a width of 0.2 s2, but not greater than 0.25 I on each side of the column centerline, where I is the span in the direction moments are being determined, measured center to center of supports, and 2 is the span transverse toll measured center to center of supports. B. Middle strip. Middle strip means a decision strip bounded on each of its opposite sides by the column strip. C. Panel. Panel means that part of a slab bounded on each of its four sides by the center line of a column or center lines of adjacent spans. 31.2 Purport Law Nel 31.2.1 Thickness of flat slab. The thickness of the flat slab shall be generally controlled by considerations of span to effective depth ratios given in 23.2. For slabs with drops conforming to 31.2.2. Span to effective depth ratios liven in 23.2 shall be applied directly, otherwise the span to effective depth ratios obtained in accordance with provisions in 23.2 shall be multiplied by 0.9. For this purpose, the longer span shall be considered. The minimum thickness of slab shall be 12 mm. 31.2.2 Drop. The drops when provided shall be rectangular in plan, and have a length in each direction not less than 1/3 of the panel length in that direction. For exterior panels, the width of drops at right angles to the non-continuous edge and measured from the center line of the columns shall be equal to 1/2 the width of drop for interior panels. 31.2.3 Column heads. Where column heads are provided, that portion of a column head which lies within the largest right circular cone or pyramid that is a vertex on leaf 90° and can be included entirely within the outlines of the column and the column head, shall be considered for design purposes, STT Fig. Point 12. 31.3 Determinatio d of Bendinel moment. 31.3.1 Methods 01 Analysis and design. It shall be permissible to design the slab system by one of the following methods. A. The direct design method as specified in 31.4. And B. The equivalent frame method as specified in 31.5. In each case the applicable limitations given in 31.4 and 31.s shall be met. 31.3.2 Bend number ng moments in panels with marginal beams or walls where slab is supported by a marginal beam with a depth greater than 1.5 times the thickness of the slab, or by a wall, then S3 is 456, 2000, R critical section or sure immediately adjacent to column 1 to a slab with our drop and column without column head critical section for shear 12B slab with drop and column with column head // I. Any CO and chloride in this area to be neglected in the calculations. 12C slab without drop column with column head. Note, D is the diameter of column or column head to be considered for deci, and DIA effective depth of alab or drop to IA propryl flow. 12C RJ11CALSEC110NS for shear in flat slabs. A. The total load to be carried by the beam or wall shall comprise those loads directly on the wall or beam plus a uniformly distributed load equal to 1/4 of the total at the slab. And B. The bending moments on the half column strip adjacent to the beam or wall shall be 1/4 of the bending moments for the FLLST interior column strip. 1.3.3 Transfer of bending moments to columns when unbalanced gravity load, wind, earthquake, or other lateral loads cause a transfer of bending moment between slab and column. The flexural stresses shall be investigated using a fraction, a oft moment given by 1 AL plus AJ3 Fa, where equals a overall dimension of tile critical section for shear in the direction in which moment acts, and A2 equals overall dimension of the critical section for shear transverse to the direction in which moment acts. A slab width between -θ1 and done half slab or drop panel thickness, 1.5 d, on each side of the column or capital may be considered effective, d being the size of the column. Concentration of reinforcement over column head by closer spacing or additional reinforcement may be used to resist moment on this section. 31.4 Delrete Dest P method. 31.4.1 Limitation slab system designed by direct design method shall fulfill the following conditions. A. There shall be minimum of 3 continuous spans in each direction. B. The panels shall be rectangular, and the ratio of the longer span to the shorter span within a panel shall not be greater than 2.0. C. It shall be permissible to offset columns to a maximum of 10% of the span in the direction of the offset notwithstanding the provision in B. D. The successive span lengths in each direction shall not differ by more than 1/3 of the longer span. The end spans may be shorter but not longer than the interior spans, and is456. ZOOE, the desist live load shall not exceed 3 times the design dead load. 31.4.2 Total design moment / aura span. 31.4.11 In the direct desip method, the total design moment for a span shall be determined for a strip bounded laterally by the center line of the pane, on each side of the center line of the supports. 31.4.2.2 The absolute sum of the positive and negative bendina momenta in each direction shall be taken mo when 8 where equals m total moment, equals w design load on an area 2. In equals clear span extending from face to face of columns, capitals, brackets, or walls, but I equals not less than 0.651, length of span in the direction of mo, and 2 equals length of span transverse to R. 31.4.2.3 Circular supports shall be treated as square support shaving the same area. 31.4.Z.4 When the transverse span of the panels on either side of the center line of supports varies, 12 shall be taken as the average E of the transverse spans. 31.4.Z.5 When the span adjacent and parallel tone edge is being considered, the distance from the edge to the center line of the panel shall be substituted for LZ in 31.4.2.2. 31.4.3 Negative and positive design moments. 31.4.3.1 The negative deci-bn moment shall be located at the face of rectangular supports, circular supports being treated as square supports having the same area. 31.4.3.2 In an interior span, the total design moment mu shall be distributed in the following proportions: negative design moment 0.65, positive design moment 0.35. 31.4.3.3 In an end span, the total design moment m shall be distributed in the following proportions: interior negative design moment 0.7s_O.L1 plus at positive design moment 0.630.21 plus AC exterior negative design moment -0.6s1 plus AC is the ratio of flexural stiffness of the exterior columns to the flexural stiffness of the slab. At a joint taken in the direction moments are being determined and is livened by AE equals EKXA where equals S, sum of the flexural stiffness of the columns meeting at their joint, and K equals flexural stiffness of the slab, expressed as moment per unit rotation. 3.1.4.3.4 It shall be permissible to modify these design moments by up to 10%. So 10 nlas the total design moment, m, for the panel in the direction considered is not less than that required by 3.1.4.1.1. 3.1.4.3.5 The negative moment section shall be designed towards ist IB1 JCR of Thetwy interior negative design moments determined for Thes bench framing into a common support unless an analysis is made to distribute the unbalanced moment in accordance with the stiffness of the adjoining parts. 3.1.4.4 Distribution of bending MO,Ts across the panel with bending moments at critical cross-section shall be distributed to the column strips and middle strips as specified in 31.5.5 as applicable. 3.1.4.5 Moments in columns 3.1.4.5.1 Columns built integrally with slab system shall be designated to resist moments arising from loads on the slab system. 3.1.4.5.1 At an interior support, the supporting and members above below the slab shall be designed to resist them given by the following equation, in direct proportion to their stiffnesses unless a general analysis is made, m equals O.os, WD plus O.sw, 111, 1 Wi, I1 plus Al, where equals way Wi design dead and live loads respectively, per unit area, 2 equals length of span transverse to the direction of m, 5s is 456, 2000 I equals length of the clear span in the direction of m, measured facet face of supports, equals AKC and I where KKC and K are as defined in 3.1.4.3.3, and W.IL and I. Refer to the shorter span. 3.1.4.6 Effects of pattern loading in the direct design method. When the ratio of live load to dead load exceeds OS, A, the sum of the flexural stiffnesses of the columns above and below the slab, I shall be such that X is not less than the appropriate minimum value EXILTIA specified in table T7. Or B, if the sum of the flexural stiffnesses of the columns I does not satisfy, A, the positive design moments for the panels ball be multiplied by the coefficient P given by the following equation, B, each such frame may be analyzed in its entirety, or, for vertical loading, each floor thereof and the roof may be analyzed separately with its columns being assumed fixed at their remote ends. Where slabs are analyzed separately, it may be assumed in determining the bending moment at a given support that the slab is fixed at any support 2 panels distant therefrom provided the slab continues beyond the point. C. For the purpose of determining relative stiffness of members. The moment of inertia of any slab or column may be assumed to be that of the gross cross-section of the concrete alone. D. Variations of moment of inertia along the axis of the slab on account of provision of drops shall be taken into account. In the case of recessed or coffered slab which is made solid in the region of the columns, the stiffening effect may be ignored provided the solid part of the slab does not extend more than 0.15 EI in top span measured from the center line of the columns. The stiffening effect of lowered column heads may be ignored. 3.1.5.2 Loading pattern 3.1.5.2.1 When the loading pattern is known, the structure shall be analyzed for the load concerned. Ex is the ratio of flexural stiffness of the columns above and below the slab to the flexural stiffness of the slabs at a joint taken in the direction moments are being determined and is given B, x equals IC, C IC where Kc and K are flexural stiffnesses of column and slab respectively. 31.5 Equivalent frame method 3.1.5.1 Assumptions The bending moments and shear forces may be determined by an analysis of the structure as a continuous framing. The following assumptions may be made. A. The structure shall be considered to be made up of equivalent frames on column lines taken longitudinally and transversely through the building. Each frame consists of a row of equivalent columns or supports, bounded laterally by the center line of the panel on each side of the center line of the columns or supports. Frames adjacent and parallel to an edge shall be bounded by the edge and the center line of the adjacent panel. Table 17 Minimum permissible values of EXC, Clause 3 1.4.6, Impo HD Load Ideld Load, 1, OS 1.0 1.0 1.0 1.0 1.0 2.0 2.0 2.0 2.0 2.0 3.0 3.0 3.0 3.0 3.0 Redlow 2 OS to 2.0 0.50, 8 1.0 1.25 2.0 OS 0.8 1.0 1.2 S 2.0 0.5 0.8 1.0 1.25 2.07 Aura 3 O 0.6 0.7 0.7 0.8 1.2 1.3 1.5 1.6 1.9 4.9 1.8 2.0 2.3 2.8 13.03 1.5.2.1 when the live load is variable but does not exceed 3/4 of the dead load. Or the nature of the live load is such that all panels will be loaded simultaneously, the maximum moments may be assumed to occur at all sections when full design live load is on the entire slab system. S6 is 456, 2003 1.5.2.3 for other conditions of live load/dead load ratio and when all panels are not loaded simultaneously, a maximum positive moment near midspan of a panel may be assumed to occur when 3/4 of the full design live load is on the panel and on alternate panels, and b maximum negative moment in the slab at a support may be assumed to occur when 3/4 of the full design live load is on the adjacent panels only. 3.1.5.1.4 In no case shall design moments be taken to be less than those occurring with full design live load on all panels. 31.5.3 Negative design moment 31.5.3.1 At interior supports, the critical section for negative moment, in both the column strip and middle strip, shall be taken at the face of rectilinear supports, but in no case at a distance greater than 0.1752 from the center of the column where 2 is the length of the span in the direction moments are being determined, measured center to center of supports. 31.5.3.2 At exterior supports provided with brackets or capitals, the critical section for negative moment in the direction perpendicular to the edge shall be taken at a distance from the face of the supporting element not greater than 1/2 the projection of the bracket or capital beyond the face of the supporting element. 31.5.3.3 Circular or regular polygon-shaped supports shall be treated as square supports having the same area. 31.5.4 Modification of maximum moment moments determined by means of the equivalent frame method, for slabs which fulfill the limitations of 31.4 may be reduced in such proportion that the numerical sum of the positive and average negative moments is not less than the value of total design moment m specified in 31.4.2.2. 31.5.5 Distribution of bending moment across the panel with 31.5.5.1 Column strip, negative a moment at an interior support. At an interior support, the column strip shall be designed to resist 7% of the total negative moment in the panel at that support. 31.5.5.2 Column strip negative moment at an exterior support at an exterior support. The column strip shall be designed to resist the total negative moment in the panel at that support. b. Where the exterior support consists of a column or a wall extending for a distance equal to or greater than 3/4 of the value of 1, the 2 length of span transverse to the direction moments are being determined, the exterior negative moment shall be considered to be 2 uniformly distributed across the length. 31.5.5.3 Column strip, positive a moment for each span. For each span the column strip shall be designed to resist 60% of the total positive moment in the panel. 31.5.5.4 Moments in the middle strip. The middle strip shall be designed on the following basis: a. That portion of the design moment not resisted by the column strip shall be assigned to the adjacent middle strips. b. Each middle strip shall be proportioned to resist the sum of the moments assigned to its 2 half middle strips. c. The middle strip adjacent and parallel to an edge supported by a wall shall be proportioned to resist twice the moment assigned to half the middle strip corresponding to the first row of interior columns. 31.6 Shear in flat slab. 31.6.1 The critical section for shear shall be at a distance d/2 from the periphery of the column/capital/drop panel perpendicular to the plane of the slab where d is the effective depth of the section, see Fig 12. Tile Shapian plan is geometrically similar to the support immediately below the slab, see Fig 13a and 13b. Note, 4 column sections with entrant angles. The critical section shall be taken as indicated in Fig 13ca and D130. 3.1.6.1.1 In the case of columns near the free edge of a slab, the critical section shall be taken as shown in Fig 14. 31.6.1 When openings in flat slabs are located at a distance less than 10 times the thickness of the slab from a concentrated reaction, or when the openings are located within the column strips. The critical sections specified in 3.1.6.1 shall be modified so that the part of the periphery of the critical section which is enclosed by radial projections off the openings to the centroid of the reaction area shall be considered ineffective. /EE Fig 15, and openings shall not encroach upon column head. 3.1.6.2 Calculation of shear stress. The shear stress TV shall be the sum of the values calculated according to 3.1.6.2.1 and 3.1.6.2.2. 3.1.6.2.1 The nominal shear stress in flat slabs shall be taken as VIBD, where V is the shear force due to design load, bit is TH, periphery of the critical section, and D is the effective depth. 2116 815/07-957 15456, 2000 RL critical section I. T II. IL_ID/2TT support Suliport section column I column head 13A support section RR, L.D/2 critical section TII, dot colon, dot 1 colon dot dot colon dot R4 backslash L I D/2 ID/2 1 note D I the effective depth of the nat slab /drop flow 13 Carnielsk nons in plan for shear in flat slabs LR re-edge II2 dot Vikrasiet Sitsio and L dot colon I T/I_D/2 a free corner L__ corner column critical section 148 fro 14 EFFECR of FRBB boobs on Carniel SBC 110N for shear 3.1.6.2.2 when unbalanced gravity load, wind, earthquake, or other FOS cause transfer of bending moment between slab and column. A fraction, I, x, of the moment shall be considered transferred by eccentricity of the shear about the centroid of the critical section. Shear stresses shall be taken all varying linearly about the centroid of the critical section. The value of A shall be obtained from the equation given in 3.1.3.3. 3.1.6.3 Permissible shear stress 3.1.6.3.1 when shear reinforcement is not provided. The calculated shear stress at the critical section shall not exceed C. S8 opening, -4m subtract from periphery R column II colon J, JN20 ... plus AILTR is 46, 2000 opening column. LD/2 -1 I, 11 I6 IIIJ, RNIL. Critical I section __ I 15A 158 Penelng, IITI, critical I, section J1 STIIII. T0. Column I, OJ, colon dot. CR identical, IL colon. I section IL. G regard opening as free edge 15D flow. 15 EFFECF of openings on crinkle semen for SH pound AR where equals K, OS plus PC, but not greater than 1, PC being the ratio of short side to long side of the column. Capital, and equals TT 0.25 L, in limit state method of design, and 0.16 L, in working stress method of design. 3.1.6.3.2 when the shear stress at the critical section exceeds the value given in 3.1.6.3.1, but less than 1.S1 shear reinforcement shall be provided. If the shear stress exceeds IS1 CT the flat slab shall be redesigned. Shear stresses shall be investigated at successive sections more distant from support, and shear reinforcement shall be provided up to a section where the shear stress does not exceed 0.5 tons c. While designing the shear reinforcement, the shear stress carried by the concrete shall be assumed to be 0.5 t and reinforcement shall carry the remaining shear. 31.7 Slab reinforcement 31.7.1 Spacing. The spacing of bars in a flat slab shall not exceed 2 times the slab thickness, except where a slab is of cellular or ribbed construction. 31.7.1 Area of reinforcement when drop panels used. The thickness of drop panel for determination of area of reinforcement shall be the lesser of the following: a. Thickness of drop, and b. Thickness of slab plus 1/4 the distance between edge of drop and edge. Pf capital 31.7.3 Minimal 4 NL Length of reinforcement. A. Reinforcement in flat slabs shall have the minimum length specified in Fig. 16. Larger lengths of reinforcement shall be provided when required by analysis. B. Where adjacent spans are unequal. The extension of negative reinforcement beyond each face of the common column shall be based on a longer span. E. The length of reinforcement for slabs in frames not braced against sideways and for slabs resisting lateral loads shall be determined by analysis but shall not be less than those prescribed in Fig. 16. S9 IS4 S6, 2000. R. Minimum. Ailtit cent. OE0 LTE, T.IC1I0 N without DFT oft, nil, 10 Rima.Noir ITTTIRTR, I2, dash plus dash H, JIIIC, 1 RC, C = OP Gil, LC4IC, HLR colon dash dash colon dash colon dash J.TIR equals dash dash dot. Dash. Percent HIP 10 remainder. I. TLOIIRI 0 dot. TLO underscore underscore. C. I dot backslash. C slash Gil. I1A plus 10 LR colon colon T plus H, F dash dot O dash dash OR dash F yen, F dash I, FI10 dash PIIC asterisk equals AI, NWAR, underscore I, IXT dot LLL 011 SU, off T. DICLIA S, NL recreaten dot RASO SU, ORT. IA, I of SU underscore TTT employee SU FOIT, Lkviloit SU IOIT ENOS LA. Conti, MVII continuity, Ovoya. Cleos LA. Coflonui bar length FMMFAC of SLQI port minimum length muimum length mark ABCDEJG length 0.14/0.201. 0.22 I 0.30 I 0.33 0.201 0.24 Bent banet cluckreer supports may be used if anira I analyze is NIID. Knots. D is, Hediamisor of CBC column and DIICI /Zion of CBC recitant recaluled in thethanodon. Coileiduraltion. Flow. 16 Melnulmum bent joint LOC all 0 NS and extensions for reinforcement in flat slabs 60 is 456, 2003 1.7.4 Anchoring reinforcement. A. All slab reinforcement perpendicular to a discontinuous edge shall have an anchorage, straight, bent, or otherwise anchored, past the internal face of the spandrel beam. Wall or column, of an amount, 1, for positive reinforcement, not less than 150 mm except that with fabric reinforcement having a fully welded transverse wire directly over the support, it shall be permissible to reduce this length to 1/2 of the width of the support or so whichever is greater, and 2, for negative reinforcement, such that the design stress is developed at the internal face, in accordance with Section 3. B. Where the slab is not supported by a spandrel beam or wall, or where the slab cantilevers beyond the support. The anchorage shall be obtained within the slab. 31.8 Openings in flat slabs. Openings of any size may be provided in the flat slab if it is shown by analysis that the requirements of strength and serviceability are met. However, for openings conforming to the following, no special analysis is required. A. Openings of any size may be placed within the middle half of the span in each direction, provided the total amount of reinforcement required for the panel without the opening is maintained. B. In the area common to two column strips, not more than 1/8 of the width of strip in either span shall be interrupted by the openings. The equivalent of reinforcement interrupted shall be added on all sides of the openings. C. In the area COMM onto one column stripe and one middle strip, not more than 1/4 of the reinforcement in either strip shall be interrupted by the openings. The equivalent of reinforcement interrupted shall be added on all sides of the openings. D. The shear requirements of 31.6 shall be satisfied. 32 walls 31.1 General reinforced concrete walls subjected to direct compression or combined flexure and direct compression should be designed in accordance with Section 5 or Annex B provided the vertical reinforcement is provided in each face. Braced walls subjected to only vertical compression may be designed as per empirical procedure given in 31.2. The minimum thickness of walls shall be 100 ROM. January 1, 32 guidelines or design of walls subjected to horizontal and vertical loads are given in 32.3. 32.2 Empirical decimal method for walls subjected to in-plane vertical loads February 1, 32 Braced walls shall be assumed to be braced if they are laterally supported by a structure in which all the following apply. A. Walls or vertical braced elements are arranged in two directions so as to provide lateral stability to the structure as a whole. H. Lateral forces are resisted by shear in the planes of these walls or by braced elements. C. Floor and roof systems are designed to transfer lateral forces. D. Connections between the wall and the lateral supports are designed to resist a horizontal force not less than 1, the simple static reactions to theta tail applied horizontal forces at the level of lateral support, and 2.5% of the total vertical load that the wall is designed to catch at the level of lateral support. January 2, 32 Eccentricity O/vertical load. The design of a wall shall take account of the actual eccentricity of the vertical force subject to a minimum value of O.ost. The vertical load transmitted to a wall by a discontinuous concrete floor or roof shall be assumed to act at 1/3 the depth of the bearing area measured from the span face of the wall. Where there is an in situ concrete floor continuous over the wall, the load shall be assumed to act at the center of the wall. The resultant eccentricity of the total vertical load on a braced wall at any level between horizontal lateral supports, shall be calculated on the assumption that the resultant eccentricity of all the vertical loads above the upper support is 0. February 3, 32 Max, MRLM effective height to thickness ratio. The ratio of effective height to thickness weld shall not exceed 30. 1.2.4 Effective height. The effective height of a braced wall shall be taken as follows. A. Where restrained against rotation at both ends by 61 is 456, 2000 J, floors 2, intersecting walls or similar members whichever is the lesser. 0.75/1 or W 0.75 J, H, where not restrained against rotation at both ends by I, floors 2, intersecting walls or similar members whichever is the lesser. 1.02 or A 1.0 L1 where I equals shear force due to design loads. Equals wall thickness. D equals N.RL where L, is the length of the wall. April 2, 32. RJNDC, no circumstances shall the nominal shear stress RVWM walls exceed 0.17 tons, in limit state method and 0.12/ in working stress method. L. April 3, 32 Design shear strength of concrete 2/2, the unsupported height of the wall, equals L, the horizontal distance between centers of lateral restraint. 32.2. 5. Design axial strength of wall. 111E Design axial strength Pu per unit length of a braced wall in compression may be calculated from the following equation, equals P 0.3, T, 1.2E, 2E, FCKL1W where equals thickness of the wall, equals E eccentricity of load measured at tight angles to the plane of the wall determined in accordance with February 2, 32, and EL, Addizione eccentricity due to SLE Entranas effect taken as /1I2 500 tons We 32 walls subjected to combined horizontal and vertical forces March 1, 32 When horizontal forces are in the plane of the wall, it may be designed for vertical forces in accordance with 32.2 and for horizontal shear in accordance with 32.3. In plane bending may be neglected in case a horizontal cross-section of the wall is always under compression due to combined effect of horizontal and vertical loads. March 2, 32 walls subjected to horizontal forces perpendicular to the wall and for which the design axial load does not exceed 0.04 fkai shall be designed as slabs in accordance with the appropriate provisions under 24, where A is gross area of the section. It 32.4 Design for horizontal shear April 1, 32 critical section / or shear The critical section for maximum shear shall be taken at a distance from the base of OSLW or 0.5 h, whichever is less. April 2, 32 Nominal shear stress The nominal shear stress T/LW in walls shall be obtained as follows: RYW equals VU/T.D. The design shear strength of concrete in walls, T and V without shear reinforcement shall be taken as below. A. For HWILW1 equals KT. W. 3,0 ILO/LW, K, where K1 is 0.2 in limit state method and 0.13 in working stress method. B. For I/LWJ lesser of the DLJFLCLCJ left from A. above and.IROLJIR.WZ. Point 1, r h.v /i, j /1, underscore, where k, p.n for injure at ftt and /1 hot and 0.03 in work in strT.s method. But shall be not less than k /t in liv.rc. Where k is f, l.t, in Linnet state method and 0 in working stress method. 2. 4.4 Design OJ shear re or sem shear reinforcement shall he provided to carry a shear equal to v, w.t, ojl, In case of working stress L method v is replaced by v. The strength of shear L1 reinforcement shall be calculated D per 40.4 or BS.4 with A defined as below, equals A / OIPW, 0.8 LW, T where PW is determined as follows: A, for walls where HW Li S1. PW shall be the gesser of the ratios of either the vertical reinforcement area or the horizontal reinforcement area to the cross-sectional area of wall in the respective direction. B, for walls where HWILW1, P6 shall he the ratio of the horizontal reinforcement area to the cross-sectional area of wall per vertical meter. 32.5 Minimum requirements for reinforcement in walls. The reinforcement for walls shall be provided as below. 62 is 456, 2000 A. The minimum ratio of vertical reinforcement to gross concrete area shall be 1. 0.0012 for deformed bars not larger than 16 mm in diameter and with a characteristic strength of 415 N/mm2 or greater. 2. 0.0015 for other types of bars. 3. 0.12 for welded wire fabric not larger than 16 mm in diameter. B. Vertical reinforcement shall be spaced not farther apart than 3 times the wall thickness NOR 450 mm. C. The minimum ratio of horizontal reinforcement to gross concrete area shall be 1. 0.0020 for deformed bars not larger than 16 mm in diameter and with a characteristic strength of 415 Nzmm or greater. 2. 0.0025 for other types of bars. 3. 0.002, for welded wire fabric not larger than 16 rntn in diameter. D. Horizontal reinforcement shall be spaced not farther apart than 3 times the wall thickness nor 450 mm. Note_. The minimum reinforcement may not always be sufficient to provide adequate resistance to the effects of shrinkage, and temperature may first. 32 For walls having thickness more than 200 mm, the vertical and horizontal reinforcement shall be provided in 2 grids, one near each face of the wall. May 2, 32 Vertical reinforcement need not be enclosed by transverse reinforcement as given in 26.5.3.2 for column. If the vertical reinforcement is not greater than 0.0 I times the gross sectional area, or where the vertical reinforcement is not required for compression. 33 Stairs 33.1 Effective span of stairs. The effective span of stairs without stringer beams shall be taken as the following horizontal distances: a. Where supported at top and bottom risers by beams spanning parallel with the risers. The distance center to center of beams. b. Where spanning onto the edge of a landing slab, which spans parallel with the risers, see Fig 17. A distance equal to the going of the stairs plus at each end either half the width of the landing or 1 meter, whichever is smaller, and c. Where the landing slab spans in the same direction as the stairs. They shall be considered as acting together to form a single slab, and the span determined as the distance center to center of the supporting beams or walls. The going being measured horizontally. 33.2 Distribution of loading on stairs. In the case of stairs with open wells, where spans partly crossing at right angles occur, the load on areas common to any 2 such spans may be taken as 1/2 in each direction, as shown in Fig 18. Where flights or landings are embedded into walls for a length of nor less than 10 mm and are designed to span in the direction of the flight, a 150 mm strip may be deducted from the loaded area and the effective breadth of the section increased by 75 mm for purposes of design, see Fig 19. 33.3 Depth of section 111 Depth of section shall be taken as the minimum thickness perpendicular to the soffit of the staircase. 34 Footing, hesitant face. 34.1 General footings shall be designed to sustain the applied loads, moments and forces and the induced reactions, and to ensure that any settlement which may occur shall be as nearly uniform as possible and the safe bearing capacity of the soil is not exceeded. SA is 1904, January 1, 34 In sloped or stepped footings the effective III1K it up XX foregoing, G, plus VIVLXY1M1M1MM1MLM. M span in meters GXYGX plus 1 GYG, plus 1 Fig 17 Effective span for stairs supported at each end IW landings spanning parallel WNH. The risers 63 is 456, 2000. C8 EAM up IINIW. The load on are common to 2 systems to 81 pounds taken as 1 HAL. In each direction flow. 18 Low ADINO on stairs with open wells flow. 19 Low ADINO on stairs bun. T into WAJ.LS cross section in compression shall be limited by though area above the neutral plane, and though angle of slope or depth and location of steps shall be such that the DSUP requirements are satisfied at every section. Sloped and stepped footings that are designed as a unit shall be constructed to assure action as a unit. January 2, 34 Thickness at the edge 01 Footing in reinforced and play concrete footings, the thickness at each shall be not less than 150 mm for footings on soils, nor less than 300 mm above the top soft piles for footings on piles. January 3, 34 In the case of plain concrete pedestals, the angle between the plane passing through the bottom edge of the pedestal and the corresponding junction edge of the column with pedestal and the horizontal plane, see Fig 20, shall be governed by the expression, PUC 10A 0.9 plus 1 I where Q calculated maximum bearing pressure at the base aft pedestal in N/mm2, and equals LEII. Characteristic strength of concrete at 28 days in N/mm2 34.2 moment band 4. 34.1.11 And the case of footings on piles, computation for moments and shears may be based on the assumption that the reaction from any pile is concentrated at the center of the pile. February 2, 34 For the purpose of computing, stresses in footings which support a round or octagonal concrete column or pedestal, the face of the column or pedestal shall be taken as the side of a square inscribed within the perimeter octaround or octagonal column or pedestal. February 3, 34 Bending moment 34.2.3.1 The bending moment at any section shall be determined by passing through the section a vertical I-column I-plane concrete pedestal flow. 2064 is 456, 2000 plane which extends completely across the footing and computing the moment of the forces acting over the entire area of the footing on one side of the said plane. 34.2.3.2 The greatest bending moment to be used in the design of an isolated concrete footing which supports a column, pedestal or wall, shall be the moment computed in the manner prescribed in 34.2.3.1 at sections located as follows: a. At the face of the column, pedestal, or wall, for footings supporting a concrete column, pedestal, or wall; b. Halfway between the center line and the edge of the wall, for footings under masonry walls; and c. Halfway between the face of the column or pedestal and the edge of the gusset base, for footings under gusset bases. February 4, 34 Shear and bond 34.2.4.1 The shear strength of footings is governed by the more severe of the following two conditions: a. The footing acting essentially as a wide beam, with a potential diagonal crack extending in a plane across the entire width. The critical section for this condition shall be assumed as a vertical section located from the face of the column, pedestal, or wall at a distance equal to the effective depth of footing for footings on piles. b. Two-way action of the footing, with potential diagonal cracking along the surface of truncated cone or pyramid around the concentrated load. In this case, the footing shall be designed for shear in accordance with appropriate provisions specified in 31.6. 34.2.4.2 In computing the external shear of any section through a footing support in piles, the entire reaction from any pile of diameter d1, whose center is located d/2 or more outside the section shall be assumed as P opposing shear on the section. The reaction from any pile whose center is located drive/2 or more inside the section shall be assumed as producing no shear on the section. For intermediate positions of the pile center, the portion of the pile reaction to be assumed as producing shear on the section shall be based on straight line interpolation between full value at d1/2 outside the section and zero value at d/2 inside the I section. 34.2.4.3 The critical section for checking the development length in a footing shall be assumed at the same planes as those described for bending moment in February 3, 34 and also at all other vertical planes where abrupt changes of section occur. If reinforcement is curtailed, the anchorage requirements shall be checked in accordance with 26.2.3. 34.3 Tensile reinforcement. The total tensile reinforcement at any section shall provide a moment of resistance at least equal to the bending moment on the section calculated in accordance with February 3, 34. March 1, 34 Total tensile reinforcement shall be distributed across the corresponding resisting section as given below. A. In one-way reinforced footing, the reinforcement extending in each direction shall be distributed uniformly across the full width of the footing. H. In two-way reinforced square footing, the reinforcement extending in each direction shall be distributed uniformly across the full width of the footing. And C. In two-way reinforced rectangular footing, the reinforcement in the long direction shall be distributed uniformly across the full width of the footing. For reinforcement in the short direction, a central band equal to the width of the footing shall be marked along the length of the footing, and portion of the reinforcement determined in accordance with the equation given below shall be uniformly distributed across the central band. Reinforcement in central bandwidth to total reinforcement in short direction equals +1, where is the ratio of the long side to the short side of the footing. The remainder of the reinforcement shall be uniformly distributed in the outer portions of the footing. 34.4 Transfer of load at the base of column. The compressive stress in concrete at the base of a column or pedestal shall be considered as being transferred by bearing to the top of the supporting pedestal or footing. The bearing pressure on the loaded area shall not exceed the permissible bearing stress in direct compression multiplied by a value equal to Ka, but not greater than 2, where equals Ai supporting area for bearing of footing, which in sloped or stepped footing may be taken as the area of The lower base of the largest frustum of a pyramid or cone contained wholly within the footing and having for its upper base, the area actually loaded and having side slope of 1 vertical to 2 horizontal, and equals a loaded area at the column base. 2116 815/07-1065 is 456, 2000 For working stress method of design. The permissible bearing stress in full area of concrete shall be takinas 0.25, c. For limit state method of design, he permissible bearing stress shall be 0.45 let. April 1, 34 Where the permissible bearing stress on the concretine the supporting or supported member would be exceeded, reinforcement shall be provided for developing the excess force, either by extending the longitudinal bars into the supporting member, or by dowels, see April 3, 34. April 2, 34 Where transfer of force is accomplished by reinforcement, the development length of the reinforcement shall be sufficient to transfer the compression or tension to the supporting member in accordance with 26.2. April 3, 34 Extended longitudinal reinforcement or dowels of at least 0.s% off the cross-sectional area of the supported column or pedestal, and a minimum of 4 bars shall be provided. Where dowels are used, their diameter shall no exceed the diameter of the column bars by more than 3 mm. April 4, 34 Column bars of diameters larger than 36 mm, in compression only can be doweled at the footings with bars of smaller size of the necessary area. The dowel shall extend into the column a distance equal to the development length of the column bar, and into the footing, a distance equal to the development length of the dowel. 34.5 Nominal reinforcement May 1, 34 Minimum reinforcement and spacing shall be as per the requirements of solid slab. May 2, 34 The nominal reinforcement for concrete sections of thickness greater than 1 m shall be 360 mmz per meter length in each direction on each face. This provision does not supersede the requirement of minimum tensile reinforcement based on the depth of the section. Section 5 Structural Design, Limit State Method, is 456, Z00035 Safety and Serviceability Requirements 35.1 General in the method of design based on limit state concept, the structure shall be designed to withstand safe loads liable to act on it through its life. It shall also satisfy the serviceability requirements, such as limitations in deflection and cracking. The acceptable limit for the safety and serviceability requirements before failure occurs is called a limit state. The aim of design is to achieve acceptable probabilities that the structure will not become unfit for the use for which it is intended, that is, that it will not reach a limit state. January 1, 35 All relevant limit states shall be considered in design to ensure an adequate degree of safety and serviceability. In general, the structure shall be designed on the basis of the most critical limit state and shall be checked for other limit states. January 2, 35 For ensuring the above objective, the design should be based on characteristic values for material strengths and applied loads, which take into account the variation seen in the material strengths and in the loads to be supported. The characteristic values should be based on statistical data JF available. Where such data are not available, they should be based on experience. The design values are derived from the characteristic values through the use of partial safety factors, one for material strengths and the other for loads. In the absence of special considerations, these factors should have the values given in 36 according to the material, the type of loading. And the limit state being considered. 35.2 Limit State 01 CO DAPS The limit state of collapse of the structure or part of the structure could be assessed from rupture of one or more critical sections and from buckling due to elastic or plastic instability, including the effects of sway where appropriate, or overturning. The resistance to bending, shear, torsion and axial loads at every section shall not be less than the appropriate value at that section produced by the probable most unfavorable combination of loads on the structure using the appropriate partial safety factors. 35.3 Limit States of Serviceability March 1, 35 Deflection limiting values of deflections are given in 23.2. March 2, 35 Cracking of concrete should not adversely affect the appearance or durability of the structure. The acceptable limits of cracking would vary with type of structure and environment. where a specific attention is required to limit the designed crack width to a particular value. Crack width calculation may be done using formula given in Annex F. The practical objective of calculating crack width is merely to give guidance to the designer in making appropriate structural arrangements and in avoiding gross errors in design, which might result in concentration and excessive width of flexural crack. The surface width of the cracks should not, in general, exceed 0.3 mm in members where cracking is not harmful and does not have any serious adverse effects upon the preservation of reinforcing steel nor upon the durability of the structures. In members where cracking in the tensile zone is harmful either because they are exposed to the effects of the weather or continuously exposed to moisture in contact soil or groundwater, an upper limit of 0.2 mm is suggested for the maximum width of cracks. For particularly aggressive EE environment, such as the severe category in Table 3, the assessed surface width of cracks should not in general exceed 0.1 mm. 35.4 Other limit state structures designed for unusual or special functions shall comply with any relevant additional limit state considerate appropriatito that structure. 36 Characteristic and design values and partial safety factors. 36.1 Characteristic strength of materials. The term characteristic strength means that value of the strength of the material below which not more than 5% of the test results are expected to fall. The characteristic strength for concrete shall be in accordance with Table 2. Until the relevant Indian standard specifications for reinforcing steel are modified to include the concept of characteristic strength, the characteristic value shall be assumed as the minimum yield stress 10.2% proof stress specified in the relevant Indian standard specifications. 36.2 Characteristic loads. The 10 characteristic load means that value of load which has a 9% probability of not being exceeded during the life of the structure. Since data are not available to express loads in statistical terms, for the purpose of this standard, dead loads given in is 875. Part 1. Imposed loads given in is 875, Part 2, wind loads given in is 875, Part 3, snow load as given in is 875, Part 4, and seismic forces given in is 1893 shall be assumed as the characteristic loads. 61 is 456. 2036.3 Design values. March 1, 36 Materials. The design strength of the materials. J is given B. 36.4.2 Partial safety factor. Aim for material strength. 36.4.2.1 When assessing the strength of a structural member for the limit scale of collapse, the values of partial safety factor R should be taken as IS for concrete and US for steel, where equals F characteristic strength of the material, C31.1, and equals EM partial safety factor appropriate to the material and the limit state being considered. March 2, 36 Loads. The design load Phi is given by FD equals F year, where F equals characteristic load, C36.2, and equals YF partial safety factor appropriate to the nature of loading and the limit state being considered. March 3, 36 Consequences of attaining limit state, where the consequences of a structure attaining a limit state are of a serious nature, such as huge loss of life and disruption of the economy. Higher values for YF and EM than those given under 36.4.1 and 36.4.2 may be applied. 36.4 Partial safety factors. April 1, 36 Partial safety factor YF for loads. The values of YF given in Table 18 shall normally be used. Note, Y values are .1 ready incorporated il the equations and tables even il this .standard for limit state. Design 36.4.2.2 When assessing the deflection, the material properties such as modulus of elasticity should be taken 8, those associated with the characteristic strength of the material. 37 Analysis. 37.1 Analysis of structure. Methods of analysis as in 22 shall be used. The material strength to be assumed shall be characteristic values in the determination of elastic properties of members irrespective of the limit state being considered. Redistribution of the calculated moments may be medias given in January 1, 37. January 1, 37 Redistribution of moments in continuous beams and frames. The redistribution of moments may be carried out satisfying the following conditions. A. Equilibrium between the internal forces and the external loads is maintained. H. The ultimate moment of resistance provided at any section of a member is not less than 70% of the moment at that section obtained from an elastic maximum moment diagram covering all appropriate combinations of loads. C. The elastic moment at an ejection in a member due to a particular combination of loads shall Table 18 values of partial safety factor YF for loads, Clause T1 8.2.3.1.36.4.1 and B4.3, load combination, I. Unlit state 01 COI-IP. DLILWL, 2, 3, 4, limit statal of Sinel-Sabuloy DLILWL, 5, 6, 7, DL /LDL and WLDL /L and WLIS 1.0 IS or 1.S.091. 1.2 1.0 1.0 1.0 1.0 1.0 0.8 0.8 Notes 1 While considering earthquake effects, substitute L for WL2 for LH limit states of serviceability. The Voluca or 1. Liven in Thistobary applicable fortune term effects. While asses. Inith a loft term effects to eto en epthed load and that part of the live load likely to be permanent may and live considered. And this values to be considered when stability against overturning or stress revenal il critical. 68 Not be reduced by more than 30% off the numerically largest moment given anywhere by the elastic maximum moments diagram for the particular member. Covering O appropriate combination of loads. D. At sections where the moment capacity after redistribution is less than that from the elastic maximum moment diagram. The following relationship shall be satisfied: 5L plus 8M so 0.6 D 100 where SU equals depth of neutral axis equals D effective depth and equals 6M percentage reduction in moment. E. In structures in which the structural frame provides the lateral stability. The reductions in moment allowed by condition January 1, 37, C, shall be restricted to 10% for structures over 4 stories in height. January 2, 37 Analysis of slabs spanning in LO directions at right angles yield line theory or any other acceptable method may be used. Alternatively, the provisions given in Annex D may be followed. 38 Limit state of collapse, flexure 38.1 Assumptions designed for the limit state of collapse in flexure shall be based on the assumptions given below. A. Plane sections nominal to the axis remain plane after bending. _RT-FA 15456, 2000 B. The maximum strain in concrete at the out and ost compression fibres taquinas 0.0035 in bending. C. The relationship between the compressive stress distribution in concrete and the sustaining concrete may be assumed to be rectangle, trapezoid, parabola or any other shape which results in prediction of strength in substantial agreement with the results of test. An acceptable stress-strain curve is given in Fig 21. For design purposes, the compressive strength of concrete in the nature shall be assumed to be 0.67 times the characteristic strength. The partial safety factor Y equals 1.5 shall be applied in addition to this. Note, Porti Strulerlinkomil RRLJ. 21 Didiap stress block plyoid chlori is follows, FLFIP at 22 area of Suis block 0.36 lot x depth of cellidal of Koloploliv force 0.42 x from the extreme FIM if compression when I equals Shankdiatic C Permissible both often Leal C x equals DEPCH of Newton LWID, the tensile strength of the concrete is ignored. E. The stresses in the reinforcement are derived from representative stress-strain curve for the type of steel used. JE Pica 1 curves are given in Fig 23. For design purposes, the partial safety factor EM equal to 1.15 shall be applied. F. The maximum strain in the tension reinforcement in the section at failure shall not be less than, T plus 0.0021.15 E. Where F, equals characteristic strength of steel. and equals E, modulus of elasticity of steel. T33, H7FCKTO42 Su3 IL, TIII 0.67 FCKIRM Su036 FCK Su0002 strain 003 S Fig 21 stress strain curve RRCONCRM 69 Fig 22 stress block paramay I1, Rs 18456, 2000 ton stress dash phi slash I dot. 200010000-0001 SLRAIN. 23A cold work defoned bar RT-L.15 pound, 2000000N/mm 238 steel bar with 0 MNNE yield point flow. 23 representative stress S11 Ta 1 N curves for reinforcement. Note, the limiting values of the depth of neutral Lewis for diff NL gratis off steel based on the assumptions in 31.1118 as FOUs, F, X underscore LD2S003 415 0.480 Su 0.46. The expression for obtaining the moments REA.iltons for etanellular and T section L. Bild oil the Liothi apply UA.1, 118, given in Annex 39 Guaranese limit stat of collapse. Compression 39.1 also them in addition to the assumptions given in 38.1a, to 38.1, c, for flexure, the following shall be assumed. A. 1 BE maximum compressive strain in concrete in axial compression is taken as 0.002. B. 1 BE maximum compressive strain at the highly compressed extreme fiber in concrete subjected to axial compression and bending, and when they race Noten section shall be 0.003 s minus 0.75 times the strain at the least compressed extreme fiber. 39.2 MWW is Cedarity Al members in compression shall be designated for the minimum eccentricity in accordance with 25.4. Where 70 is 456. 2000 calculated eccentricity is larger, the minimum eccentricity should be Baynard. 39.3 short axially low decimi ben in cold nalid. The member shall be designed by considering the assumptions given in 39.1 and the minimum eccentricity. When the minimum eccentricity as per 25.4 does not exceed O.os times the lateral dimension, the members may be designed by the Folowen's equation, equals ET. Pi 0.4.ac plus 0.67 f, .aie where pu axial load on the member equals I characteristic compressive strength of the concrete, equals AC area of concrete, T, equals characteristic strength of T compression reinforcement, and L equals area of longitudinal reinforcement for columns. 39.4 compression membrane with radial reinforce meet the strength of compression members with helical reinforcement satisfying. The requirement of 39.4.1 shall be taken as 1.0 times T strength of similar member with later alties. April 1, 39. The ratio of the volume of helical reinforcement to the volume of the core shall not be less than 0.36, A.IACL, F** F, where equals APSS area of the section, equals AC area of theory of the helically reinforced column measured to the outside diameter of the helix, Fa characteristic compressive strength of the concrete, and I, equals characteristic strength of the helical reinforcement but not exceeding 41 N/mm2. 39.5 membrane subjected to combined axial load at Dunlal Bedield. A member subjected to axial force and uniaxial bending shall be decised on the basis of 39.1 and 39.3. Note, the Delhi, of member subject to combined ulo at and unio bendin will involve left-tilhe calculation by trial and error. In Orci. To overcome these difficulties intonacio DDIQL1 UDL may be the have been prepared ad published by 8 is in SP 16 Dealan Ida for reinforced CO and Siri 2 to is456. 39.6 members subjected to combined axial load and biaxial Benel D. The resistance of a member subjected to axial force and biaxial bending shall be obtained on the basis of assumptions given in 39.1 and 39.2 with neutral axis so chosen as to satisfy the equilibrium of load and moments about twoaxes. Alternatively, such members may be designed by the following equation: AA plus mu es 10 ALUX1 ATU1, where mu LT mi E equals moments about x and y axes due to design loads, equals maximum uniaxial moment capacity for an axial load off Pu bending about x and y axes, respectively, and Q is related to pulp G equals where pi z 0.4 slit AC plus 0.7 S1. L equals 4 values of Pu Pui 0.2 to 0.8, the values of A vary linearly from 1.0 to 2.0. For values less than 0.2, AA is 1.0. For values greater than 0.8, Q is 2.0. 39.7 Slender Comp, Lawn Member. The design of slender compression members, C25.1.1, shall be based on the forces and the moments determined from an analysis of the structure, including the effect of deflections on moments and forces. When the effect of deflections are not taken into account in the analysis, additional moment given in July 1, 39 shall be taken into account in the appropriate direction. July 1, 39 The additional moments M and Mi shall be calculated by the following formulae: M equals pi d, A2U 2000 d mm. 22.y 2000 b, where equals Pu axial load in the member, equals law effective length in respect of the major axis, equals Ey effective length in respect of minor axis, equals d depth of the cross section at right angles to the major axis, and b equals width of the member. For design of section, 39.5 or 39.6 as appropriate shall apply. 71 18456, notes 1 A column may be considered B Arcadina Jivan plane if 1 alil stability to the I1 nick to I hole is provided by W. A. Euler-Bersin. Or bolt jaladi dilapet 2. Il al 1 alurlf. In that plane, it should upper y. Beo de lichterd _udn cc. 2 in the Q of a beamst cola. Without uitnn any load la kurik in it a hay pt, that additional moment e halbidded to an initial mom dt equal to lum of 0.4 miles and 0.6 w2, where mwj is the laker end moment and mi is the smaller end moment, illumed neptiv if the column 2 bent in double curvature. In do CIIE shalth initial molded. Belay. Then 0.4 m.2 noric total moment in kluklil dynishimomet belisathat md, for \1 braced kalumua, the dishiatal moment shall be to themed momenta. 3 Unberkedkomschen memben .11 Analiven level OR1 TORE. Lubject to lateral load are ulually codal drain to cleftect equally. Inso chb taken the kilanklkmu rita forukla vini for all eoluiddi ikdinikalulil may ill the same dejection. 39.7.1.1 The values given by equation July 1, 39 may be multiplied by the following factor, equals p, ijsi pui / where p axial compression member, equals p as defined in 39.6, and equals pH axial load corresponding to the condition of maximum compressive strain of 0.0035 in concrete and tensile strain of 0.002 in outermost layer of Fenton steel. 40 Limit state of collapse, shear 40.1 nomio E shear S. The nominal shear stress in beams of uniform depth will be obtained by the following equation. T:(LB where Vi shear force due to dissip loads, B breadth of T member, which forflan lead section shall be taken U the breadth of the web, B, and equals D effective depth. January 1, 40 BDMI of varying depth. In the case of beams of varying S depth the equation shall be modified U, of the beam. The negative sign in the null applies when the bending moment Mi increases numerically in the same direction as the effective depth D increases. And the positive sign when the moment decreases numerically in this direction. 40.2 Dissip shear strength 01 Coerit February 1, 40 Theed sign shear strength of concrete in beams without shear reinforcement is liven in table 19. November 1, 40 for solid slabs, the deci end shear strength for concrete shall be Fel, where IE has the values given below, overall DTPTH 300 or 275 150 M 200 175 ISO or 01 SLAB, mm more less IE 1.00 1.0 S 1.10 I.IS 1.20 1.25 1.30 NOYS, null PROV alien shall not apply to flat slab. Formwork 31.6 shall apply. February 2, 40 shear strength of MTMBTRS under axial compression for members subjected to axial compression. PU the design shear strength of concrete, given in Table 19, shall be multiplied by the following factor, equals 6I plus 2A. L but not exceeding 1.5 I jet where equals PU axial compressive force in newtons, A equals gross area of the concrete section in, and equals let. Characteristic compressive STL1 NATH of concrete. 40.13 with shear reinforcement under no circumstances. Even with shear reinforcement. Shalt nominal shear stress in beams TV exist TCMU liven in Table 20. 40.2.3.1 for solid slabs, the nominal shear stress shall not exceed half the appropriate values given in Table 20. 40.3 minimum shear reinforcement when TV is less than TC liven in Table 19. Minimum shear reinforcement shall be provided in accordance with 26.5.1.6. VI, M, TANF JF DVBTL where 1 VVB and D are the same as in 40.1. M bend in L moment at the section, and an aisle between the top and the bottom edges. 40.4 DAP of shear reinforcement when E exceeds 1C given in Table 19. Shear reinforcement shall be provided in any of the following forms: A. Vertical Stein-ups. B. Bent up Banalona with stirrups, and 72 18456, 2000 L00 BTL, L, Table 19 DIP shear TRE01 concrete, TCNI, R, CLTUs 40.2.1. February 2, 40.3. 40.440.S.3. March 2, 41 March 3, 41 and 41.4.3. COD CNT ENA Miss M20 M2S M30, 2, 3, 4, 5, M3S, 6, M40 ILD above, 7, 0.T5 0.280 0.280 0.290 0.290 0.290 0.30 0.25 0.35 0.36 0.36 0.37 0.37 0.38 0.50 0.46 0.48 0.49 0.50 0.50 0.51 0.1 S 0.54 0.56 $0 1 0.59 0.59 0.60 1.00 0.60 0.62 0.64 0.66 0.61 0.68 1.2 S 0.64 0.61 0.10 0.11 0.73 0.74 ISO 0.68 0.12 0.14 0.76 0.18 0.79 1.1 S 0.11 0.7 S 0.78 0.80 0.82 0.84 2.00 0.11 0.79 0.82 0.84 0.86 0.88 2.25 0.11 0.81 0.85 0.88 0.90 0.92 2.50 0.11 0.82 0.88 0.9 tons 0.93 0.95 2.7 S 0.71 0.82 0.90 0.94 0.96 0.98 3.00 0.71 0.82 0.92 0.96 0.99 1.01 N and D. Above note, the term A is the aral of lonaltudinal 110. Lon reinforcement which can lose ediclist own effective depth beyond the section bane, considered EXC, PT ets upon where the full area of tension reinforcement may be used provided the det la line CONF-on.TO16.1.1 and 26.1.3 Table 10 Maximum Shear Stress, FCN/MMJ, CIA February 3, 40. 40.2.3.140.S.1 Arad March 1, 41, Concrete Miss M20 M2S M30 Nkl 2.52. 3.13.SM3S 3.7 M40 Lied I above 4.0 C, Inclined Stirrups. Where bent-up bars are provided. Their contribution towards shear resistance then not be more than half that of the total shear reinforcement. Shear reinforcement shall be provided Tokaria shear equal to Vu, FBD the Atranath of Akar reinforcement V, shall be calculated U below, A, for vertical stirrupa, _0_87, /.1, A, .ydvu14b, for inclined stirrups or a series of barrel bent up at different cross sections, VU10.8.7e-/VDSV, SMA and COSA, C, for 5 in 1 E-bar or 5 in IE group of parallel bars. All bent up at the same cross section, where A2, total cross-sectional area of stirrup legs or bent-up band within a distance SS specina of the stirrups or bent-up bars alone the length of the member, TV3 and C, Nominal shear sire. S, E, 2, Dizian shear strenath of the concrete. B3 breadth of the member which for flan. Ed beams, shall be taken as the breadth of tube equals IR characteristic itranjath of the stirrup or bent up reinforcement which shall not be taken J redder than 41 N/mm2, a 3 angle between the inclined stirrup or bent up barrent axis of T member. Not less than 4 degree. And D, effective depth. 21H1815/07_1173 is 456, 2000 notes 1 where more, Hanan type of shear reinforcement is used to reinforce its same portion of the beam. The total shear resistance shall be computed as the sum of resistance for the various types separately. 2 Theory of the stirrups hall not be less than the minimum specified in 26.5.1.640.5 Enhanced shear strength of sections closed to supports May 1, 40 General shear failure at sections of beams and cantilevers without shear reinforcement WIIJ normally occur on plane. Inclined at an angle 30 degrees to the horizontal. If the angle of failure plane is forced to be inclined more steeply than this because the section considered, X, in Fig 24 is close to a support or for other reasons, the shear force required to produce failure is increased. The enhancement of shear strength may be taken into account in the design of sections near a support by increasing design shear strength of concrete to 2 DREIA, provided that design shear stress at the face of the support remains less than the values given in Table 20. Account may be taken of the enhancement in any situation where the section considered is closer to the face of a support or concentrated load than twice the effective depth. D. To be effective, tension reinforcement should extend on each side of the point where it is intersected by a possible failure plane for a distance at least equal to the effective depth, or be provided with an equivalent anchorage. May 2, 40 Shear reinforcement for sections closed to supports if shear reinforcement is required. The total area of this is given by AI equals IB, TV, 2DFJA, I 0.87/0.4 IB/0.87. This reinforcement should be provided within the middle 3/4 of LV where E is less than D. Horizontal shear reinforcement will be effective than vertical. May 3, 40 Enhanced shear strength near supports, simplified approach. The procedure given in 40.5.1 and 40.5.2 may be used for all beams. However, for beams carrying generally uniform load or where the principal load is located farther than 2D from the face of support, the shear stress may be calculated at a section a distance D from the face of support. The value of Tc is calculated in accordance with Table 19 and appropriate shear reinforcement is provided at sections closer to the support. No Funher check for shear at such sections is required. 41 Limit STA1E of collapse, torsion. 41.1 General in structures, where torsion is required to maintain equilibrium, members shall be designed for torsion in accordance with 41.2, 41.3 and 41.4. However, for such indeterminate structures where torsion can be eliminated by releasing redundant restraints, no specific design for torsion is necessary, provided torsional stiffness is neglected and the calculation of internal forces. Adequate control over torsional cracking is provided by here reinforcement as per 40 N. T. The approach to design in this clause is as follows: torsional reinforcement is not calculated separately from that required for bending and shear. Instead, the lodal longitudinal reinforcement is determined for a fictitious bending moment which is a function of actual bending moment and torsion. Note, the shear causing failure is that acting on section XX Fig 24 shear failure near support 74 is 456, 2000. Similarly, web reinforcement is determined for 3 fictitious shear which is a function of actual shear and torsion. January 1, 41. The design rules laid down in 41.3 and 41.4 shall apply to beams of solid rectangular cross-section. However, these clauses may also be applied to flanged beams, by substituting BW for B, in which case they are generally conservative, therefore specialist literature may be referred to. 41.2 Critical sections located less than a distance d from the face of the support may be designed for the same torsion as computed at a distance d, where it is the effective depth. 41.3 Shear and torsion. March 1, 41. Equivalent shear where I is the torsional moment, d is the overall depth of the beam and b is the breadth of the beam. For 1.4.2.1 if the numerical value of m as defined L in April 2, 41 exceeds the numerical value of the moment A1, longitudinal reinforcement shall be provided on 11 the flexural compression face, such that the beam can also withstand an equivalent ME2 given high ME2 equals M, mu the moment M.2 being taken as a kung in the opposite sense to the moment MU. 41.4 Transverse reinforcement. 2-legged closed hoops enclosing the corner longitudinal bars shall have an area of cross-section A / given by equivalent shear, VC shall be calculated from the formula, where V equals equivalent shear equals V shear, U1 U equals torsional moment, and B equals breadth of beam, the equivalent nominal shear stress. TV in this case shall be calculated as given in 40.1, except for substituting /U high VC. The values of RV shall not exceed the values of TT mol given in Table 20. March 2, 41. If the equivalent nominal shear stress, T/L docs not exceed TL given in A Block 19, minimum shear reinforcement shall he provided as per 26.5.1.6. A::7J SV and VUSV SV high lil, O.H7J, 2.5 ft, J7/ HUT. The total transverse reinforcement shall not be less than, F/E, FC.pound S 0.87 J where 1, torsional moment, I_, shear force, S, equals spacing of the stirrup reinforcement. B. Center to center distance HCTWCC and CT under I bars in the direction of the width. D. 0 center to center distance between corner bars, March 3, 41. If TV / exceeds T, given in Table 19. Both longitudinal and transverse reinforcement shall he provided in accordance with 41.4. 41.4 Reinforcement in members subjected to torsion. April 1, 41. Reinforcement for torsion, when required, shall consist of longitudinal and transverse reinforcement, H, breadth of the member, T, characteristic strength of the stirrup reinforcement, T, equivalent shear stress as specified in W. March 1, 41, and shear strength of the concrete as RTR Table it. April 2, 41. Longitudinal reinforcement. The longitudinal reinforcement shall he design to resist an equivalent bending 1L10111 CNL, MD, given by MD equals mu plus M, where equals M bending moment at the cross section, and UM equals T. I plus, JLB, U 1.742 limit station of SFRVLLEBI.4 IT / NEII.LE:RL on 42.1 flexural members in all normal cases. The deflection of a flexural member will not be excessive if the ratio of its span to its effective depth is not greater than appropriate ratios given in 23.2.1. When deflections are calculated according to an XC, they shall not exceed the permissible values given in 23.2. 75 is 456, 2043 limit state of serviceability, cracking 43.1 flexural members in general compliance with the spacing requirements of reinforcement given in 26.3.2 should be sufficient to control flexural cracking. If greater spacing are required, the expected crack width should be calculated by formula given in Annex F. 43.2 compression members cracks due to bending in a compression member subjected to a design axial load greater than 0.2 fc. AC where JIET is the characteristic compressive strength of concrete and AC is the area of the gross section of the member, need not be checked. A member subjected to lesser load than 0.2 let AC may be considered as flexural member for the purpose of crack control, see 43.1. I. Annexa, Clause 2, List of referred Indian standards is 456, Z000 is number 269, 1989 383, 1970 432, Part 1, 1982 4SS, 1989 516, 19S 9875, Part 1, 1987, Part 2, T987, Part 3, 1987, Part 4, 1987, Part S, 1987 1199, 1959 1343, 1980 1489, Part 1, 1991, Part 2, 1991 1566, 1982 1641, 1988 Nile specification for ordinary Portland cement, 33 grade, 4th revision, specification for coarse and fine aggregates from natural sources for concrete, 2nd revision, specification for mild steel and medium tensile steel bars and hard-drawn steel wire for concrete reinforcement, Part 1 mild steel and medium tensile steel bars, 3rd revision, specification for Portland slag cement, 4th revision, method of test for strength of concrete code of practice for design loads, other than earthquake, for building sand structures, dead loads, unit weights of building material and stored materials, 2nd revision, imposed loads, 2nd revision, wind loads, 2nd revision, snow loads. 2nd revision, special loads and load combinations, 2nd revision, methods of sampling and analysis of concrete code of practice for pre-stressed concrete, 1st revision, specification for Portland pozzolana cement, fly ash based, 3rd revision, calcined clay based, 3rd revision, specification for hard-drawn steel wire fabric for concrete reinforcement, 2nd revision, code of practice for fire safety of buildings, general principles of fire grading and classification, 1st revision, is number 1642, 1989 1186, 1985 1791, 1968 1893, 1984 1904, 1986 2062, 1992 2386, Part 3, 1963 2502, 1963 2S05, 1980 2506, 1985 2514, 1963 2751, 1979 3025, Part 17, 1984, Part 18, 1984 Entel Code of Practice for Fire Safety Off Buildings, N. Details of Construction, 1st IT Vilio 1L, Specification for High-Strength Deformed Steel Bar Sand Wire S4 Concrete Reinforcement, 3rd Emule, Specification for Batch-Type Concrete Mixers, STCOM Revision, Criteria for Earthquake Resistant Design of Structures, 4th Envision, Code of Practice for Design and Construction of Foundations in Soils, General Requirements, 3rd Revision, Steel for General Structural Purposes, 4th Tnuyen, Methods of Test for Agrepties for Concrete, PART3 Specific Pavity, Density, Voids, Absorption and Bulking Code of Practice for Bending Gond Fixing of Bars for Concrete Reinforcement Concrete Vibrators Immersion Type, General Requirements for Screed Board Concrete Vibrators, 1st Revision, Specification for Concrete Vibrating Tables Recommended Practice for Welding of Mild Steel Plain and Deformed Bars for Reinforced Construction, 1st Tnuyen, Methods of Sampling and Test, Physical and Chemical, for Water and Wastewater, Non-Filterable Residue, Total Suspended Solids, 1st Vision, Volatile and Fixed Residue, Total Filterable and Non-Filterable, 1st Revision, 77 is 456, 1000 is no. Title is no. Title, Part 22, 1986, Part 23, 1986, Part 24, 1986, Part 32, 1988 3414, 1968 3812, 1981 395I, Part 1. 1975 403I, Part S 1988 4082, 1996 4326, 1993 4656, 1968 4845, 1968 4925, 1968 4926, 1976 S816, 1999 6061, Part 1, 1971, Part 2, 1971 6452, 1989 6461, Part J, 1972, Part 2, 1972 Acidity, 1st Revision, Alkalinity, 1st Revision, Sulfates, 1st Revision, Chloride, 1st Revision, Code of Practice for Design and Installation of Joints in Buildings Specification for Fly Ash for Use as Pozzolana and Admixture, 1st Revision, Specification for Hollow Clay Tiles for Floors and Roofs, Part 1 Filler Type, 1st Revision, Methods of Physical Tests for Hydraulic Cement, Part S Determination of Initial and Final Setting Times, 1st Revision, Recommendations on Stacking and Storage of Construction Materials and Components at Site, 2nd Revision, Code of Practice for Earthquake-Resistant Design and Construction of Buildings, 2nd Revision, Specification for Form Vibrators for Concrete Definitions and Terminology relating to Hydraulic Cement Specification for Concrete Hatching and Mixing Plant Specification for Ready Mixed Concrete, 2nd Revision, Method of Test for Splitting Tensile Strength of Concrete, 1st Revision, Code of Practice for Construction of Floor and Roof with Joists and Filler Blocks, with Hollow Concrete Filler Blocks with Hollow Clay Filler Blocks, 1st Revision, Specification for High Alumina Cement for Structural Use Glossary of Terms relating to Cement, Concrete Aggregates Materials, Part 3, 1972 Concrete Reinforcement, Part 4, 1972 Types of Concrete, Part S, 1972 Formwork for Concrete, Part 6, 1972 Equipment Tool and Plant, Part 7, 1973 Mixing, Laying, Compaction, Curing and Other Construction Aspect, Part 8, 1973 Properties of Concrete, Part 9, 1973 Structural Aspects, Part 10, 1973 Tests and Testing Apparatus, Part 11, 1973 Pre-Stressed Concrete, Part 12, 1973 Miscellaneous 6909, 1990 Specification for Supersulfate Cement 7861 Code of Practice for Extreme Weather Concreting, Part 1, 1975 Recommended Practice for Hot Weather Concreting, Part 2, 1975 Recommended Practice for Cold Weather Concreting 8041, 1990 Specification for Rapid Hardening Portland Cement, 2nd Revision, 8043, 1991 Specification for Hydrophobic Portland Cement, 2nd Revision, 8112, 1989 Specification for 43 Grade Ordinary Portland Cement, 1st Revision, 9013, 1978 Method of Making, Curing and Determining Compressive Strength of Accelerated Cured Concrete Test Specimens 9103, 1999 Specification for Admixtures for Concrete. 1st Revision 9417, 1989 Recommendations for Welding Cold Worked Bars for Reinforced Concrete Construction, J. RSTR/Lision, 11817, 1986 Classification of Joints in Buildings for Accommodation of Dimensional Deviations During Construction 12089, 1987 Specification for Granulated Slag for Manufacture Portland Slag Cement 12119, 1981 General Requirements for Pan Mixers for Concrete 78 is number 12269, 1981 12330, 1988 12600, 1989 13311 Title is No. Specification for S3 Grade Ordinary Portland Cement Specification for Sulfate Resisting Portland Cement Specification for Low Heat Portland Cement Methods of Non-Destructive Testing of Concrete, Pan I, 1992, Pan II, T992 13920, 1993 14687, 1999 is 456, 1000 Title Ultrasonic Pulse Velocity Rebound Hammer Code of Practice for Ductile Detailing of Reinforced Concrete Structures Subjected to Seismic Forces Guidelines for False Work for Concrete Structures 79 is 456, 2000 Annex B, Clauses 18.2.2, 22.3.1, 22.7, 26.2.1 and 32.1, Structural Design, Working Stress Method, 8:1 General BL.1 General Desil Requirements. The general design requirements of Section 3 shall apply to this Annex 0 to 1.2 redistribution of moments except where the simplified analysis using coefficients, C 22.5, is used. The moments over the support for any assumed arrangement of loading, including the dead load moments, may each be increased or decreased high not more than 15%, provided that these modified moments over the supports are used for the calculation of the corresponding moments in thespans. 8:1.3 Assumptions for Desil D of members in the methods based on elastic theory. The following assumptions shall be made: IL at any cross section. Plane sections before bending remain plane after bending. B. All tensile stresses are taken up by reinforcement and none by concrete, except as otherwise specifically permitted. C. The stress-strain relationship of steel and concrete, under working loads, is a straight line. D. The modular ratio M has the value 280. 30 cbc where HC is permissible compressive stress due to bending in concretine N/mm2 as specified in Table 21. Note the expression given for M Poniali takes into account long-term effects such as creep. Therefore this in is not the same Wi. The modular ratio derived BDSCD on the value of F, given in 6.2.3.1. B2 Permissible stresses B2.1 per mel. Cybal stresses in concrete. Permissible stress as for the various grades of concrete shall he taken as those given in tables 21 uno 23. Note, for increase in strength with key 6.1.1 shall be applicable. The values of permissible stress shall hen Bruinevi interpolation between the grades of concrete. B2.1.1 Direct tension for members. In direct tension, when full tension is taken by the reinforcement alone, the tensile stress shall be not greater than the values given below. F. Grad til coli at mi, M20 M2 MO M3 M40 Ti. Fut stress 1.22.02.83.23, 64.04.4 NLL NLLL M44.8 MO.2 FF. The tensile stress shall be calculate this A plus ma.T where equals F total tension on the member minus pre-L tension in steel. If any, before concreting, equals A backslash, cross-sectional area at concrete excluding any finishing material and reinforcement n, equals modular ratio, and equals a cross-sectional area of reinforcing steel in tension. And 1.1% bond stress S for deformed bars in the case of deformed bars conforming to is 1786, the bond stresses given in total May 21 be increased by 60%. 0 to 2.2 permissible stresses in steel reinforcement. Permissible stresses in steel reinforcement shall not exceed the values specified in Table 22. 8-2.2.1 In flexural members the value of 0. Given in Table 22 is applicable at the centroid of the tensile reinforcement subject to the condition that when more than one layer of tensile reinforcement is provided, the stress at the centroid of the outermost layer shall not exceed by more than 10% the value given in TOB 22. 8 to 2.3 Increase in permissible stress where stresses due to wind, or earthquake, temperature and shrinkage effects are combined with those due to dead, live and impact load. The stresses specified in Tables 21 tons 22 and May 23 be exceeded up to a limit of 33%. Wind and seismic forces need not be considered as acting simultaneously. 80 Table 21 Permissible stresses in concrete, clauses BL.3, B2.1, B2.L.2. B2.3 and B4.2, all values in anti-mml. Urade 01 Concrete, 1, M10 M15 M20 M2S M30 M35 M40 M45 M50 Permissible stress in compression bending, 2, 3.05.07.08.5 10.0 11.5 13.0 14.5 16.0 Direct, 3, 02.54.05.06.08.0 LJ.O 10.0 11.0 T2.0 Notes I. The values of permissible, shear stress in concrete are given in Table 23. 2. The bond stress given in COL4 shall be increased by 25% for bars in compression. Is 456, 2000 Permissible stria in bond, Avril, 4 plain bars in tension, 4, 0.60.8.0.91.0 B3 Permissible loads in compression members B3.1 Pedestals and short columns with lateral ties. The axial load P permissible on a pedestal or short column reinforced with longitudinal bars and lateral ties shall not exceed that given by the following equation, where equals 0 and permissible stress in concrete in direct compression equals A. Cross-sectional area of concrete excluding any finishing material and reinforcing steel. 0 equals A, equals permissible compressive stress for column bars, and cross-sectional area of the longitudinal steel. Note, the minimum eccentricity mentioned in 25.4 may he deemed to be incorporated in the above equation. B3.2 Short columns with helical reinforcement. The permissible load for columns with helical reinforcement satisfying the requirement of 39.4.1 shall be 1.05 times the permissible load for similar member with lateral ties or rings. B3.3 Long columns. The maximum permissible stress in a reinforced concrete column or part thereof having a ratio of effective column length to least lateral dimension above 12 shall not exceed that which results from the multiplication of the appropriate maximum permissible stress as specified under B2.1 and B2.2 by the coefficient C, given by the following formula, C equals 1.25 SLR48B where equals C, reduction coefficient, equals I, effective length of column, and equals B least lateral dimension of column. For column with helical reinforcement, B is the diameter of the core. For more exact calculations, the maximum permissible stresses in a reinforced concrete column or part thereof having a ratio of effective column length to least lateral radius of gyration above 40 shall not exceed those which result from the multiplication of the appropriate maximum permissible stresses specified under B.2.1 and 0 to 2.2 by the coefficient C, given by the following formula, C equals 1.25 LERIBOMIN where IMIP is the least radius of gyration. B3.4 Composite columns. A, allowable load, The allowable axial load P on a composite column consisting of structural steel or cast iron column thoroughly encased in concrete reinforced with both longitudinal and spiral reinforcement shall not exceed that given high. The following formula, 2116815/07-1281 is 456, 2000 Table 22 Permissible stresses in steel reinforcement, clauses 8 to 2.2, 8-2.2.1, B 2.3 and B 4.2, SI type of stress in steel no. Reinforcement mild steel band conforming to grade I of is4J2, Pan I, permissible stresses in N/mm2 medium tensile steel conforming to is432, Port 1, high yield strength deformed bars conforming to is1786, grade FE41s, L, L2, I, tension, 0.1 or 0.11, A, LJP, 0 and including I, 3, 4, half the guaranteed, 5, 230 20 mm 140 yield stress subject to a maximum of 190 B, over 20 ROM 130 232, compression in column 130 billion Argentine pesos, all, 130 193, compression in bars in a beam, or slab when the compressive resistance of the concrete is taken into account. The calculated compressive stress in the surrounding concrete multiplied by 1.s times the modular ratio or 0, whichever is lower for, compression in bars in a beam or slab where the compressive resistance of the concrete is not taken into account, A, up to and including I half the guaranteed 190 20 mm 140 yield stress subject to a maximum of 190 B, over 20 mm 130 J90 notes 1 for high yield strength deformed bars of grade FE. So the permissible stress in direct tension and flexural tension shall be OJ.F. The permissible stresses for shear and compression reinforcement shall be as for grade FE 415. 1 for welded wire fabric conforming to is156 FL, the permissible value in tension CJIII is 230 nzmm. 3 for the purpose of this standard, the yield stress of steels for which there is no clearly defined yield point should be taken to be 0.2% proof stress. 4 when mild steel conforming to grade 2 of is432, part I, is used, the permissible stresses shall be 90% of the permissible stresses in COL3, or if the design detail shall already been worked out on the basis of mild steel conforming to grade I of is432, Pan I, the area of reinforcement shall be increased be 10% off that required for grade I steel. Where equals, JCC permissible stress in concrete in direct compression, at equals net area of concrete section, which is equal to the gross area of the concrete, J equals section, A, M, IC permissible compressive stress for column bars, A equals cross-sectional area of longitudinal bar, dot reinforcement, equals, JMA allowable unit stress in metal core, not to exceed 125 N/mm2 for a steel core, or 70 N/mm2 for a cast iron core, and equals MP cross-sectional area of the steel or cast iron core B, metal core and reinforcement. The cross-sectional area of the metal core shall not exceed 20% of the gross area of the column. If a hollow metal coat is used, it shall be filled with concrete. The amount of longitudinal and spiral reinforcement and the requirements as to spacing of bars, details of splices and thickness of protective shell outside the spiral, shall conform to requirements of 16.5.3. A clearance of at least 75 mm shall be maintained between the spiral and the metal core at AJL points, except that when the core consists of a structural steel H column, the minimum clearance may be reduced to 50 mrn. C. Splice sand connections of metal cores. Metal cores in composite columns shall be accurately milled at splices and positive provisions shall be made for alignment of one core above another. At the column base, provisions shall be 82 is 456, 2000 made to transfer the load to the footing at safe unit stresses in accordance with 34. The base of the metal section shall be designed to transfer the load from the entire composite columns to the footing. or it may be designed to transfer the load from the metal section only. Provided it is placed in the pier or pedestal as to leave ample section of concrete above the base for the transfer of load from the reinforced concrete section of the column by means of bond on the vertical reinforcement and by direct compression on the concrete. Transfer of loads to the metal core shall be provided for by the use of bearing members, such as billets, brackets, or other positive connections. These shall be provided at the top of T.E metal core and at intermediate floor levels where required. The column as a whole shall satisfy the requirements of formula given under A. At any point, in addition to this, the reinforced concrete portion shall be designed to carry, according to A 3.1 or B 3.2 as the case may be, all floor loads brought into the column at levels between the metal brackets or connections. In applying the formulae under B 3.1 or A to 3.2, the gross area of column shall be taken to be the area of the concrete section outside the metal core, and the AJ allowable load on the reinforced concrete section shall be further limited to 0.28 tk times gross sectional area of the column. D. Allowable load on metal core only. The metal core of composite columns shall be designed to carry safely any construction or other loads to be placed upon them prior to their encasement in concrete. B4 members subjected to combined axial load and bending 8 to 4.1 design based on unacted section. A member subjected to axial load and bending, due to eccentricity of load, monolithic construction, lateral forces, etc., shall be considered safe provided the following conditions are satisfied: AA, CT, Cal plus, 1 CHC Cal 1 ACE 0 CVC where ACL equals calculated direct compressive stress in concrete, TCEACHFAAL equals permissible axial compressive stress in concrete, equals calculated bending compressive VE stress in concrete, and equals permissible bending compressive stress in concrete. B. Tile resultant tension in concrete is not greater than 35% and 25% of the resultant compression for biaxial and uniaxial bending respectively, or does not exceed 3/4, the 7-day modulus of rupture of concrete. Notes 1A equals LU1A. P plus 1.5 Ma. For column swifties where P.A and A, defined in B 3.1 and M is the modular ratio. ZM2OL.HUIII: where M equals the moment and Z equals modulus of section. In the case of sections subject to moments in two directions, the stress shall be calculated separately, not added algebraically. 8 to 4.2 design based on crack section. If the requirements specified in 8 to 4.1 are not satisfied, the stresses in concrete and steel shall be calculated by the theory of crack section, in which the tensile resistance of concrete is ignored. If the calculated stresses are within the permissible stress specified in tables 21, 22, and 23, the section may be assumed to be safe. Note the maximum stress in concrete and steel may be found from tables and charts based in the cracked section theory or directly by determining the no stress line, which should satisfy the following requirements: A. The direct load should equal to the algebraic sum of the forces on concrete and steel. B. The moment of the external loads about any reference line should be equal to the algebraic sum of the moment of the forces in CA and CRD, ignoring the tensile force in concrete and steel about the same Li. And C. The moment of the external loads about any other reference lines should be equal to the algebraic sum of the mol neft1 of the forces in concrete, ignoring the tensile force in concrete and steel about the same line. B 4.3 members subjected to combined direct load and flexure. Members subjected to combined direct load and flexure and shall be designed by limit slate method as in 39.5 after applying appropriate load factors as given in table 18. BS shear BS.L nominal shear stress. The nominal shear stress R in beams or slabs of V uniform depth shall be calculated by the following equation: TV equals V bell, where V equals shear force due to design loads. 83 is 456, 2000 equals B. Breadth of the member, wick for flanged sections shall be taken as the breadth of the web, and D equals effective depth. BS.L.1 beams of varying depth. In the case of beams of varying depth, the equation shall be modified as V plus or minus mlanf JF equals VBDD, where TYV, band D are the same as in B 5.1, M equals bending moment at the section, and equals angle between the top and the bottom edges of the beam. The negative sign in the formula applies when the bending moment M increases numerically in the same direction as the effective depth D increases, and the positive sign when the moment decreases numerically in this direction. Or 8 to 5.2 Design shear strength concrete 8s.2.1 The permissible shear stress in concrete in beams without shear reinforcement is given in Table 23. Bs.z.L.1 For solid slabs the permissible shear stress in concrete shall be Kfc where K has the value liven below, Obmal depth 300 AR 275 2SO 22s 200 175 150, 1 off slab, more less K 1.00 1.05 1.10 1.1s 1.20 1.25 1.30 Note this does not apply to L1AT slabs for which 31 shall apply 8-5.2.2 Shear strength of members under axial compression for members subjected to axial compression P The permissible shear stress in concrete Tc given in Table 23, shall be multiplied by the following factor, equals 1 plus but not exceeding 1.5 A.FCK where P equals axial compressive force in N, A, equals gross area of the concrete section in M, and IE equals characteristic compressive strength of concrete. 8-5.2.3 With shear reinforcement When shear reinforcement is provided the nominal shear stress Fc in beams shall not exceed Fc. Given in Table 24. Table 23 Permissible shear stress in concrete, clauses B2.1 B2.3, 8 to 4.2, 8-5.2.1, BS.2.2, BS.3, BS.4, 8.5.5.1, 8.5.5.3, B6.2. B6.3.3 and 8-6.4.3 and Table 21. L00BD Permissible shear stress in concrete, TCN/MMJ grade of concrete Miss M20 M2S M30 M3S M40 and above, I, 2, 3, 4, S, 6, 7, SO.IS 0.18 0.18 0.19 0.20 0.20 0.20 0.25 0.22 0.22 0.23 0.23 0.23 0.23 O.SO 0.29 0.30 0.31 0.31 0.31 0.32 0.7 S 0.34 0.3 S 0.36 0.37 0.37 0.38 1.00 0.37 0.39 0.40 0.41 0.42 0.42 1.25 0.40 0.42 0.44 0.45 0.45 0.46 1.50 0.42 0.45 0.46 0.48 0.49 0.49 1.7 0.44 0.47 2.00 0.44 0.49 0.49 O.SO 0.52 0.52 O.SI 0.53 04 O.SS 2.25 0.44 0.512.S 0.44 0.510 0.55 OS 0.S706 0.570 SA 0.602.7 S 3.00 and above 0.44 0.51 0.44 O.S 0.56 0.580 S7 0.60 0.60 0.62 0.61 0.63 Note A is the terrier of longitudinal tension reinforcement which continues at least on effective depth beyond the Lettian Beatty I considered except at support where full area of tension reinforcement may be used provided. Theta 1 in confot mel to 26.2.2 and 26.2.3. 84 8-5.2.3.1 For slabs, T shall not exceed half the value Y of Ft mal given in Table 24. BS.3 Minimum shear reinforcement when Ty is less than Tc given in Table 23. Minimum shear reinforcement shall be provided in accordance with 26.5.1.6. B5.4 Design of shear reinforcement when TV exceeds T, given in Table 23, shear reinforcement shall be provided in any of the following forms: A. Vertical stirrups, B. Bent up bars along with stirrups, and C. Inclined stirrups. Where bent up bars are provided, their contribution towards shear resistance shall not be more than half that of the total shear reinforcement. Shear reinforcement shall be provided to carry a shear equal to VTC.BD. The strength of shear reinforcement V shall be calculated as below: A. For vertical stirrups V equals OSV ASV DSSVH, for inclined stirrups or a series of bars bent up at different cross sections, equals C1 SVVD, sin A plus COSA, SVC, for single bar or single group of parallel bars, all bent up at the same cross section, where ASV equals GV ASV SI dex equals total cross-sectional area of stirrup legs or bent up bars within a distance, Y equals spacing of the stirrups or bent up bars along the length of the member, equals TC design shear strength of the concrete, B equals breadth of the member, which for flanged beams, shall be taken as the breadth of the web BWT equals JY permissible tensile stress in shear reinforcement, which shall not be taken is 456, 2000 greater than 230 N/Mn12, X equals angle between the inclined stirrup or bent up bar and the axis of the member, not less than 45 U, and D equals effective depth. NF, TE where more than one type of shear reinforcement is used to reinforce the same portion of the beam. The iota shear resistance shall be computed as the sum of the resistance for the various types separately. The area of the stirrups shall not be less than the minimum specified in 26.5.1.6. 8 to 5.5 Enhanced shear strength of sections closed to supports. 8s.5.1 General shear failure at sections of beams and cantilevers without shear reinforcement will normally occur on plane inclined at an angle 30 to the horizontal. If the angle of failure plane is forced to C inclined more steeply than this I because the section considered, X, in Fig 24 is close to a support or for other reasons, the shear force required to produce failure is increased. The enhancement of shear strength may be taken into account in the design of sections near a support high, increasing design shear strength of concrete, to 2dr/A. Provided that the design shear stress at the face of support remains less than the values given in Table 23. Account may be taken of the enhancement in any situation where the section considered is closer to the face of a support of concentrated load than twice the effective depth, D. To be effective, tension reinforcement should extend on each side of the point where it is intersected high a possible failure plane for a distance at least equal to the effective depth, or be provided with an equivalent anchorage. 8-5.5.2 Shear reinforcement for sections closed to supports. If shear reinforcement is required, the total area of this is given by, equals AAVB, FV2DF job, /0.87 phi 0.4 AVB/0.RF. This reinforcement should be provided within the middle 3/4 of AVU where QV is less than .L. Horizontal shear reinforcement will be more effective than vertical. Concrete grade /MN/MM1M, 1.6 Table 24 Maximum shear stress, ARMA. N/MM1, clauses 8-5.2.385.2.3 T, 85.5,1 and B6.3.1, M20 M2 MJO 1.81.92.22. J140 and above 2.585 is 456. 2008-5.5.3 Enhanced shear strength near supports, simplified approach, V equals shear, T equals torsional moment, and the procedure given in DS.S.L and 8-5.5.2 may be used for all beams. However, for beams carrying generally uniform load or where the principal load is located further than 2D from the face of support, the shear stress may be calculated at a section a distance D from the face of support. The value of Tc is calculated in accordance with Table 23 and appropriate shear reinforcement is provided at sections closer to the support. No further check for such section is required. B equals breadth of beam. the equivalent nominal shear stress, yet in this case shall J be calculated as G yen in B5.1, except for substituting V by VE. The values of 1 VC shall not exceed the values of C max given in Fable 24. B6.3.2 if the equivalent nominal shear stress Ri does not exceed Fe given in Table 23. Minimum shear reinforcement shall be provided as specified in 26.5.1.6. 8-6 torsion 8-6.1 general 8-6.3.3 if 1 yet exceeds 1 given in Table 23, both longitudinal and transverse reinforcement shall be provided in accordance with B6.4. In structures where torsion is required to maintain equilibrium, members shall be designed for torsion in accordance with 8-6.2, 8-6.3, and 0-6.4. However, for such indeterminate structures where torsion can be eliminated by releasing redundant restraints, no specific design for torsion is necessary provided torsional stiffness is neglected in the calculation of internal forces. Adequate control of any torsional cracking is provided by the shear reinforcement as per BS. Note the approach to design in this clause for torsiones as follows: torsional reinforcement is not calculated separately from that required for bending and shear. Instead, the total longitudinal reinforcement is determined for an fictitious bending moment which is a function of actual bending moment and torsion. Similarly, web reinforcement is determined for a fictitious shear which is IL function of IL till shear and torsion. 8-6.4 reinforcement in members subjected to torsion. B6.4.1 reinforcement for torsion, when required, shall consist of longitudinal and transverse reinforcement. B6.4.2 longitudinal reinforcement. The longitudinal reinforcement shall be designed to resist an equivalent bending moment, MRL, given by where MEL: M plus MRM equals bending moment at the cross section, and J plus D/B, M equals T1.7 where T is the torsional L moment, D is the overall depth of the beam and B is the breadth of the beam. 8-6.1.1 The design rules laid down in 8.6.3 and 8-6.4 shall apply to beams of solid rectangular cross-section. However, these clauses may also be applied to flanged beams by substituting BW for B, in which case they are generally conservative, therefore specialist literature may be referred to. B6.2 Critical sections located less than a distance d from the face of the support may be designed for the same torsion as computed at a distance d, where d is the effective depth. B6.4.2.1 If the numerical value of m as defined L in 8-6.4.2 exceeds the numerical value of the moment mt, longitudinal reinforcement shall be provided on the flexural compression face, such that the beam can also withstand an equivalent moment mt2 given by equals may mlm, the moment me2 being taken as acting in the opposite sense to the moment m. 8-6.4.3 Transverse reinforcement. Two-legged closed hoops enclosing the corner longitudinal bars shall have an area of cross-section A.y given by B6.3 shear and torsion. B6.3.1 Equivalent shear, VE shall be calculated from the formula, V equals V plus 1.6 TB where equals equivalent shear, V equals ATS, plus VSVT but the tota I bid, J2.5 D1, JV transverse reinforcement shall not be less than, TB. TC, B.SYA.V where T equals torsional moment. Equals V shear force. 86 equals S spacing of the stirrup reinforcement, V equals high center to century distance between corner bars in the direction of the width, RI. Center to century distance between corner bars in the direction of the depth, B breadth of the member, is 456, 2000, V equals per in ISSI BTC NSI1 ESTRC Sinchi AR reinforcement, equals T equivalent shear stress as specified in \, 8-6.3.j, and T \ equals shear strength of the concrete T's specified in Fable 2387 is 456, 2000 Annex C, Clauses 22.3.2, 23.2.1, and 42.1, Calculation of deflection COL total deflection CI.L Total deflection shall be taken as sum of the short-term deflection. determined in accordance with C2 and the long-term deflection, in accordance with C, and C4. C2 short-term deflection. C2.1 The short-term deflection may be calculated by the usual methods for elastic deflections using the short-term modulus of elasticity of concrete, E, and an effective moment of inertia left given by the following equation, I, where I equals moment of inertia of the crack section, equals for Im, cracking moment, equal to where Yti is the modulus of rupture of concrete, Ig is the moment of inertia of the gross section about the centroidal axis, neglecting the reinforcement, and E is the distance from centroidal axis of gross section. Neglecting the reinforcement, to extreme fiber in tension. M equals maximum moment under service loads, Z equals lever arm. R equals depth of neutral axis. D equals effective depth. BW equals breadth of web. And equals B breadth of compression face. For continuous beams, deflection shall be calculated using the values of it lit and M are modified by the following equation, XE equals K11 plus 2XL plus, I, KL, XO where equals XE modified value of X, 11XL equals values of Z at the supports, equals 12 value of X at mid-span, equals K, coefficient given in table 2s, and equals X value of it I or MR as appropriate. C3 deflection due to shrinkage. C3. The deflection due to shrinkage A may be computed from the following equation, AE equals K3YCS12 where K is a constant depending upon the supon conditions, OS for cantilevers, 0.125 for simply supported members, 0.086 for members continuous at one end, and 0.063 for fully continuous members. Equals TV, E is shrinkage curvature equal to K where FEA is the ultimate shrinkage strain of concrete, set 6.2.4. Equals K 0.72 XPS 1.0 for 0.25 SPPC 1.01, equals 0.65 x1, S 1.0 for PI, R, 1.01, Table 2's values of coefficient K, clause C 2.1, 0.5 or less 0.6 0.7 0.8 0.9 1.0 JI 1.2 1.3 1.40 0.03 0.08 0.16 0.30 0.50 0.73 0.91 0.97 1.0 asterisk 1 note, is given B where equals MIM. Support moments. Lind equals MF. M dot. Lixt end momenta. 88 where P equals and P equals BDC BD and D is the total depth of the section, and I is the length of span. C4 deflection due to creep. C4.1 The creep deflection due to permanent loads may be obtained from the following equation, LC, FICI2, is 456, 2000 where AI.cc, PMN, equals initial plus creep deflection due to permanent loads obtained using an elastic analysis with an effective modulus of elasticity, equals ECE. 1 plus 89 being the creep coefficient, and equals AI.ERM, short-term deflection due to permanent load using EC 2116 818/07-1389 is 456, 2000 Annex D, clauses 24.4 and January 2, 37, slabs spanning in two directions OI restrained slabs 1.0 when the comers of a slab are prevented from lifting, the slab may hit signed as specified in DI.L to DL.11. D1.1 The maximum bending moments per unit width in a slab are given by the following equations, U, equals AXWI, X, WLX2 where U and Xi are coefficients given in TABLE26, equals W total design load per unit area, equals M, my moments on strips of unit width spanning I and Li respectively, and I, and E equals lengths of the shorter span and longer span respectively. DL.2 slabs are considered all divided in the direction into middle strips and edge strips as shown in Fig 25, the middle strip being 3/4 of the width and each edge strip 1/8 of the width, 0 to 1.3 the maximum moment, Calculate this in 0.1.1. Apply only to the middle strips and no redistribution shall be made. 1.4 Tension reinforcement. Provide that midspan in the middle strip shall extend in the lower part of the slab to within 0.25 I of a continuous edge, or OJ5 LOF a discontinuous edge. 0 to 1.5 Over the continuous edges of a middle strip, the tension reinforcement shall extend in the upper part of the slab a distance of OJ5 from support. And at least 50 perk ENT shall extend a distance of 0.3 IDI.6 at a discontinuous edge. Negative moments may arise. They depend on the degree of fixity at the GE of the slab. In general, tension reinforcement equal to % of that provided at midspan. Extending 0.1 I into the span will be sufficient. DT.7 Reinforcement in edge strip, parallel to that edge, shall comply with the minimum given in section 3 and LHP. Requirements for torsion given in DT.S to 1.10. DUI torsion reinforcement shall be provide that any corner where the slab is simply supported on both edges meeting at that corner. It shall consist of top and bottom reinforcement, each with layers of bars placed parallel to the sides of the slab and extending from the edges a minimum distance of 1/5 of the shorter span. The area of reinforcement in each of these 4 layers shall be 3/4 of the area required for the maximum midspan moment in the slab. 0 to 1.9 Torsion reinforcement equal to half that described in DT.S shall be provided at a corner contained by edges over only one of which the slab is continuous. DL.2 Torsion reinforcements need not be provided at any corner contained by edges over both of which the slab is continuous. VD 1.11 Torsion I is greater than 2, the slabs shall be designed as spanning one way. 0 to 2 Simply supported slabs. DZ.1 When simply supported slabs do not have adequate provision to resist torsion at corners and to prevent the corners from lifting, the maximum R_T, T, I, LRLLITII MIOALE strip -S toy II1E0 G.1 first. MIOOLISTRP plus, III1OJ Li JJL25A for span 258 for span PIO. 25 Division of slab IN1 UMIDLLE and EOOE strips 90 is 456. 2000 Table 26 Bending moment coefficients for rectangular panels supported on 4 sides with provision for torsion at corners, CLA.FCSDJ.1 ALIT 24.4. 1. Case type of panel and no. Nominals calculated, I, 2, interior P, /. Negative moment at continuous edge positive renornentat en lid span. 1.0, 3, 0. 32 0.024 1.1, 4, 0.037 0.028 short span, Ambient 5 fluid, values or 1,11. 1.2 1.3, 6, 1.4 1.5, 7, 8, 0.04 J0, 47.0.OS 10.032, LOJ60.OJ9 0.053 0.04121 Slulrel ETIJ, E continuous, negative moment at continuous edge O.OJ7 positive moment at midspan O.FL28 0.04 J0.OJ2, UL480, IO, H6 0.019 0.055 0.041, L.057 0.044 on LTMETINT discontinuous, negative moment at continuous edge O.CN7 0.044 OJL2 N.OS1 0.063 OOLL67 positive moment at midspan, 02H 0.03 JN, J9, J, 44 0.047 OJ51 1.75, 9. 0.060 0.045 0.064 0.048 0.077 length span coemiclinelt, L, 4. All values of 2.UI. CLO, 2, 0.065 0.049 0.032 0.024 0.06 and 0.037 0.052 0.028 0.0850 65 07 0.02842 Oiled edges discontinuous, negative moment at continuous edge 0.047 positive moment. And 1 null span O, and 2 short et je/g/2 iophias, and C a tipped moment at continuous edge n.045 positive moment at midspan, dot, n, 2/iighd, dot. Discontinuous, negative moment at continuous edge positive moment at midspan, un 711, comma, 1 titt backslash, ifmt, nulili alt l.oll. EDG continuous negative moment at continuous edge pn /lift moment at il lidsilin 0.0570.04 jxthrceii, t dit, lilt, o. Jill shore edge, connuous, negative moment at en unuous edge positive moment at, dspan, .tl49foi at ji. Discontinuous, pll /idiful moment at midspan, dot, 0.05 j 0.0400, 49, dot, 70.04 j n.064 n.04 sooi 0,064, ul 600, 40.oesn.n710, 4j, .oj 0.075, .060.0520.n56 0.040 0.043 0.059 0.044 0.060 0.045 0.051 0.057 0.63 0.068 0.071 0.070 ljo.uso 0.0510.flow 0.084 n.064, .09, L, XL 0.071 0.076 0.072 0.079 0.08 S 0.089 0.084 0.063 0.065 0.049 0.080, dot, L, J 0.069 0.087 0.100 0.091 0.069 0.069, U, 20.08 ROJ, 0.073 0.096 0.107 0.047, .NO, JO, 4, .CN 0.043. O, 70.04. 0.06 moments per unit width arc given by the following equation, I, equals mx my a, equals ay, /, where m, mv91.l are same /s those in di.l, /yi and ux and ay are moment coefficients given in table 27 d2.i.la, t least 50% of the tension reinforcement provided at midspan should extend to the supports. The remaining 50% should extend to within 0.12 or 0.1 li of the support. As appropriate. Table 27 bending moment coefficients for slabs spanning in two directions at right angles, simply supported on four sides T closk D2.1, 1/1, 1.0 1.1 I. 1.3 1.4 I 1.7 2.0 AO, 62 0.074, 84 0.09 JO, L, 90.1040.US, L.IIS, 40, L620.0610.OSL, .O.OS, 0.046 N.07 0.0292.50 0.122 VO 0.124, LO1491 is 456, 1000 Annex E, CLMU 25.2, effective length or columns E.L in the absence of Marigzic analysis. The effective E.2 to determine whether a COL /JIDD is IDO's way or length of columns in from structures may be obtained a sway column, Stability index may be computed U from the ratio of effective length to unsupported length given below, etl. Given in Fis.26 when relative displacement of the ends of the column is prevented and in Fil. 26 when relative lateral displacement of the ends is equals prevented. In the latter case, it is recommended that, where the effective length ratio 1:11 may not be taken to be d bum of axial loads on all column in the less than 1.2 story, equals a analytically computed first order lateral notes 1 apria 26 and 27 are reproduced from the structural in ADCCJ number 7, volume 52, July 1974 by the Penilio of the Council of the Institutio de of Structural on Payane, UK UIC 2 in Pip. 26 and 27.1 liters. UD3L equal to XC plus B deflection, equals H total latera 1 for C actidal within theatory, and H equals height off the story. If QS 0.04 then the column in the frame may be taken as no sway column, otherwise the column will be considered as sway column. Where the lummatio D is to be done for the membrane frame in into joyat at top and bottom respectively, and KC and K bane, the flexural stiffness for column and beam respectively. £3 for normal usagiles suminel idealized conditions. The effective length I of in a given plane may be assessed on the basis of table 28. Hinged 10. W, I fixed D3, M, flow. 26 FNVLB Nant ratios poi a column in a prami. WRRH nose way 92 hinged 1.0 is 456, 2000 0.7 tons 0.62 plus underscore ROS, plus plus 1 0.30.20.1 fixed 000.1 CW, U, 0.20.3 hinged. 0.5 0.6 0.7 0.8 0.9 1.02 flow. 27 EFFF, IV length RI /TOS for a column in a frame without restri /int against sway 2116 BISL 07-14 is 456, 2000 Dean 01 EDD Ran Elm 01 Com. Lawn membrane, I. Effectively held in position and retrained against rotation in both ends. BFT actively held in position at both ends. Retrained against rotation at Onind 18 W.28 Mead. Liot Belcom. Manaben, CO number 3, N. Oleal V. Liotol, 2, 3, I 0.501 I 0.701 effectively held in position at both ends. But not restrained against rotation i.e. effectively held in position and retrained against rotation at one end. And lit the other restrained against rotation but not held in position effectively held in position lield restrained against rotation in Onind, and at the other pertlally restrained against total but no held in position. Effectively held in position lit Onind but not N1 trained against rotation, lield at theater and rathunt and epilesti rot8 lion but not held in position effectively held in position lied trained against rotation at one end but not held in position normed 9 against rotation lit the auth crond L note I is the lias liported /enethoph C omp mayan member. UIO I 1.00 I 2.00 I 2.00 I.L.V.L, A underscore L.U. E, T.L, 4, 0.6510.1011.00 I 1.2012.5012.0012.00194 Annex F, Clause 3.5.3.2 and 43.1, calculation of crack width is 456, 2000 provided that the strain in the tension reinforcement is limited to 0.8 F/eta d subsurface cock width, which should not exceed the appropriate value given in March 2, 35 may be calculated from the following equation: design surface crack width where equals a, distance from the point considered to the surface of the nearest longitudinal bar, equals C minimum cover to the longitudinal bar, equals M average steel strain at the level considered, H equals overall depth of the member, and equals X depth of the neutral axis. The average steel strain M may be calculated on the basis of the following assumption: the concrete and the steel are both considered to be fully elastic in tension and in compression. The elastic modulus of the steel MB taken as 200 kN/mm2 and the elastic modulus of the concrete is as derived from the equation given in 6.2.3.1 both in compression and in tension. These assumptions are illustrated in Fig. 28. Where equals h the overall depth of the section, equals x the depth from the compression facet to the neutral axis, I equals the maximum compressive stress in the concrete, T equals the tensile stress in the reinforcement, and equals E the modulus of elasticity of the reinforcement alternatively. As an approximation, it will normally be satisfactory to calculate the steel stress in the basis of a crack section and then reduce this by an amount equal to the tensile force generated by the triangular distributions. Having a value of 0 at the neutral axis and a value at the centroid of the tension steel of LOL/mm2 instantaneously, reducing to 0.55 N/mm2 in the long term, acting over the tension zone divided by the steel area. For a rectangular tension zone, this gives B, Hx, Ax, pound m equals 1 pound, 3E.A, dx where equals A area of tension reinforcement. B equals width of the section at the centroid of the tension steel. Equals 1 pound strain at the level considered. Calculated ignoring the stiffening of the concrete in the tension zone. Equals a distance from the compression facet to the point at which the crack width is being calculated. And equals D effective depth. IHA section crack/EEIE strain ST88 in CONCFETE1NZ in short term OSS high 2 in long term stress Fig 2895 is 456, 2000 Annex G, CL GU 38.1. Moments of resisted.NCE for rectangular and T sections GO. The momenta of Rossi stands of rectangular and exceeds the IL/MIT/LIL value, MU compare lon T Chanel bailed on I. Lona of 38.1 area even reinforcement may be obtained from the following, in this annex. Equation, GL rectangular sections GL.L sec lo M without comprelateral enforcement the momerite of resistance of rectangular section. Without compression reinforcement should be obtained as follows: A. Determine the depth of neutral axia from the following equation, 30.879 ASCD 0.36 kkb.db, if the value of sold is less than the limiting value, see note below 38.1, calculate the moment of resistance by the following expression, DLL, equals mu 0.875 L, a stir, dfec C, if the value of sold is equal to the limiting value. The moment of resistance of the section is given by the following expression, equals, BD mu tum 0.36 sud. Ma x, 1 minus 0.42 sud, ma x2 jek hor mu mi I16 mdr lame uing I.L, f comedy sil strel in compare. Lion reinforcement corresponding to a strain of 0.0035, su mu d. Su mu where su. Gae ni the limit in L value of su from 38.1 equals AI and, area of comp E8CO reinforcement, and D equals depth of compression reinforcement from compression face. The total area of tension reinforcement shall be obtained from the following equation, where A equals A1 plus A1 T2A, area of the total tensile reinforcement equals LAM1 area of the tensile reinforcement for a singly reinforced section for MG and equals F8. A li IE, I 0.871. ID, if SU ID is greater than the limiting value, the section should be redesigned. In the above equations, equals SU depth of neutral axis, equals D effective depth, equals T.Y characteristic strength of reinforce. Ment, a lit equals area of tension reinforcement. Equals T, characteristic compressive strength of concrete. B, width of the compression face. GZ flanged section G2.1 for Su Doctor. The moment of resistance may be calculated from the equation given in GL.1 G2.2. The limiting value of the moment of resistance of the section may be obtained by the following equation when the ratio Doctor ID does not exceed 0.2, 36, 1 to 0 mu equals 0 D42 Sud max, GKBWD2 DPT, plus 0.4 spec, BFBW, DF, mu.ln, limiting moment of resistance of a section without compression where reinforcement, and equals Su, 2 limiting value of Su from 39.1. GL.2 section with compression reinforcement mu where ultimate moment of resistance of section mu. OSU.MTAID and C are same as in GL.1. Equals B breadth of the compression face / flange, I equals BW breadth of the web, and D equals thickness of the flange. 96 is 456, 2000 GZ.Z.I when the low drive / L exceeds 0,2, the moment of resistance of the section may be calculated by the following equation, /ek mil equals 0.36 Su, I. 1 to 0.42 Su Lichel BWD2 plus 0.45 HK, BRHW, year, DT, where, equals, 0, JSU plus 0.65 D dot, but not greater than D, and the other symbols or main I1S in 0 to 1.1 N and DGZ.2. 0 Z.3. For X high U underscore XDJ, the moment of resistance mu E be calculated by the equation given in GZ.2 when J, 9 does not exceed 0.43 and AZ.2.1 when N/XLIXVEDS 0.43. In B, auth came substitute NG Suma underscore New York Su is 456, 2000 Annex H, forward, COMMI1TEE Composman Cement and Concrete Sectional Committee, CBD2 Sitguy. 3 HCA of Isyalia CIB, 0.15 DT0 ml, 63. Mal IB. 560,003 DRSC Alu Alia Shri Gr Barn Kai Shri T Antawadi DRD Gosh, Alma, CTUEPBNOIMD, I, Ashan, Subsurintendent Obnoinia, I, SCLS, Alt 17 UI1, Chiap Ginber, Naveo Dam Superintending Gnoinier, QCC, Alt, Chief Inoanai, Rubsilat Kumdalib Toll, Rubsearch OPFICA, Concurs T Boinalui, Al IIUJI, Director Joint DLRBCTOR, Al NTI.I, DLRECIOR, CMDD, N&W, Deputy Director, CMDD, NWITS, ALTMTLI. She. KH Ganaul Shri Vipa 1 Ta 8H1, Alar Lul, SHIIVK Gon Kate Shri S Golna 11 I Shil R. Tamale Kaitan, AIIMTAI. Shil SK Guha Thakata SHIIS Sanklanarayanan, Al, E, Shit, NSBHALDRI. Shad Masua, A/MTLT, Shri NC Jain Joint Glukroa Standards, 8 and 5, CBI, Joint D Standards, 8 and 5, CB2, Alicia.comma. Shi ing Joshi Shil DKM.ua, A, SHIIDK Kananushi.B.R. MI. And NA, AI.comma. Shitty Peeklshnamumdi SHIIS Chadabama, AII 17 Tayat, or AG Madhairao SHIIK Mani, 8 Rui, Shiij.suup Shi. Pajul.akome Shi PP Nair, A Mat, Bo Shiite A Quayignation Teklo LOL, Limited Pulk The Associated Cement Companies Ltd, Mumbai Central Public Work. Department, New Delhi Sardar Sovar Narman Nipm Ltd Gond by Dapril Nilation and Power Roll 8 RH Institute. Amritar AP Engineering Research Labo ILL Oriel, Hyderabad Central Water Commission, New Delhi Hyderabad Industries Limited Hyderabad Stun Electoral and Adhering Research Center, CSIR. Ahaziabad The India Cementa Ltd, Chennai AOD Dunkerley. CO Limited Mumbai Cetrol Sugati, Rayardalnel Teacher, CSIR. Rurbi Cement Corporation of India. New Delhi Reset Arth. Dia. CL Stadirti Orpnal Zidua, Ministry of Railway, Lucknow Indian Hume Pipes Co Limited Mumbai Nashodal Tel House, Calcualinan and Tubro Limited. Mumbai Struct Lyre in Linearinel Research CCNN, CSIR, Chennai Hoipalal Services CODLC, Corporation, LAC IIA, Ltd, New Delhi Ministry of Surface Tumspod, Depunent of Surf. Trinapalt, Roadswood, New Delhi, Kali Aj till FLGI 99, C Tiratil D/TTL PAL 98, MMBCRJMDT Spldave Diishioi, Oval, Alt, comma, Sri Skanathani. So IDRAS00ILBB, Alt L7 idled, SKIISS Spluia SMA. Satandai Kumar, Alt Mat, SHIIYRPU. SMRIA.K. Shalma, AI, de CRAJICUNLDRK Mohan, ALRNA, Shi Ramdas 8HRIRC Sharma, AII Mal, SMRISA Riddhi SHIIJS Sano Akriya SMRL. NA Orwell, A.LT Null, SH1.V Bkadich SHIIN Chandrasbikayan, Alt Renat, Su, Entendino Inoanibra, Disan, Expconvi Inoanir, S.M.R.Dlblotion, Alt Te, Shore AK Chata Shri JR Sil Alt NAT, DRHC Visibes Varayashi. DC Shaturvdi, All None, Shil Vinod Kume Director, Civ N. is456, ZOOORPJNTLLLL Central Board of Eruption and Power, New Delhi Engineer Inihai FL Branch, Army Headquarters, New Delhi Central Road Research Institute, CSIR, New Delhi Indian Roads Conlel, New Delhi National Council Forcement and Suildan. Materials, New Delhi Directorate 0 Enara IOF Supplies and Disposal, New Delhi Omo DLDA Ltd Mundal Geololica 1 Survey of India CAI Uta Central Soiland Material. Reared / Station New Delhi Public Works Department, Government of Tamil Nadu. Chennai Hindustan Prefab Limited New Delhi The Institution of Engineers, India, Calcutta Director General. 8 IS, Exeld Ficio Ember, CLLFTV. DRC Ralcomate. M. SHIIVKGHAN8KAJL Shat. SA Riddhi Shat, JOSB Kurian DRAK Mitral DRS.C.Mam DRN. Kumar, Alternat, Prop AK Jain DRV. Thlubinodam Ember Eskritler, E.F. Shri JK Prasad ADDL Director, Civ. Dis Shri Sanjay Pant Deputy Director, Civ English, Dis Panel for Revision of Design Codes National Council for Cement and Building. Materials, Bala Barb Structural Engine Sarana Research Center Ghaziabad Gammon India Ltd. Mumbai Central Public Works Department, New Delhi Central Public Works Department. New Delhi National Council for Cement and Building Materials. Balabgarh University of Roorkee, Roorkee School of Planning and Architecture, New Delhi, continued on page 1, 0, 99 is456, 2000 T continued from PDF: 99, MTMBTR.F SNU ODIDRC Rajkumar Special Ad Hoc Group for Revision of is456, CTWVTNTR Drive HC65 Veeps Varia Chandrine OTITH Crow 14, 6364 Nless None, Bonplor 560 Right Prefelteleng Gammon Indio Ltd, Muulbay Einran QL Council Forcement and Building Duranellar, Rollenroom Jipern 211685/2007-10000. 100 Bureau of Indian Standards. BIS is a statutory institution established under the Bureau of Indian Standards Act, 1986 to promote harmonious development of the activities of standardization, mark and quality certification of goods and attending to connected matters in the country. Copyright Bishast copyright of all its publications. No part of his publications may be reproduced in any form without the prior permission in writing of 81s. This does not preclude the free use, in the course of implementing the standard, of necessary details, such as symbols and sizes, type, or grade designations. Inquiries relating to copyright be addressed to the Director, Publications, BIS. Review or Indian standards amendments are issued to standards as the need arises on the basis of comments. Standards are also reviewed periodically. A standard along with amendments is reaffirmed when such review indicates that no changes are needed. If the review indicates that changes are needed, it is taken up for revision. Users of Indian standards should ascertain that they are in possession of the latest amendments or addition by referring to the latest issue of BIS Catalog and Standards, monthly editions. This Indian standard has been developed from Doc. No. CED 2, 5525. Amendments issued since publication. Amend No. Date of issue. Text affected. Headquarters, Bureau of Indian Standards, Manak Bhavan, 9 Bahadur Shah Zafar Marg, New Delhi. 110,002. Telephones, 23230131, 23233375, 23239402. Regional offices, Central, Manak Bhavan, 9 Bahadur Shah Zafar Marg, New Delhi. 110,002. Telegrams, Manak Sanstha, common to all offices. Telephone 2323 76 17 23233841 Eastern, 1/14C. IT Scheme VIIM VIP Road, Kankurgaki, Kolkata. 700,054 Northern, SEQ 335 to 336, Sector 34A, Chandigarh. 160,022 Southern C. IT Campus, Ivy Cross Road, Chennai. 600-113 Western, Manakalaya, E9 MIDC Moral and Hiri, East, Mumbai. 400-093, 23378499, 23378561, 2337 862, 23379120 600, and 3843 609,285 22S41216, 2254 1442 22542519, 22542331 S283292995, 2832 7858 28327891, 28327892. Branches, Ahmedabad, Bangalore, Bhopal, Bhubaneswar, Coimbatore, Faridabad, Ghaziabad, Guwahati, Hyderabad, Jaipur, Kanpur, Lucknow, Nagpur, Nalagarh, Patna, Pune, Rajkot, Thiruvananthapuram, Visakhapatnam. Printed at Government of Indica Press. Mayapuri, Ring Road, New Delhi. 110,064.